Hello there, and welcome to Life Beyond Seen, where curiosity settles in softly and science takes its time guiding us into places most of us have never been. Tonight, we're leaving behind the familiar world above and slipping downward into one of Earth's most hidden realms, a place so vast and yet so little known that we've explored more of the surface of Mars than we have of it. This is the deep ocean, the enormous shadowed heart of our planet where light dies, pressure builds, and life, against all odds, not only survives, but thrives. Before we begin this slow descent into that unseen world, I'd like to know where you are as you listen to this. Are you somewhere near the sea, where you can smell the salt in the air? Or are you hundreds of miles from any shore, with the idea of the ocean existing only as a map or a memory? However far you are from it right now, beneath your feet, thousands of meters below the waves, is a realm that operates under rules utterly different from those that shape our daily lives. And if you find these quiet journeys into the unknown a comforting way to end your day, I'd be grateful if you'd give this a like or subscribe so this small space of calm and curiosity can reach others who might be drifting off to sleep too. Let's start with something simple. If you stood on a beach right now and looked out at the ocean stretching before you, you might think of it as a surface. Water rolling, glittering, catching the sunlight, endlessly moving. But that thin, bright skin of water is only the beginning. Beneath it lies a vertical wilderness deeper and more alien than the surface of any other planet we've yet visited. Most of us think of the ocean as shallow because that's all we ever see. We swim near the shore, dive in the first few meters, maybe venture far enough to feel the pull of the tide tugging at our feet. But the average depth of Earth's oceans is nearly 4 kilometers, and in some places, like the Mariana Trench, the seafloor drops down nearly 11 kilometers below the surface. That's deeper than Mount Everest is tall. If you place the entire mountain into the Pacific Ocean, its peak would still be far below the surface, buried under layers of darkness and crushing pressure. And yet, life is there. Not just a few isolated microbes clinging to existence, but entire ecosystems built in conditions so extreme that, until recently, scientists weren't sure anything complex could live there at all. The deep ocean begins where sunlight fades, roughly 200 meters below the surface. At that depth, the last rays of the sun weaken into a ghostly blue twilight. Go deeper still, beyond 1,000 meters, and light disappears completely. This is the midnight zone, a world of permanent darkness where the daily rhythms of sunrise and sunset mean nothing. There's no photosynthesis here, no green plants turning sunlight into food. The surface world runs on light. Down here, life has found other ways to fuel itself. The journey into this hidden world is not a fast one. As you descend, the water grows colder and heavier, the pressure increasing by 1 atmosphere, about the weight of the air pressing on you at sea level. For every 10 meters you go down. At 1,000 meters, that's 100 times the pressure you feel on land. At 10,000 meters, the pressure is more than 1,000 times greater. It's the equivalent of having 50 jumbo jets stacked on top of you. Metal spheres have been crushed by that pressure. Submarines must be built like fortresses to survive it. Yet for countless species that call this place home, this is normal. Their bodies are adapted not just to endure the pressure but to rely on it. Remove many of them from these depths and bring them to the surface, and they simply can't survive. Their cells rupture, their organs fail. They are creatures of the deep in every sense. It's tempting to imagine the deep ocean as empty, a silent desert stretching endlessly beneath the waves. For a long time, scientists did too. In the early 20th century, oceanographers believed that life below about 600 meters would be sparse if it existed at all. Without sunlight, they reasoned, there could be no photosynthesis, and without photosynthesis, no food chain. What they didn't know was that life here had built a completely different system, one that doesn't depend on the sun at all. Instead of capturing light, organisms in the deep capture chemical energy. They feed not on plants but on particles drifting down from above, a slow, steady rain of detritus known as marine snow. Composed of dead plankton, fecal pellets, and fragments of organic material, marine snow is the primary food source for much of the deep sea. It drifts gently downward from the sunlit layers, sometimes taking weeks to reach the seafloor, where it sustains scavengers and filter feeders in the dark. But marine snow is only part of the story. In some places, life in the deep doesn't wait for hand-me-downs from the surface. It creates energy from the earth itself. At hydrothermal vents, cracks in the ocean floor where seawater seeps down, heats up, and blasts back out rich with minerals, bacteria and archaea use chemical reactions to convert those minerals into energy. This process, called chemosynthesis, forms the foundation of entire ecosystems, ones that exist completely independent of sunlight. Giant tube worms, clams, crabs, and fish cluster around these vents, thriving in water that can reach 400 degrees Celsius, just a few centimetres from near-freezing seawater. Here, life isn't just surviving in the dark, it's flourishing in a place where, by surface standards, it shouldn't exist at all. The sheer adaptability of life in these depths is staggering. Many deep-sea fish have bodies so soft and gelatinous that they would collapse under their own weight on land. Their muscles and bones are reduced to the bare minimum, conserving energy in a world where food is scarce. Some have evolved enormous mouths and expandable stomachs to swallow prey almost as large as themselves, an essential trick when meals might be weeks apart. Others use bioluminescence, producing light through chemical reactions in their bodies. In the eternal night, light becomes a tool, a lure, a language. Anglerfish dangle glowing bait to draw prey close enough to snap. Flashlight fish use bioluminescent bacteria living in pockets under their eyes to communicate or confuse predators. Some squid release glowing clouds instead of ink, dazzling attackers long enough to escape. In the absence of sunlight, life has learned to make its own. Pressure and darkness shape not just how these creatures look, but how they live. Metabolism slows in the cold, conserving energy. Lifespans stretch far longer than their shallow water relatives. Some deep-sea corals are estimated to be thousands of years old, growing millimetre by millimetre in the quiet gloom. Even reproduction follows its own logic. Many deep-sea species are hermaphrodites, or have unusual mating strategies, reducing the risk of never encountering a partner in the vast emptiness. The male anglerfish, for example, is tiny compared to the female. When he finds one, he latches onto her body and fuses with her bloodstream, becoming little more than a permanent source of sperm. In the deep, survival often means bending biology itself. And yet, despite these adaptations, the deep ocean remains one of the least explored regions on Earth. We've mapped Mars and the Moon in greater detail than the seafloor. Less than 20% of it has been surveyed with modern technology. Most of what we know comes from remote vehicles and deep-diving submersibles that can withstand the crushing pressure long enough to capture images, collect samples, and send them back to the surface. Each expedition reveals new species, new geological formations, and new mysteries. In 1977, scientists discovered hydrothermal vents for the first time, an entire ecosystem unknown to science until then. Since then, we've found methane seeps, cold water coral gardens, and creatures so bizarre they seem like science fiction. It's a reminder that our planet still holds secrets, and many of them lie hidden in the deep. The deep ocean also plays a crucial role in the health of the planet as a whole. It acts as a massive carbon sink, absorbing and storing vast amounts of carbon dioxide from the atmosphere. It regulates climate by transporting heat around the globe through deep ocean currents. It supports fisheries that feed billions of people and harbours genetic resources that may hold the keys to new medicines. And yet, it's also vulnerable. Deep-sea ecosystems are slow to recover from disturbance, and human activities, from deep-sea mining to trawling to climate change, are beginning to reach even these remote places. Sediment plumes from mining operations can smother fragile communities. Noise pollution from ships and drilling can disrupt communication among marine life. Even microplastics have been found in the deepest trenches, carried down by the same marine snow that once nourished life. Understanding how life survives here isn't just a matter of curiosity, it's a matter of urgency. The adaptations that allow organisms to thrive in darkness, pressure, and scarcity may hold lessons for biotechnology, medicine, and even the search for life beyond Earth. Moons like Europa and Enceladus, with their subsurface oceans sealed beneath ice, may host environments strikingly similar to Earth's deep sea. If life can flourish in the crushing dark beneath kilometres of water here, it might do the same out there. Studying these ecosystems may be our best guide to understanding where else in the cosmos life could exist. The story of the deep ocean is also a story about perspective. We tend to think of the ocean as a backdrop, something that exists around us, occasionally reminding us of its presence in the form of tides, storms, or vacations. But in reality, it dominates the planet. More than 70% of Earth's surface is covered by water, and most of that water is deep. The deep ocean is not a fringe environment. It is the main stage, the vast majority of Earth's living space. Life began in the sea and has evolved alongside it for billions of years. The surface world with its sunlight and air is the exception. The deep is the rule. It's humbling to think that while we build cities, launch satellites, and explore distant planets, there is still a realm beneath us where the unknown vastly outweighs the known. A realm where life thrives in ways that defy our expectations, where ecosystems exist without sunlight, and where evolution has taken forms we're only beginning to understand. The deep ocean reminds us that life is not fragile, that it does not cling only to comfort and familiarity. It adapts, it endures, it invents. Even in the most hostile corners of the planet, it finds a way. And so, as we prepare to journey deeper into this hidden world, it's worth pausing for a moment to imagine what lies beneath the waves just now. Not far from where you sit, creatures are drifting through the darkness, glowing softly in the black water. Entire landscapes stretch across the seafloor, mountains taller than Everest, trenches deeper than the Grand Canyon, fields of hydrothermal vents that roar with the heat of the Earth's interior. It's a world that has existed for eons, mostly unseen, mostly unknown, shaping the planet and cradling life in ways we're only beginning to grasp. We're standing at the edge of an unexplored universe, not above us in the stars, but below, hidden beneath a shifting blue skin. The deeper we go, the stranger and more extraordinary it becomes. Down there, light is not a given, but a gift. Energy does not fall from the sky. It seeps from the rocks. Life does not follow the rules we thought it must. It writes its own. And as we follow it into the darkness, we may discover not just how life survives without sunlight, but how it has always survived, by adapting, by evolving, and by turning the impossible into the ordinary. The surface of the ocean is a familiar sight, a restless skin of waves reflecting the sun, shifting under the wind, carrying ships and stories across its vastness. But beneath that restless surface lies another world entirely, one most of us will never see with our own eyes. It begins just beyond the reach of sunlight, a place that feels close when you look at the water, yet remains as remote as another planet. Our journey into that hidden realm begins not with a plunge into darkness, but with a slow, deliberate descent, a journey downward that transforms the ocean from a mirror of the sky into a universe all its own. The first few meters below the surface hardly seem alien at all. Sunlight pours through the water, scattering into shifting patterns that ripple across your vision. Fish dart in and out of view, their scales glinting like polished metal. Seagrasses sway gently in the current, and coral reefs bloom with colour and life. This upper layer, known as the epipelagic zone, is the ocean most of us know. It stretches from the surface down to about 200 meters, where light still penetrates strongly enough to support photosynthesis. Almost everything we associate with marine life, the vibrant reefs, the schools of fish, the playful dolphins and the towering kelp forests, exists within this narrow slice. It is, in planetary terms, the ocean's thin and fragile skin. As we descend past 200 metres, the light begins to change. It dims and cools, shifting from bright white to deepening blue. This is the mesopelagic zone, often called the twilight zone, a band of water where sunlight fades into memory. The deeper you go, the less light there is, until it becomes impossible for plants to survive. Photosynthesis ceases, and the food web built around it begins to unravel. In its place emerges a new way of living, one defined by scarcity, adaptation, and patience. Here, life depends on the rain from above, tiny particles of organic material drifting down from the sunlit surface. It is a slow, steady trickle, but for the creatures of the twilight zone, it is enough. The twilight zone is also where the ocean becomes more dynamic and mysterious. Vast clouds of small organisms known as zooplankton rise toward the surface each night to feed and retreat, back into the depths by day, a vertical migration involving billions upon billions of animals. It is the largest daily migration on Earth, happening every single day, and yet it occurs mostly unseen. Predators follow them, lanternfish, bristlemouths, squid, forming shifting layers of life that rise and fall like the ocean's heartbeat. It is here that bioluminescence becomes a common language. Tiny organisms flash to confuse predators, squid release glowing clouds to hide their escape, and fish light up their bellies to erase their silhouettes against the faint glow from above, a camouflage known as counter-illumination. Light here is no longer a gift from the sun, it is something life makes for itself. Beyond 1,000 meters, light disappears completely. The water turns black, and the ocean becomes a place defined by darkness and pressure. This is the bathypelagic zone, often called the midnight zone. No sunlight reaches this far and the temperature drops close to freezing. The pressure is immense, 100 times greater than at the surface, and increases by another atmosphere for every 10 meters you go deeper. To most land-dwelling creatures, such conditions would be instantly lethal. But life here is built differently. It does not resist the pressure. It is shaped by it. Its bodies are soft, its bones reduced, its movements slow and deliberate. Energy is scarce, and nothing is wasted. The deeper we go, the stranger life becomes. Some fish here have jaws so large they can swallow prey half their size. Others have transparent heads that allow them to see above them while staying hidden below. The gulper eel can open its mouth to a size far larger than its own body, ready to engulf anything that drifts within reach. The angler fish, with its glowing lure, waits motionless in the dark for prey to come to it. Energy is too precious to spend on unnecessary motion. Every adaptation is a strategy for survival in a world where food is rare and competition is fierce. If you could pause the descent here and look around, you might notice something remarkable. Despite the darkness, despite the pressure, despite the cold, the deep ocean is not empty. It is filled with life in every direction, drifting, glowing, hunting, waiting. Some creatures are solitary wanderers, others gather around rare sources of food, and still others form intricate relationships with one another. Tiny crustaceans ride on jellyfish, glowing bacteria live symbiotically inside fish, and scavengers gather in vast numbers when a whale carcass drifts down from above. Every part of this ecosystem is connected, every organism part of a web that stretches from the surface to the sea floor. At around 4,000 meters, the descent brings us to the abyssopelagic zone, the abyssal plains. Here, the ocean floor stretches out in vast flat expanses of fine sediment, interrupted by seamounts, canyons, and the occasional volcanic ridge. The pressure is more than 400 times that at the surface, and the temperature hovers just above freezing. Yet even here life persists. Sea cucumbers crawl slowly across the sediment, feeding on the constant rain of marine snow. Brittle stars and amphipods scavenge for whatever they can find. Strange fish patrol the bottom, their eyes adapted to detect the faintest glimmers of bioluminescent light. Some species spend their entire lives here, never venturing more than a few meters above the seafloor. The abyss is also where some of the most dramatic geological features on Earth are found. Mid-ocean ridges, vast mountain ranges formed by tectonic plates pulling apart, snake across the seafloor. At these ridges, magma rises from beneath the crust, creating new ocean floor and forming hydrothermal vents. These vents spew superheated, mineral-rich water into the surrounding sea, creating an environment unlike anywhere else on Earth. Here, life thrives without sunlight. Bacteria and archaea use the chemicals in the vent fluid to produce energy through chemosynthesis, forming the base of a unique food web. Tube worms grow to meters in length, their bodies harbouring symbiotic bacteria that provide them with nutrients. Giant clams and mussels cluster around the vents, and predatory crabs and fish patrol the edges of these oases. It is a vibrant, bustling community, existing in complete darkness, fueled not by the sun but by the heat of the Earth itself. Descending even further, past 6,000 meters, we enter the Hadal Zone, the deepest part of the ocean. Named for Hades, the Greek underworld, this zone is found only in deep ocean trenches, narrow, steep-sided depressions formed where tectonic plates collide. These trenches can reach depths of more than 10,000 meters, places so remote and extreme that only a handful of human beings have ever visited them. The pressure here is unimaginable, more than 1,000 times that at the surface, and yet life endures. Amphipods the size of dinner plates scavenge in the darkness. Snailfish, their bodies adapted to withstand the pressure, swim gracefully along the trench walls. Microbes thrive in the sediment, feeding on chemical energy seeping from the rocks. Even here, in the deepest, darkest corners of the Earth, life finds a way. Our descent into this hidden world is more than just a journey through water, it is a journey through time. Much of the life we see here has changed little in millions of years. Some deep-sea species are so ancient that they are often called living fossils, their lineages stretching back to the earliest days of complex life. The environment itself is stable and unchanging, insulated from the storms, seasons and fluctuations that shape life at the surface. Evolution here moves slowly, and the creatures that inhabit this world are finely tuned to its demands. Remove them from it, and they cannot survive. They are not just living in the deep ocean, they are of it. The first human attempts to explore this realm were cautious and clumsy. In the 19th century, weighted ropes and dredges were lowered from ships, bringing up samples from the deep. These early expeditions revealed strange and unfamiliar creatures, many of which did not survive the journey to the surface. As technology advanced, so did our ability to explore. The bathyscaphe Trieste, a small spherical submersible, descended nearly 11 kilometers into the Mariana Trench in 1960, carrying 2 men into the Hadal Zone for the first time. They saw a world few had imagined, a flat, featureless seafloor, life sparse but present, and a silence so complete it felt almost alive. Since then, remotely operated vehicles and deep-diving submersibles have carried cameras and instruments into places no human could survive, revealing landscapes and life forms stranger than anything we expected. Each descent teaches us more, but it also reminds us how little we know. More than 80% of the ocean remains unexplored, and the deep sea holds countless secrets still waiting to be discovered. New species are found with almost every expedition, many of them unlike anything seen before. Some glow with bioluminescence in ways that defy explanation. Others feed on chemical reactions we barely understand. Entire ecosystems exist around methane seeps and brine pools. Underwater lakes of saltier, denser water that collect on the seafloor like alien seas within the sea. Even the geology of the deep is full of surprises, from towering undersea volcanoes to vast fields of manganese nodules that grow at a rate of just a few millimeters every million years. exploring this world is not easy. The pressure alone is enough to crush most equipment. Temperatures near freezing complicate engineering. Darkness demands powerful lighting systems, and the vastness of the ocean makes navigation a challenge. Every dive is a technical and logistical feat, requiring careful planning, precise control, and no small amount of courage. Yet despite these challenges, we keep going deeper. The rewards are too great to ignore. Each discovery reshapes our understanding of life, evolution, and Earth itself. Each new species challenges our assumptions about where and how life can exist. Each sample of water or sediment holds clues to the planet's past and hints about its future. And still, as extraordinary as all of this is, the most profound lesson of the deep ocean may be a simple one: that life is more resilient, more inventive, and more adaptable than we ever imagined. It is not confined to the narrow band of conditions we consider normal. It does not require sunlight, gentle pressure, or warm temperatures. It can thrive in darkness, in crushing weight, in freezing cold, and in chemical chaos. It can build communities where none should exist and endure in places that seem utterly inhospitable. The deep ocean shows us the full range of life's creativity, and in doing so, it broadens our sense of what is possible, not just on Earth, but anywhere in the universe. As our descent continues, we begin to understand that the deep sea is not a single place, but a continuum, a gradient of change stretching from the familiar world above to the alien world below. Each layer brings new challenges and new solutions. Each step downward reveals another way life has solved the puzzle of survival. And while we've mapped only the edges of this vast realm, we know enough to see that it is not lifeless or barren. It is vibrant, complex, and deeply interconnected, a living system that sustains itself without sunlight, and has done so for millions of years. There is something humbling about looking out into that darkness, about realizing that beneath the surface of our planet lies an entire biosphere we're only beginning to understand. It is a reminder that our world is bigger, stranger, and more wondrous than we often remember. It is also a reminder that even here, in the most extreme corners of Earth, life not only survives but flourishes, writing stories in the dark that we are only now learning to read. And as we go deeper still, those stories will only become more intricate, more surprising, and more essential to understanding our planet and our place within it. The first descent is just the beginning. Ahead lies a world where light is a memory, where energy bubbles up from the Earth's core instead of streaming from the sun, where evolution has taken paths we could never have predicted. It is a world where life has rewritten the rules, and in doing so, revealed truths that reach far beyond the ocean. And as we continue downward, deeper into this vast hidden universe beneath the waves, the story of how life survives here will unfold in ways more intricate and astonishing than anything we have seen so far. The deeper you travel beneath the surface, the more you begin to understand that the ocean is not just a vast body of water, but a world governed by forces far beyond those we experience on land. The most relentless of these forces is pressure, an invisible weight that builds silently with every meter you descend. At sea level, we live under the weight of the atmosphere, the mass of air pressing down on us from above. We don't feel it because our bodies have adapted to it over millions of years. But water is far denser than air, and it exerts pressure much more powerfully. Every 10 meters you travel downward adds another atmosphere of pressure. At 100 meters, the weight is 10 times greater than what you feel on land. At 1,000 meters, it is 100 times greater, and by the time you reach the deepest trenches, more than 10,000 meters down, the pressure is over 1,000 times what you're used to. It's a force so immense it can crush metal, warp steel, and turn air-filled spaces into imploded shells. For most of human history, this made the deep ocean an unreachable frontier. Even the earliest diving bells and primitive submersibles could only descend a few hundred meters before the pressure became too great. Beyond that, the weight of the water was simply too overwhelming. It wasn't until the 20th century that technology advanced enough to send humans safely into the deep. And even now, building something capable of withstanding those crushing forces is one of the greatest engineering challenges we face. Submersibles designed for the deepest dives are not sleek, streamlined vessels, but spherical, heavily reinforced capsules with walls up to 20 centimeters thick. Their windows are small and made of specially shaped acrylic or glass, designed to distribute the pressure evenly. Even the slightest flaw, a microscopic crack, an imperfect weld, can mean disaster. At those depths, there is no margin for error. The ocean is not forgiving. Pressure shapes everything in the deep sea. It shapes the environment, the geology, the water itself, and most of all, the life that calls it home. Creatures that live under these conditions are not merely tolerating the pressure, they are built by it. Their bodies are flexible and compressible, their tissues often gelatinous rather than rigid. Many deep-sea fish lack swim bladders, the gas-filled organs that help shallow water fish control their buoyancy. A gas bladder would collapse under the immense pressure of the deep, so instead, these animals rely on oil-filled organs or simply allow their bodies to match the density of the surrounding water. Their bones are often reduced or replaced with cartilage. Their muscles are softer, less structured, and their enzymes are adapted to function under immense compression. Remove them from this environment and bring them to the surface, and they are no longer in balance. Their bodies may rupture, their proteins may denature, and they may die within moments. They are creatures not just of the ocean, but of the pressure itself. Even the chemistry of life changes under such conditions. At high pressure, water molecules pack more tightly together, and chemical reactions occur differently. Membranes that are fluid and flexible at the surface become stiff and brittle under pressure. So deep-sea organisms have evolved unique lipids that remain fluid even when compressed. Proteins, too, must be adapted. The shapes they fold into, which are crucial for their function, can be distorted by pressure. To compensate, many deep-sea species produce specialized molecules called piezolites, small organic compounds that stabilize proteins and prevent them from losing their shape. These adaptations are invisible, occurring at the molecular level, but they are the difference between life and death in a world where pressure never relents. Pressure also affects how sound and light behave. In the deep ocean, sound travels farther and faster than it does near the surface, allowing some animals to communicate across vast distances. Light, on the other hand, is quickly absorbed by water. Even the faintest trace of sunlight is gone by 1,000 meters down. The only illumination comes from bioluminescence, the cold chemical light produced by living organisms, and even that is shaped by pressure. The structures that create bioluminescence, the luciferins and luciferases that react to emit light, must work under conditions that would disable their surface-dwelling counterparts. Every system, from communication to metabolism, is re-engineered by the physics of the deep. For humans, pressure is a constant and deadly hazard in deep-sea exploration. A small leak in a submersible at great depth can become a catastrophic implosion in an instant. Equipment must be meticulously tested, every seal and weld inspected and reinforced. Even remotely operated vehicles which don't carry humans face enormous challenges. Electronics must be shielded, cameras encased, and robotic arms designed to function reliably under crushing forces. The deeper we go, the harder it becomes to explore. At depths beyond 6,000 meters, few machines are capable of functioning for long. The Hadal Trenches, the deepest parts of the ocean, remain among the least visited places on Earth, not because we lack curiosity, but because pressure itself is a gatekeeper. This relentless force also influences the landscape of the deep. Sediments behave differently under immense weight, compacting into dense layers that preserve a record of Earth's history stretching back millions of years. The movement of tectonic plates, too, is shaped by pressure. Subduction zones, where one plate is forced beneath another, create deep trenches and immense geological forces that can trigger earthquakes and volcanic eruptions. Hydrothermal vents and cold seeps, where fluids escape from the sea floor, exists because of the interplay between pressure, temperature, and geology. Even water itself behaves differently here. Under the weight of thousands of meters of ocean, its density increases and its freezing point drops slightly. At extreme depths, water can even become supercritical, a state that is neither liquid nor gas, creating environments with properties unlike anything at the surface. The challenges posed by pressure extend to the smallest inhabitants of the deep. Microbes that live in the sediments thousands of meters below the surface must carry out life's most basic processes: replication, metabolism, repair, under conditions that would destroy surface-dwelling organisms. Some of these microbes are barophilic, meaning they require high pressure to grow. They have enzymes that only function properly when compressed, and membranes that fall apart if the pressure drops too low. These organisms not only survive, but thrive under conditions that would crush others. Studying them has revealed surprising insights into the flexibility of life, and has even informed research into how life might exist on other worlds, such as the icy moons of Jupiter and Saturn, where liquid water may lie beneath thick layers of ice. Pressure also influences how larger animals behave. Many deep-sea creatures move slowly, conserving energy in an environment where food is scarce and the cost of movement is high. Their metabolic rates are often lower than those of shallow water species, and their reproductive cycles may be slower as well. Some species grow to enormous sizes, a phenomenon known as deep-sea gigantism, possibly because larger bodies are more efficient in the cold, pressurized environment. The giant isopod, for example, is a relative of the pill bugs you might find in a garden, but in the deep sea it can grow to over 1/2 meter long. The Japanese spider crab, another deep dweller, has a leg span of up to 4 meters. These are not exceptions, but examples of how pressure shapes biology in unexpected ways. The effects of pressure extend beyond individual organisms to entire ecosystems. Around hydrothermal vents, for example, the intense pressure helps keep water in a liquid state even at temperatures above 300 degrees Celsius. Without that pressure, the superheated fluids would boil away instantly. The organisms that live there, from chemosynthetic bacteria to giant tube worms, depend on these conditions. If the pressure were suddenly reduced, the ecosystem would collapse. This is why attempts to recreate deep-sea environments in laboratories are so difficult. It is not enough to simulate the temperature or chemistry. The pressure must be replicated as well, and that requires specialized equipment capable of containing forces that would crush almost anything else. Our understanding of pressure's role in the deep ocean is still evolving. Each expedition brings new data and new questions. How do organisms sense pressure? How do they repair the molecular damage it causes? How did life evolve to tolerate or even require such extreme conditions? These are not just questions about the ocean, they are questions about life itself. The answers could reshape our understanding of biology, evolution, and the limits of life on Earth and beyond. Pressure also serves as a reminder of the interconnectedness of Earth's systems. The same forces that shape the deep ocean influence the atmosphere, the climate, and even the continents themselves. The weight of the water helps drive ocean circulation, which in turn regulates global temperatures. The movement of tectonic plates under immense pressure shapes the seafloor, creating mountains, trenches, and volcanic vents. Even the carbon stored in deep sea sediments, compressed over millions of years, plays a role in the planet's long-term climate stability. The deep ocean is not an isolated world. It is a fundamental part of the Earth system, and pressure is one of the threads that binds it all together. Humans, too, are shaped by pressure, even if we rarely think about it. Our bodies evolved under the constant weight of the atmosphere, and our biology depends on it. Divers who descend too quickly or ascend too rapidly can experience decompression sickness, as dissolved gases form dangerous bubbles in their blood. Submarines must carefully manage internal pressure to keep their crews safe, and in the rare instances where humans have ventured into the Hadal depths, they have done so inside meticulously engineered capsules designed to keep the crushing weight at bay. Pressure is a universal force, one that shapes not only the deep ocean but also the surface world we inhabit. Yet for all its danger and difficulty, pressure is also a source of possibility. It has created environments and forms of life that would be impossible without it. It has preserved records of Earth's history in the sediments of the sea floor. It has shaped the chemistry and physics of the deep in ways that continue to surprise us. And it may hold clues to questions we have yet to ask, about the origins of life, the potential for life elsewhere, and the ways in which living systems can adapt to conditions we once thought uninhabitable. Exploring this world means confronting pressure not as an obstacle, but as a fundamental part of the environment. It is not something to be defeated or avoided. It is a defining feature of the deep, as essential to its character as darkness or cold. To understand life in the deep ocean, we must understand how it responds to pressure, how it bends, adapts, and thrives under its weight. And as we continue to push deeper, both literally and figuratively, into this hidden realm, pressure will remain one of the central challenges and one of the greatest sources of discovery. Even in the quietest moments of the deep, pressure is always present. It presses down on every cell, every structure, every movement. It shapes the way sound travels, how light behaves, how rocks fracture, and how fluids flow. It is the constant background to every story the deep ocean tells. And though we may never feel it directly, its influence reaches us too. It affects the currents that shape our climate, the carbon that cycles through our atmosphere, the resources that form beneath the sea floor. The weight of the ocean is part of the weight of the world. As we continue deeper into this vast and hidden realm, the lessons of pressure remain with us. They remind us that life is not fragile but flexible, that it can adapt not just to the absence of light or the scarcity of food, but to forces that seem overwhelming. They remind us that even the most powerful constraints can become the conditions for new forms of life. And they remind us that the deep ocean, for all its strangeness, is not a world apart but a vital part of the planet we call home. Down here, beneath the waves, under the weight of 1,000 atmospheres, life endures, and in enduring it teaches us just how boundless its possibilities truly are. The deeper we descend, the more the ocean reveals itself not as a lifeless void, but as a place teeming with activity, invention, and endurance. It's a realm where life has had to solve problems utterly unlike those faced on the surface, and in doing so, it has demonstrated just how flexible and creative evolution can be. Long before humans built machines capable of surviving the pressure, or lights bright enough to pierce the darkness, life was already there, quietly adapting, refining, and thriving. The story of how it began and how it persists is one of nature's most remarkable achievements, a testament to the resilience that lies at the heart of every living thing. For much of history, scientists assumed the deep ocean was barren. Without sunlight, they reasoned, there could be no photosynthesis, and without photosynthesis, no life. It was a neat and logical conclusion, but it was also wrong. The first clues that life might exist in the deep came not from explorers, but from dredges and trawls dragged along the seafloor in the 19th century. When they were hauled back up, they often brought with them strange and unexpected creatures, soft-bodied sea cucumbers, spindly brittle stars, and ghostly fish with oversized eyes. These discoveries hinted at a hidden biosphere beneath the waves, but they raised more questions than they answered. How could these creatures survive with so little food? What were they eating? And where did the energy come from to sustain them? The first answers came slowly. Scientists realized that the ocean surface was not a closed system. Every day, trillions of tiny organisms lived, fed, reproduced, and died in the sunlit waters above. As they decayed, their remains sank. Some of it drifted down as microscopic particles, forming a slow but steady rain of organic material known as marine snow. It fell constantly, blanketing the deep ocean with a thin layer of nutrients. Most of it was consumed long before it reached the abyss, but enough survived the journey to sustain life in the darkness below. For many deep-sea creatures, this rain of debris is their primary source of food. They sift it from the water, filter it from the sediment, or scavenge it from the sea floor. It is a meagre existence, but it is enough. Even larger events occasionally deliver bounty to the depths. When a whale dies and its body sinks to the seafloor, it becomes a feast that can sustain entire communities for decades. These whale falls attract scavengers from miles away, hagfish, amphipods, sleeper sharks, which strip the flesh within weeks. Bacteria move in next, breaking down the remaining tissues and releasing nutrients into the surrounding water. Finally, specialized organisms called bone-eating worms colonize the skeleton, consuming lipids within the bones themselves. Each stage supports different species, creating a succession of ecosystems that can persist for generations. It is a stark reminder that in the deep ocean, nothing is wasted. Every scrap of organic matter is precious, every morsel reused and recycled in the endless struggle for survival. But marine snow and whale falls are not the whole story. In 1977, scientists exploring the Galapagos Rift in the eastern Pacific Ocean discovered something that would change our understanding of life forever. While investigating a region of seafloor spreading, they came across towering hydrothermal vents, spewing superheated, mineral-rich water into the cold abyss. Around these vents were dense communities of organisms, giant tube worms, clams, mussels, crabs and fish, thriving in complete darkness. It was a revelation. Here was an ecosystem that did not depend on sunlight or photosynthesis. Instead, it was powered by chemosynthesis, a process in which bacteria and archaea convert inorganic chemicals like hydrogen sulfide into energy. These microbes form the base of a new kind of food web, one that existed entirely independent of the surface world. The discovery of hydrothermal vent communities rewrote the rules of biology. It showed that life could thrive without sunlight, relying instead on the chemical energy stored deep within the Earth. It also suggested that life on Earth might have begun in places like this, in the dark, mineral-rich waters around ancient vents, where chemical reactions provided the energy needed to build complex molecules. Some scientists now believe that hydrothermal systems may have been the cradle of life itself, and that similar environments on icy moons like Europa or Enceladus could harbour life today. What was once thought to be a biological curiosity has become central to our understanding of a life's origins and its potential beyond Earth. The pioneers of these deep-sea ecosystems are the microbes that live at the base of the food chain. They are astonishingly diverse, capable of using a range of chemical reactions to fuel their metabolism. Some oxidize hydrogen sulfide, others methane or ammonia. Some fix carbon dioxide into organic matter, just as plants do, but without the need for sunlight. These microbes live in dense mats around hydrothermal vents, coat the surfaces of rocks, and even inhabit the bodies of larger animals. Many vent species have symbiotic relationships with bacteria, hosting them inside their tissues in exchange for nutrients. The giant tube worm, Riftia pachyptila, has no mouth, no stomach, and no digestive system. Instead, it relies entirely on symbiotic bacteria, living inside a specialized organ called a trophosome. The bacteria convert hydrogen sulfide from the vent fluid into organic compounds, which the worm then absorbs. It is an elegant partnership, a collaboration between two forms of life that allows both to thrive where neither could survive alone. Other organisms take advantage of the vent environment in different ways. Mussels and clams filter bacteria directly from the water. Crabs and shrimp graze on microbial mats. Predatory fish and octopuses hunt the creatures that gather around the vents. Even scavengers benefit, feeding on the remains of animals that live and die in this unusual ecosystem. It is a complete food web, built not on sunlight but on the chemistry of the Earth itself. Hydrothermal vents are not the only sites of chemosynthetic life in the deep ocean. Cold seeps, where hydrocarbons like methane and hydrogen sulfide seep from the seafloor, support similar communities. These seeps are less dramatic than vents. Their fluids are cooler and flow more slowly, but they host rich ecosystems nonetheless. Mussels and clams cluster around the seeps, supported by symbiotic bacteria that oxidize methane or sulfide. Tube worms grow in dense colonies, some living for centuries. Bacterial mats carpet the sediment, providing food for grazing snails and crabs. As at vents, the entire system is driven by chemical energy, independent of sunlight. These discoveries have expanded our understanding of where life can exist and how it can sustain itself. They show that the deep ocean is not a biological desert, but a mosaic of ecosystems, each built on a different source of energy. Some rely on the rain of organic material from above, others on the carcasses of large animals, and still others on the chemical energy that seeps from the Earth's crust. Together, they form a vast and interconnected web of life that spans the depths, linking the surface to the seafloor in ways we're only beginning to understand. The adaptations that allow life to persist in these extreme environments are as varied as they are ingenious. Many deep-sea species have evolved metabolic pathways that function efficiently under high pressure and low temperature. Their enzymes are flexible, their membranes fluid, their proteins stabilized by specialized molecules. Some microbes can switch between different energy sources depending on what is available, an ability known as metabolic versatility. Others form biofilms, dense cooperative communities that protect them from environmental stress. Still others enter dormant states when conditions are unfavorable, waiting patiently for better times to return. Larger organisms, too, display remarkable adaptations. Many deep-sea fish have enormous mouths and expandable stomachs, allowing them to swallow prey almost as large as themselves, a crucial advantage in a world where meals are rare and unpredictable. Others have specialized sensory organs that detect the faintest movements or chemical traces in the water, helping them locate food in the darkness. Some rely on bioluminescence to lure prey, attract mates, or communicate. In the deep sea, where light is scarce and energy is precious, every adaptation is honed by necessity. The diversity of life in the deep ocean is astonishing, and much of it remains undiscovered. Each expedition reveals new species, strange gelatinous creatures that drift through the water, bizarre crustaceans with unexpected forms, worms that build tubes from minerals, and microbes that thrive in conditions once thought lethal. Many of these organisms have no close relatives in the surface world, their evolutionary paths shaped by millions of years of isolation. The deep ocean is a vast laboratory of evolution, a place where life experiments with new solutions to old problems. Some of these adaptations may even hold clues to fundamental questions about life itself. How does life originate? What are the minimum conditions required for it to persist? How do organisms cope with extreme environments? By studying the pioneers of the deep, scientists hope to answer these questions, not just to satisfy curiosity, but to better understand our own origins and the potential for life elsewhere in the universe. The discovery of chemosynthetic ecosystems on Earth has already transformed our search for extraterrestrial life, shifting the focus from planets with sunlight to worlds with internal heat and liquid water. If life can thrive around hydrothermal vents in the darkness of Earth's oceans, it might also exist beneath the ice of Europa or in the subsurface seas of Enceladus. The resilience of deep-sea life also offers lessons for biotechnology and medicine. Enzymes from barophilic microbes are used in industrial processes that require high pressure. Bioluminescent proteins from deep-sea organisms are used as markers in molecular biology. Compounds produced by vent bacteria may hold promise as new antibiotics or anti-cancer agents. The adaptations that allow these organisms to survive in the deep are not just scientific curiosities, they are tools with the potential to improve human life. Yet for all we have learned, the deep ocean remains one of the least understood parts of our planet. Less than a fraction of 1% has been explored in detail. The vast majority of its inhabitants have never been seen, let alone studied. Each dive into the depths is a step into the unknown, a chance to encounter forms of life that defy our expectations and expand our understanding of what it means to be alive. And each discovery reminds us that the deep is not a static, lifeless realm, but a dynamic, evolving ecosystem as complex and interconnected as any on the surface. It is easy to think of life as fragile, dependent on narrow ranges of temperature, pressure, and chemistry. But the deep ocean tells a different story. It shows us that life is not just a passenger on Earth, but a force that shapes and reshapes its environment, finding ways to persist even in the most hostile conditions. It shows us that where there is energy, from sunlight, from chemical reactions, from the slow decay of organic matter, life will find a way to use it. And it shows us that even in the deepest, darkest corners of the planet, where the weight of the water is crushing and the cold is constant, life not only endures but flourishes. The pioneers of the abyss are more than just inhabitants of a hidden world. They are reminders of life's fundamental nature, its resilience, its adaptability, its unending capacity for invention. They teach us that survival is not about overcoming obstacles, but about turning them into opportunities. The pressure that would crush most organisms becomes the condition that shapes new forms. The darkness that seems lifeless becomes a canvas for bioluminescence. The absence of sunlight becomes the catalyst for new ways of generating energy. In the deep ocean, life is not diminished by the harshness of its environment. It is defined by it. As our understanding of this hidden realm deepens, so too does our appreciation of life's capacity to surprise us. We once thought the deep ocean was barren, yet it is home to some of the most extraordinary ecosystems on Earth. We once believed life needed sunlight, yet it thrives in total darkness. We once imagined that pressure was a barrier, yet it has become a condition for life's success. The story of the pioneers of the abyss is not just a story about adaptation. It is a story about possibility, about the boundless ways in which life can shape itself to meet the challenges of its world. And as we continue downward into this vast, uncharted realm, the story is far from over. Ahead lie even stranger worlds, places where geology and biology intertwine, where ancient lineages persist unchanged for millions of years, where life builds entire communities around sources of energy that have nothing to do with the sun. The pioneers we've met so far are only the beginning, the first signs of a deeper and more complex story waiting in the darkness below. There is a point in the ocean where sunlight, so abundant and unquestioned at the surface, begins to falter. It doesn't happen suddenly. There's no clear line where day turns to night, no obvious threshold where one world ends and another begins. Instead, the light thins gradually as you descend, scattering and weakening with every meter. Reds and oranges fade first, swallowed quickly by the water. Yellows and greens follow, growing dimmer and dimmer until only blue remains. And then, even that begins to dissolve into darkness. This is the twilight zone, a band of ocean that stretches roughly from 200 meters down to about 1,000. It is a place where daylight becomes a memory, where the sun still matters but no longer rules, and where life has adapted to a world balanced delicately between light and dark. The twilight zone is unlike any other region of the ocean. Too deep for photosynthesis, it cannot support plants or algae, which rely on sunlight to convert carbon dioxide into energy, and yet it is too shallow to be considered part of the deep, where light is gone entirely. It is an in-between world, a realm defined by transition and adaptation. Life here exists in a state of constant negotiation, with the fading light, with the scarcity of food, with the pressure that grows steadily stronger as the water deepens around it. It is one of the most mysterious and least explored parts of the ocean, and yet it plays a vital role in the health of the entire planet. One of the most remarkable features of the Twilight Zone is its role as a conduit between the surface and the deep. It is here that the rain of organic matter from above slows and begins to transform. Tiny particles of dead plankton, fecal pellets, and fragments of detritus drift downward from the sunlit zone, forming what scientists call marine snow. In the twilight zone, this snow becomes the foundation of the ecosystem. Countless organisms feed on it, from microscopic bacteria to larger filter feeders. As they consume and process this material, they change its composition, making it more or less likely to continue its journey to the seafloor. Some of it is broken down and recycled back into the water column. Some clumps together into larger particles that sink faster. Some becomes the food that sustains life deeper down. The twilight zone is the ocean's great recycler, a critical step in the movement of carbon from the atmosphere to the abyss. This vertical flow of carbon, known as the biological pump, is one of the most important processes on Earth. Without it, carbon dioxide would accumulate in the atmosphere at far higher levels than it does today, and the planet's climate would be drastically different. Tiny plankton at the surface capture carbon through photosynthesis. When they die, their remains sink into the twilight zone, where much of it is consumed and transformed. What escapes further downward eventually becomes buried in deep-sea sediments, locking carbon away for centuries or even millennia. The twilight zone is thus a key part of Earth's climate system, a hidden regulator of the air we breathe and the temperature we live in. The animals that inhabit this dimly lit realm are as fascinating as they are diverse. Many are small, fragile creatures that drift with the currents: copepods, krill, jellyfish, and salps. Others are active hunters, adapted to the low-light environment with oversized eyes and sensitive lateral lines that detect the faintest vibrations in the water. Lanternfish, one of the most abundant vertebrates on the planet, are a defining species of the twilight zone. They are small, rarely longer than a few centimeters, but their numbers are staggering. Billions of them inhabit these waters, forming dense layers that rise and fall each day in a synchronized migration that dwarfs any movement on land. This daily vertical migration is one of the most extraordinary phenomena in the natural world. As night falls, vast swarms of twilight zone creatures ascend toward the surface to feed on the rich plankton in the sunlit waters. Before dawn, they retreat back into the safety of the dim depths. It is a journey undertaken by trillions of animals every single day, a cycle driven by the need to balance food and safety. Near the surface, there is abundance but also danger. Predators like tuna, squid, and dolphins patrol the upper waters. In the twilight zone, food is scarcer, but the darkness offers protection. The migration is a compromise, an evolutionary solution to the challenge of living in a world where resources and risks are unevenly distributed. This daily movement has consequences that extend far beyond the lives of the animals themselves. As they feed at the surface and return to the depths, they transport carbon and nutrients downward, accelerating the biological pump and helping to regulate the global climate. Their vertical journeys also shape the distribution of predators and prey throughout the ocean. Tuna, whales, and seabirds follow the migrating masses, timing their feeding to match the nightly ascent. Even deep-sea creatures benefit, as the rain of waste and remains from these daily movements enriches the waters below. The twilight zone, though hidden and dim, is a dynamic and vital part of the ocean's living system. Survival here demands extraordinary adaptations. Eyes are among the most striking. In the fading light, vision becomes both more important and more difficult. Many twilight zone fish have enormous tubular eyes that gather the maximum amount of light and are tuned to the wavelengths that penetrate deepest into the water, mostly blues and greens. Some species can detect bioluminescence, the faint glows produced by other organisms, giving them an advantage in hunting or avoiding predators. Others rely less on sight and more on other senses, detecting vibrations, electrical signals, or chemical cues in the water. Bioluminescence itself is a defining feature of this zone. With sunlight reduced to a dim haze from above, Many organisms produce their own light through chemical reactions within their bodies. It serves many purposes. Some species use it for camouflage, counter-illuminating their bellies to match the faint glow from above and erase their silhouettes. Others use it to lure prey, dangling glowing appendages or flashing patterns that attract curious victims. Some use it to communicate, sending signals to potential mates or warning rivals to stay away. And still others use it defensively, releasing bursts of light to startle predators or create a distraction as they flee. In the twilight zone, light is no longer just something to see by. It is a language, a weapon, and a tool of survival. Many creatures here are masters of stealth. Transparency is a common strategy. By being nearly invisible, animals can avoid detection in the dim light. Some gelatinous zooplankton are almost entirely transparent, their bodies little more than ghostly outlines drifting through the water. Others use reflective scales or mirrored surfaces to scatter light and blend into their surroundings. Some species change colour depending on depth, becoming red, a colour that is quickly absorbed by water and appears black in the twilight zone, or adopting dark hues that help them disappear against the gloom. Predation takes on new forms in this environment. Because food is scarce, many Twilight Zone predators have evolved to maximise efficiency. Some have large mouths and distensible stomachs, allowing them to swallow prey almost as large as themselves. Others have needle-like teeth and lightning-fast strikes to capture fast-moving prey before it escapes. Some hunt by ambush, lying motionless and invisible until an unsuspecting meal drifts within reach. Every adaptation is shaped by the constant trade-off between energy gained and energy spent. In a world where meals may be infrequent and hard-won, efficiency is everything. The Twilight Zone is also a realm of giants and miniatures. Some creatures grow far larger than their shallow water relatives, their size and adaptation to the cold and the scarcity of food. The giant ostracod, a type of crustacean, can be several times larger than its shallow water kin. Certain siphonophores, colonial organisms related to jellyfish, can reach lengths of over 40 meters, making them among the longest animals on Earth. At the same time, many Twilight Zone inhabitants are tiny, drifting passively with the currents. Their small size an advantage in conserving energy and surviving on limited resources. This coexistence of extremes, vast and minute, fast and slow, luminous and invisible, is part of what makes this region so ecologically rich. Despite its importance, the Twilight Zone remains one of the least understood parts of the ocean. Its sheer size and depth make it difficult to study, and its inhabitants are often delicate, destroyed by the change in pressure when brought to the surface. Much of what we know comes from nets and sensors that sample small portions of it, or from remotely operated vehicles that can withstand the pressure and darkness. Even so, new discoveries are made regularly. New species, new behaviours, new insights into the role this region plays in Earth's systems. And with each discovery, our picture of the Twilight Zone becomes more detailed and more complex. Humans have begun to realise that this hidden layer of the ocean is more important than we ever imagined. Its role in regulating the climate makes it a critical part of Earth's future, but it is also vulnerable. Overfishing threatens to disrupt the delicate balance of life here, particularly as demand grows for species like lanternfish as a source of fish meal. Climate change is altering ocean temperatures and currents, which could affect the vertical migration patterns and the efficiency of the biological pump. Pollution too reaches even this remote zone, with microplastics and chemical contaminants found in animals that live hundreds of meters below the surface. The Twilight Zone is vast and remote, but it is not untouched. Efforts are now underway to study and protect this critical part of the ocean. Scientists are developing new technologies to explore it more thoroughly. Autonomous vehicles that can travel long distances and sample the water column in detail. Advanced sensors that can track carbon flux and migration patterns, and delicate collection devices that can bring fragile organisms to the surface intact. International bodies are discussing ways to manage fishing in the twilight zone to ensure that it remains sustainable. And climate scientists are working to better understand how changes in the surface environment might ripple downward into this hidden realm. The more we learn, the clearer it becomes that the twilight zone is not just an obscure layer of the ocean, it is a crucial part of Earth's life support system, connecting the surface to the depths, recycling nutrients, storing carbon, and sustaining vast populations of life. It is a place where evolution has crafted solutions to challenges we're only beginning to grasp. And it is a place that reminds us of the complexity and interconnectedness of the natural world. The sunlight that fuels life at the surface does not simply stop at 200 meters. It echoes downward in the form of organic matter, migration, and chemical cycles, shaping life in the dim light below. Standing on the deck of a ship and looking out over the ocean, it is easy to forget that just a few hundred meters beneath you lies this hidden world. It is not visible from above, and yet it is teeming with life, movement, and activity. It is a world where day and night blur together, where light is a fleeting visitor and darkness a constant companion. It is a world of adaptations both subtle and spectacular, where life thrives on scarcity and finds ways to make the most of every opportunity. And it is a world that, though remote, shapes the conditions of the planet above. As we descend deeper still, the last traces of sunlight will vanish, and the ocean will enter a realm where darkness is complete. There, life will face new challenges and reveal new solutions, but the twilight zone remains a vital threshold, a place where the surface world fades but still lingers, where light becomes memory, and where life continues its endless dance between abundance and scarcity, predator and prey, light and dark. And as we pass through it on our way downward, we carry with us the knowledge that even here, in this half-lit world, life not only endures but shapes the fate of the entire planet. Past the faintest reach of sunlight, beyond the shifting blues of the twilight zone, there is a depth where light ceases to matter at all. The last photons from above are scattered into nothing, swallowed by the sheer mass of water pressing down from every direction. Vision, so essential in the surface world, becomes irrelevant here. Plants which rely on sunlight to live vanish entirely. The daily cycle of dawn and dusk disappears. There is no sunrise, no sunset, no shadow, no horizon. Time itself feels different in this place, stripped of the rhythms that shape life on land. This is the midnight realm, the deep ocean beyond 1,000 meters, a world in perpetual darkness. It is as close as one can get to an alien world without leaving Earth, and yet it covers more of our planet than all of the continents combined. For a long time, scientists assumed that such a place would be lifeless. Deprived of sunlight, cut off from the energy that fuels nearly all ecosystems at the surface, what could possibly survive here? But the more we explore, the clearer it becomes that the absence of light does not mean the absence of life. In fact, the midnight zone is teeming with it. Creatures of every shape and size drift, crawl, and swim through this darkness, each perfectly adapted to a world where light is not a given, but an irrelevance. They have turned the challenges of their environment into opportunities, evolving strategies and physiologies so different from our own that they often seem more like science fiction than biology. The physical environment of the midnight zone is unlike anything most of us can imagine. The pressure here is immense, hundreds of times greater than at the surface, and it increases steadily with depth. Temperatures hover just above freezing, a constant cold that slows metabolism and shapes every aspect of life. The water is still and heavy, its movement governed by deep currents that flow far more slowly than the tides and winds above. Food is scarce, arriving mostly as a slow rain of particles from the surface, or as the occasional large carcass that drifts down through the darkness. It is a world defined by scarcity and extremes, and yet it is anything but empty. One of the most striking adaptations to life in this realm is the use of bioluminescence. With no sunlight to see by, many organisms have evolved the ability to produce their own light through chemical reactions within their bodies. This light is cold and efficient, generated by molecules called luciferins that react with oxygen in the presence of enzymes known as luciferases. The result is a glow that can range from faint blue to bright green, depending on the species and the function. In the midnight zone, bioluminescence is everywhere. It flashes from the bodies of drifting jellyfish, pulses along the sides of fish, and glows softly from the lures of predatory hunters. It is used to attract prey, to communicate, to find mates, and to confuse or deter predators. It is, in many ways, the language of the deep. Some creatures wield bioluminescence as a weapon. The anglerfish, one of the most iconic inhabitants of the midnight zone, dangles a glowing lure from a modified fin ray that protrudes from its forehead. In the darkness, the light draws in curious prey, which the anglerfish swallows whole with its enormous mouth and inward curving teeth. Other predators use light as a trap, flashing patterns that mimic the movements of smaller creatures to lure in unsuspecting victims. Some squid release glowing clouds into the water, creating a dazzling distraction that allows them to escape. Even prey species use bioluminescence defensively, emitting sudden bursts of light to startle attackers or to signal that they have been spotted. Camouflage in this lightless world takes on forms that are counterintuitive to surface dwellers. Transparency is one common strategy, with many gelatinous creatures nearly invisible against the black water. Others are covered in reflective scales that scatter whatever faint light exists, erasing their outlines. Some species, paradoxically, use bioluminescence for camouflage, by producing light on their undersides that matches the faint glow filtering down from above, often from distant stars and the moon, dimly visible even at great depths. They erase their silhouettes and become invisible to predators looking up from below. This technique, known as counter-illumination, is a masterpiece of evolutionary engineering, a solution to a problem that exists only in the deep. The scarcity of food in the midnight zone has driven some of the most remarkable adaptations in the animal kingdom. Many deep-sea fish have enormous mouths and distensible stomachs, allowing them to swallow prey almost as large as themselves. The gulper eel, for example, has a mouth that can open wide enough to engulf animals far bigger than its slender body would suggest. Others have developed elongated, needle-like teeth that ensure anything they catch cannot escape. Some species, like the black swallower, can consume prey several times their own mass, stretching their stomachs to extraordinary sizes. These adaptations are not luxuries. They are necessities in a world where meals may be separated by weeks or months, and every opportunity to feed must be seized. Predation here is often a patient game. Many deep-sea hunters remain motionless for long periods, conserving energy until prey comes within reach. Movement itself is costly in an environment where energy is scarce, so efficiency is paramount. Muscles are often reduced, bodies soft and gelatinous, skeletons lightly built. Speed is less important than endurance. In some cases, organisms have traded mobility entirely for a sedentary existence, waiting for food to come to them rather than seeking it out. This is true not only of sessile animals attached to the seafloor, but also of some free-swimming predators, which rely on stealth and stillness as much as speed and strength. Reproduction in the midnight zone presents its own set of challenges. With populations spread thinly across vast distances and individuals rarely encountering one another, many species have evolved unusual strategies to ensure their genes are passed on. The anglerfish, again, is a prime example. In many species, males are tiny compared to females and spend much of their lives searching for a mate. When they find one, they bite onto her body and fuse with her bloodstream, becoming a permanent appendage that provides sperm whenever needed. It is a bizarre solution, but an effective one in an environment where chance encounters are rare. Other species release vast numbers of eggs and sperm into the water, relying on probability to bring them together. Some synchronize their reproductive cycles to environmental cues, such as changes in temperature or the availability of food, to increase the likelihood of success. Despite its isolation and hostility, the Midnight Zone is not disconnected from the rest of the planet. It plays a crucial role in global processes, from the cycling of nutrients to the storage of carbon. As organic material sinks from the surface, much of it is consumed and transformed here, fueling the deep-sea food web and influencing the chemistry of the water. The respiration of deep-sea organisms helps regulate oxygen levels and carbon dioxide concentrations, affecting the balance of gases throughout the ocean. The slow, steady currents that flow through the Midnight Zone connect distant regions, transporting heat, salt, and nutrients across the globe. It is a hidden engine of planetary stability, operating quietly beneath the waves. The creatures of the Midnight Realm are not only adapted to their environment, they shape it. Scavengers play a vital role in breaking down organic matter, recycling nutrients back into the ecosystem. Predators control populations and influence the structure of the food web. Even microbes, invisible to the naked eye, are essential players, decomposing detritus and driving chemical cycles that sustain life. Every organism, no matter how small, is part of a larger system, a web of interactions that sustains the deep ocean and, by extension, the planet itself. Our understanding of this realm is still in its infancy. Because of the immense pressure and darkness, exploration is difficult and expensive. Most of what we know comes from remotely operated vehicles, autonomous submersibles, and occasional manned expeditions. Even so, each journey into the Midnight Zone reveals new species, new behaviours, and new insights. Some discoveries challenge our assumptions about biology. Others hint at processes we do not yet fully understand. We have found fish with transparent heads that gaze upward through domes of clear tissue, crustaceans with bioluminescent organs that pulse in complex patterns, and gelatinous predators that trap prey in sticky webs of mucus. We have discovered microbial communities thriving on sunken wood, decomposing bones, and even plastic debris. Every dive adds another piece to the puzzle, but the picture remains far from complete. The deep ocean is also a place of extraordinary geological features, even in the absence of sunlight. Seamounts, underwater mountains formed by volcanic activity, rise thousands of meters from the sea floor, creating islands of biodiversity in the darkness. Deep canyons carve through the seabed, channeling currents and concentrating nutrients. Vast plains stretch for thousands of kilometers, their surfaces covered with fine sediments that record millions of years of Earth's history. And in some places, hydrothermal vents and cold seeps punctuate the seafloor, releasing chemical-rich fluids that sustain entire ecosystems independent of the surface. These geological features are not just passive backdrops. They shape the distribution of life, influence ocean circulation, and even affect global climate. For all its alien qualities, the Midnight Zone is deeply connected to life on the surface. The carbon that sinks from the sunlit waters above is sequestered here, helping to regulate the planet's climate. The nutrients recycled by deep-sea organisms eventually return to the upper layers, fueling the growth of plankton and supporting fisheries. Even the oxygen we breathe is influenced by processes that occur in the deep ocean. It is easy to think of this realm as remote and irrelevant to our daily lives, but in reality, it is an integral part of the Earth system, one that sustains the world we know in ways we're only beginning to understand. Humans are increasingly interacting with this hidden world, sometimes in ways that could have lasting consequences. Deep-sea mining, driven by demand for minerals like cobalt and manganese, threatens to disrupt fragile ecosystems that have taken millennia to develop. Bottom trawling, a destructive fishing practice that drags heavy nets across the seafloor, can devastate habitats and reduce biodiversity. Even climate change reaches into the Midnight Zone, altering temperatures, oxygen levels, and the distribution of species. Microplastics and chemical pollutants have been found in organisms living thousands of meters below the surface, a stark reminder that no part of the planet is truly isolated from human activity. These impacts are concerning not only because they threaten biodiversity, but also because they could disrupt the deep ocean's role in regulating the planet. If carbon cycling is altered, it could affect atmospheric carbon dioxide levels and accelerate climate change. If nutrient pathways are disrupted, it could affect productivity at the surface. If habitats are destroyed, it could lead to the loss of species that we have barely begun to study, species that may hold clues to new medicines, new technologies, or even new insights into life itself. Protecting the Midnight Zone is not just about preserving its beauty and mystery. It is about safeguarding the processes that sustain life on Earth. Our exploration of this realm is still in its early stages, but it is already reshaping how we think about life and its possibilities. We now know that life does not need sunlight to thrive. It does not need warmth or abundant food or gentle pressure. It can flourish in darkness, cold, and crushing weight. It can build complex ecosystems around chemical energy and survive in conditions that seem utterly inhospitable. This realization has profound implications for the search for life beyond Earth. If life can thrive here, it might also exist beneath the icy crusts of distant moons, or in the dark oceans of exoplanets orbiting far from their stars. The Midnight Zone is not just a frontier of Earth science, it is a window into the universe. Yet even as we learn more, the Midnight Zone retains its secrets. Vast areas remain unexplored, and countless species remain undiscovered. The scale of the unknown here is almost overwhelming. We have mapped the surface of Mars in greater detail than the seafloor of our own planet. We have sent probes beyond the solar system, yet we know almost nothing about what lives in the darkness beneath our oceans. Each expedition, each new discovery, is a reminder of how much more there is to learn, and how much we stand to gain by learning it. The Midnight Realm challenges us to rethink our assumptions about what is necessary for life. It forces us to confront the limits of our knowledge and to recognize that those limits are far broader than we once believed. It shows us that life is not fragile but resilient, not confined but expansive. It thrives in places we once thought impossible, adapts to conditions we cannot easily imagine, and continues to surprise us with its ingenuity. And as we push deeper into this universe without a sun, we begin to see that the story of life on Earth is far larger, far stranger, and far more intricate than we ever dared to dream. The journey downward does not end here. Even deeper realms await, where pressure rises still further, where the seafloor shapes life in unexpected ways, and where energy flows not from above but from the very heart of the planet. The Midnight Zone is a gateway to these deeper mysteries, a place where light has no meaning and darkness is not a void but a habitat. It is a world unto itself, vast and vital, hidden and essential, and it is only the beginning of what the deep ocean has to teach us. In the darkness of the deep ocean, where sunlight cannot reach and night is eternal, light still exists. It flickers softly from the bodies of drifting creatures, pulses in brief flashes from predators and prey, and glows steadily from colonies of tiny organisms suspended in the water. It appears in patterns and bursts, in faint glimmers and dazzling displays, sometimes subtle, sometimes spectacular. This light is not borrowed from the sun. It is born within the living bodies of the creatures themselves. It is bioluminescence, and it is one of the most remarkable adaptations in all of nature. Bioluminescence is the production and emission of light by living organisms. It is a form of chemiluminescence, light created by chemical reactions, that has evolved independently many times across the tree of life. Fireflies use it on summer nights, fungi glow faintly on rotting logs, and some terrestrial bacteria emit light as they break down organic matter. But nowhere is bioluminescence more common, more diverse, or more important than in the ocean. In fact, it is estimated that more than 3/4 of deep-sea organisms can produce light in some form. It is not a rare trick, but a fundamental part of life in the darkness below. At its core, bioluminescence is a simple process. A light-emitting molecule called luciferin reacts with oxygen in the presence of an enzyme known as luciferase. The reaction releases energy in the form of light. The details of this chemistry vary widely among species. There are many different luciferins and luciferases, each with slightly different properties, but the principle is the same. It is an elegant solution to the problem of living in darkness. If no light is available, make your own. The uses of bioluminescence are as varied as the creatures that wield it. For some, it is a tool for finding food. For others, it is a weapon or a shield. For many, it is a means of communication. It is a language written in flashes and glows, in rhythms and patterns, understood instinctively by those who live in the dark. In the deep ocean, where vision is often the only reliable sense over distance, light becomes the medium through which life interacts with life. One of the most familiar uses of bioluminescence is predation. The anglerfish, for example, wields its light as a lure. A modified dorsal spine extends from its head like a fishing rod, tipped with a glowing bulb produced by symbiotic bacteria. The light draws in small fish and invertebrates, curious about the glow in the darkness. When they come close, the anglerfish strikes with a speed and precision that belies its sluggish appearance. Other predators use light more subtly. Some flash bioluminescent signals that mimic the appearance of prey, drawing victims into range. Some deep-sea squid have glowing patches on their arms, which they wave in hypnotic patterns to attract smaller animals. In an environment where food is scarce and opportunities are rare, the ability to deceive with light can mean the difference between starvation and survival. Prey species, too, use bioluminescence to their advantage. Some release sudden bursts of light when threatened, startling predators and giving themselves a chance to escape. Others eject glowing mucus or ink into the water, creating a luminous cloud that confuses attackers. A few even sacrifice part of their own bodies, a glowing appendage or bioluminescent tissue, which continues to shine as a distraction while the rest of the animal slips away into the darkness. These strategies are remarkably effective. In a world where vision is limited, a sudden flash of light can be as disruptive as a loud noise, momentarily blinding or disorienting an attacker. One of the most ingenious uses of bioluminescence is camouflage. At first glance, it seems counterintuitive. How could producing light help an organism remain unseen? But in the deep ocean, where the only light comes from above and is faint and diffuse, animals looking up from below often search for the silhouettes of prey outlined against the dim glow. By producing light on their undersides that matches the brightness and colour of the faint light above, some creatures erase their outlines entirely. This technique, known as counter-illumination, is used by many deep-sea fish and squid. Specialised organs called photophores are distributed across their bellies, each capable of adjusting its brightness in response to changing light levels. The result is near-perfect invisibility from below, an adaptation so effective that it has evolved independently in multiple lineages. Bioluminescence also plays a crucial role in communication. Many deep-sea animals live solitary lives, spread thinly across vast distances. Finding a mate in this immense dark space can be extraordinarily difficult. Light offers a solution. Some species produce species-specific patterns of flashes, allowing individuals to recognize and locate one another. Others glow steadily during mating seasons, attracting partners in the gloom. In some cases, males and females of the same species produce different light signals, ensuring that they can find and identify each other, even when separated by hundreds of meters of dark water. These visual signals are often more reliable than chemical cues or sounds, which can disperse or distort over distance. The complexity of these signals can be astonishing. Some species of ostracods, tiny crustaceans, perform elaborate courtship displays using light. Males swim in intricate patterns, releasing pulses of bioluminescence from specialized glands. The resulting trails of light spiral and weave through the water, advertising their presence and fitness to females. These displays are not random but carefully choreographed, with timing and pattern playing crucial roles in their success. Even in the deep sea, where energy is scarce and every expenditure must be justified, life invests in beauty and communication. Not all bioluminescence is under the direct control of the animals that display it. Many deep-sea creatures rely on symbiotic relationships with bacteria that produce light on their behalf. These bacteria, often housed in specialized light organs, receive nutrients and protection from their hosts. In return, they provide a steady glow. Some fish can regulate the intensity of this light by controlling the flow of oxygen to the bacteria, while others use shutters of skin or pigment to block or reveal the glow as needed. These partnerships are ancient and widespread, a testament to the evolutionary advantages of shared light. The physical properties of bioluminescent light are shaped by the ocean environment. Most marine bioluminescence is blue or green, wavelengths that travel farthest through water and are most visible to the eyes of deep-sea animals. A few species produce red light, which is quickly absorbed by water and invisible to most predators, giving them a hidden channel of communication. Some deep-sea dragonfish, for example, use red bioluminescence to illuminate prey that cannot see it coming, a form of biological night vision. This adaptation gives them a significant hunting advantage in a world where stealth is often the key to survival. The ecological significance of bioluminescence extends far beyond individual interactions. It shapes the structure of food webs, influences predator-prey dynamics, and affects the behavior of entire communities. Vertical migrators, for instance, often time their movements to minimize their exposure to predators that hunt by detecting bioluminescent signals. Some predators specialize in targeting glowing prey, while others avoid them, perhaps because light is often associated with chemical defenses or unpalatability. The presence or absence of light can determine where animals feed, how they move, and when they reproduce. Bioluminescence even plays a role in global processes. Massive blooms of bioluminescent plankton can influence the behavior of larger animals, attracting fish and whales that, in turn, shape nutrient cycling and carbon transport. The light produced by microbial communities on sinking particles can affect how quickly those particles are consumed, altering the efficiency of the biological pump that drives carbon from the surface to the depths. Even the faint glow of bacteria on decomposing matter can influence the activity of scavengers and decomposers, subtly shaping the flow of energy through the deep-sea ecosystem. Studying bioluminescence is challenging. Many organisms lose their ability to produce light when brought to the surface, and the pressure and temperature differences between their native environment and our laboratories can alter their physiology. Capturing bioluminescent events on video is difficult, requiring sensitive cameras and careful lighting that does not overwhelm the faint natural glow. Even identifying the chemical pathways involved can be complex, as many species use unique luciferins and luciferases that have yet to be fully characterized. Yet each discovery deepens our understanding of this phenomenon and its role in the ocean. The applications of bioluminescence extend beyond marine biology. Luciferase enzymes are now widely used as markers in molecular and medical research, allowing scientists to track gene expression, monitor disease progression, and study cellular processes in real time. Bioluminescent proteins are used in imaging technologies and diagnostic tools. Even the principles of counter-illumination have inspired military camouflage and stealth technologies. What began as an adaptation to life in darkness has become a tool with far-reaching implications for science, technology, and medicine. Bioluminescence also challenges our understanding of communication and sensory perception. On land, we think of vision as something dependent on external light. In the deep ocean, light becomes an active part of behavior, a signal deliberately generated and shaped by the organisms themselves. It is both a message and a medium, both a product of biology and a driver of evolution. It reminds us that communication is not limited to sound or scent or touch. It can be built from photons, even in a place where photons are scarce. The diversity of bioluminescent life continues to surprise us. Each expedition into the deep reveals new species with new ways of using light. Some jellyfish produce flashes that ripple across their bodies in waves. Some worms emit clouds of glowing particles when disturbed. Some fish can modulate the colour and intensity of their light in ways we do not yet fully understand. There are even organisms that seem to use bioluminescence as a form of mimicry, imitating the flashes of other species to deceive them. The possibilities appear endless, and our current knowledge is likely only a small fraction of what exists. Despite its prevalence, bioluminescence remains one of the least understood biological phenomena. Many of the chemical pathways involved are unknown. The evolutionary origins of luciferins and luciferuses are still debated. The reasons why certain lineages evolved bioluminescence while others did not are not fully clear. And the ecological consequences of these adaptations are only beginning to be mapped. Each new discovery opens more questions than it answers, hinting at a depth of complexity we're only starting to grasp. Bioluminescence also connects the deep ocean to the broader history of life on Earth. Some scientists believe that the earliest organisms on the planet may have produced light, perhaps as a byproduct of metabolic processes in the oxygen-poor conditions of the early Earth. If so, bioluminescence may be among the most ancient biological traits, predating complex multicellular life. Its persistence across so many lineages and environments suggests that it offers fundamental advantages, not just in the deep sea, but wherever life faces darkness. The presence of bioluminescence also informs the search for life beyond Earth. If organisms on our planet can use chemical reactions to produce light in the absence of a sun, perhaps life elsewhere could do the same. Astronomers and astrobiologists are now considering how bioluminescent signatures might be detected on distant worlds or in the subsurface oceans of icy moons. A faint glow in the darkness, once considered a curiosity of marine biology, may one day be a signpost of life on another planet. As our technology improves and we peer deeper into the midnight realm, the spectacle of bioluminescence comes into sharper focus. It is not random or incidental. It is purposeful, shaped by millions of years of evolution to meet the demands of an environment without sunlight. It is a tool for survival, a strategy for success, and a symbol of life's ingenuity. It shows us that darkness is not a barrier, but an opportunity, a space where new forms of communication, predation, and cooperation can evolve. The glow of the deep ocean is more than just a biological trick. It is a reminder that life will always find ways to adapt, to exploit the conditions it faces, and to turn challenges into advantages. Where there is no sunlight, organisms make their own light. Where vision seems impossible, they invent new ways to see and be seen. Where isolation and emptiness seem inevitable, they create signals that connect them across the void. And as we continue deeper, past the regions where bioluminescence is a tool and into places where it becomes an entire foundation of life, we will see even more evidence of this adaptability. The deep ocean is not merely a dark and hostile place. It is a canvas where evolution paints with light, where living things transform the absence of sunlight into something rich and dynamic. And with every pulse and flicker, with every glow and flash, they reveal that even in the most profound darkness, life refuses to remain unseen. The deeper you travel into the ocean, the more it feels as if you've left Earth entirely. The familiar shapes and strategies of life on the surface begin to dissolve, replaced by forms so strange and unexpected that they seem to belong to another planet. Eyes stretch into enormous orbs or disappear altogether. Mouths become vast, unhinging traps capable of swallowing prey half the animal's size. Bodies lose their symmetry, their colour, their rigidity. In the abyss, evolution takes on new directions, freed from many of the constraints that shape life in the sunlit world. Here, adaptation is not about thriving in abundance, but about enduring in scarcity. It is not about speed, but efficiency, not about dominance, but persistence. It is about finding a way to exist in a realm defined by extremes of pressure, temperature, darkness, and isolation. At first glance, the inhabitants of the deep can seem monstrous. Their bodies often defy the expectations we have from the surface world, where sunlight, buoyancy, and competition shape organisms into familiar patterns. But each feature, no matter how bizarre it appears, is the product of millions of years of natural selection, honed precisely for the conditions of the deep. In a place where food is rare and unpredictable, size, shape, and behaviour all bend toward survival. One of the most noticeable features of many deep-sea animals is their soft, gelatinous bodies. The immense pressure in the abyss makes rigid structures risky. They can crack, collapse, or require costly energy to maintain. By contrast, soft tissues compress easily, distributing pressure evenly and reducing the risk of structural failure. Many creatures here have skeletons made of cartilage rather than bone, or they have lost rigid support structures altogether. Their bodies are often flabby, almost shapeless, allowing them to withstand pressure that would crush most surface-dwelling organisms. This softness also conserves energy. Building dense muscle and bone requires significant resources, and in a place where food is scarce, every bit of energy saved can mean the difference between life and death. Many deep-sea species are also remarkably slow. Movement in the abyss is costly. Water is dense, pressure is high, and food is rare. Rapid swimming burns precious energy that may not be easily replaced. As a result, many animals move with deliberate, almost ghostly grace. They drift with currents rather than fight them. They ambush rather than chase. They eat infrequently but consume vast meals when the opportunity arises. Even their metabolisms are slower, their body temperatures lower, their lifespans longer. Some deep-sea fish may live for decades or even centuries, their lives unfolding at a pace that would seem glacial on land. This slow, measured rhythm is not a sign of weakness. It is a finely tuned adaptation to a world where patience is often the key to survival. Predation in the abyss takes forms that are as diverse as they are surprising. Some hunters, like the gulper eel, have evolved enormous mouths and highly elastic stomachs, allowing them to swallow prey far larger than themselves. Others, like the viper fish, wield needle-like teeth and lightning-fast strikes, seizing prey before it can react. Some rely on stealth and patience, lying motionless in the water for hours or days, conserving energy until a meal drifts within reach. Still others have evolved lures, traps, or deceptive signals to draw prey closer. In the darkness of the deep, where visibility is limited and encounters are rare, deception and patience often matter more than speed or strength. Many deep-sea predators are opportunistic, feeding on whatever they can find. Scavenging is common, and few meals are turned down. Whale falls, the carcasses of whales that sink to the seafloor, are particularly important sources of food, creating sudden explosions of life in the deep. Scavengers converge from miles around, stripping the flesh within weeks. Bacteria break down the remaining tissues, releasing nutrients that sustain entire communities. Even the bones become habitats, colonized by specialized worms and other organisms. A single whale fall can support a complex ecosystem for decades, a reminder of how even death can sustain life in the abyss. Reproduction in the deep presents its own unique challenges, and evolution has responded with an astonishing array of solutions. In the vast emptiness of the deep ocean, encounters between individuals of the same species can be rare and unpredictable. Some species solve this problem by releasing vast numbers of eggs and sperm into the water, relying on chance to bring them together. Others form aggregations at specific times or places, increasing the likelihood of reproduction. Some deep-sea organisms are hermaphroditic, possessing both male and female reproductive organs, which ensures that any encounter with another individual can result in offspring. And then there are strategies like that of the anglerfish, where tiny males permanently fuse with much larger females, becoming little more than appendages that provide sperm on demand. These solutions may seem extreme, but they are precisely what is required in an environment where opportunities are scarce. Sensory adaptations in the deep are equally striking. Vision, for example, changes dramatically with depth. In the absence of sunlight, many deep-sea creatures have evolved enormous eyes that capture the faintest glimmers of bioluminescent light. Some can detect wavelengths invisible to most animals, allowing them to spot prey or mates that others cannot see. Others have gone in the opposite direction, losing their eyes entirely and relying on other senses instead. Some fish and invertebrates use pressure-sensitive lateral lines to detect the movements of nearby animals. Others sense electrical fields, chemical gradients, or vibrations in the water. In a place where light is a rarity, evolution finds other ways to perceive the world. Coloration in the deep is another area where expectations from the surface no longer apply. Bright colours, so common in shallow waters, are virtually absent here. Many deep-sea creatures are black or dark red, colours that render them nearly invisible in the darkness. Red light is absorbed quickly by water, so red animals appear black in the deep, an effective form of camouflage. Others are transparent, their bodies so clear that they are nearly impossible to see. Some species use reflective surfaces or mirrored scales to scatter light and erase their outlines. And then there are those that use light itself for concealment, producing bioluminescent glows on their undersides to match the faint light filtering down from above. This counter-illumination makes them invisible from below, a remarkable example of evolutionary problem-solving. Symbiotic relationships are another common theme in the abyss, often taking forms not seen elsewhere. Many deep-sea animals rely on symbiotic bacteria to provide them with nutrients. Tube worms near hydrothermal vents, for example, have no mouths or digestive systems. Instead, they house bacteria within their bodies that convert hydrogen sulfide into organic matter through chemosynthesis. In return, the worms provide the bacteria with a stable environment and access to chemicals. This partnership allows both organisms to thrive in an environment where traditional food sources are scarce. Other animals host bioluminescent bacteria in specialized light organs, using the glow for communication, camouflage, or hunting. These relationships are not incidental. They are fundamental to survival in the deep. Evolution in the abyss also produces unusual life histories and developmental strategies. Some species have larvae that live in shallow waters before descending into the deep as adults, a strategy that takes advantage of the relative abundance of food near the surface during early development. Others spend their entire lives in the deep, their life cycles timed to the slow rhythms of the abyss. Growth is often slow, reproduction infrequent, and longevity extended. Many deep-sea species live far longer than their shallow water relatives, a reflection of both the stable environment and the scarcity of resources. Life here is not rushed. It unfolds over decades, sometimes centuries, shaped by forces that move at a different pace than those on the surface. The result of all these pressures is a biodiversity that is as rich as it is strange. The deep ocean is home to an astonishing variety of life, much of it unlike anything found elsewhere. There are fish with transparent heads, jellyfish that look like drifting bells of glass, and crustaceans with limbs adapted to filter the tiniest particles from the water. There are worms that build mineral tubes around hydrothermal vents, bacteria that metabolize methane and hydrogen sulfide, and gelatinous predators that ensnare prey in webs of mucus. There are giant isopods the size of dinner plates, and microscopic plankton that glow like stars. The variety of shapes, sizes, and strategies is almost endless, a reflection of evolution's creativity when freed from familiar constraints. This creativity extends even to the basic architecture of life. Many deep-sea organisms have body plans that are radically different from those of their shallow water relatives. Some fish have elongated bodies and reduced fins, adaptations that minimize energy expenditure. Others have enormous jaws and distensible stomachs, allowing them to capitalize on rare feeding opportunities. Some invertebrates form colonies that function as single organisms, with specialized individuals performing different roles. Even the basic structure of cells can differ, with membranes and proteins adapted to function under high pressure and low temperature. Evolution in the abyss is not just about tweaking existing designs, it is about inventing new ones. The deep ocean is also a place where ancient lineages endure. Many deep-sea species are living fossils, their forms little change for tens of millions of years. The coelacanth, a lobe-finned fish once thought to be extinct, was rediscovered in deep waters off the coast of Africa in 1938. Its lineage dates back more than 400 million years. Other deep-sea creatures, such as certain species of stalked crinoids and glass sponges, also represent ancient lineages that have persisted in the stable conditions of the deep. These organisms are not relics of a bygone era, but active participants in modern ecosystems. Their continued existence is a testament to the stability and continuity of the deep-sea environment, where evolutionary pressures differ from those on land or in shallow water. Evolution in the abyss is not just about adaptation to the present, it is also about potential for the future. The unique traits that deep-sea organisms possess, from pressure-resistant proteins to efficient metabolic pathways, hold immense promise for science and technology. Enzymes from barophilic microbes, for example, are used in industrial processes that require high pressure. Bioluminescent proteins are essential tools in medical imaging and molecular biology. Compounds produced by deep-sea organisms are being investigated as potential sources of new antibiotics and anti-cancer drugs. Even the structural materials produced by some deep-sea sponges and corals are inspiring new materials for engineering and construction. The deep ocean is not just a repository of biodiversity. It is a library of evolutionary solutions, many of which we are only beginning to understand. The evolutionary experiments of the abyss also challenge our assumptions about the limits of life. They show that organisms can thrive without sunlight, at temperatures near freezing, under pressures that would crush most life, and in conditions of extreme scarcity. They show that life can find ways to exploit chemical energy, to form partnerships with microbes, to build ecosystems around sources of energy we once thought irrelevant. They show that evolution is not a linear process, but a branching, improvisational one, capable of producing solutions we could never predict. And they remind us that the diversity of life on Earth is far greater than what we see on land or in shallow seas. Most of that diversity is hidden, living in darkness, far beneath the waves. Studying these evolutionary adaptations is not easy. The pressure, darkness, and remoteness of the deep ocean make exploration challenging and expensive. Many deep-sea species cannot survive the journey to the surface, their bodies collapsing or rupturing when removed from their high-pressure environment. Even observing them in their natural habitat requires sophisticated equipment, remotely operated vehicles, autonomous submersibles, and pressure-resistant cameras. Despite these challenges, each expedition reveals new insights. We discover species we never knew existed, behaviors we never imagined, and adaptations that expand our understanding of what life can do. The deep ocean is not static. It is a dynamic environment, and evolution continues to shape its inhabitants. Climate change, pollution, and human activity are altering the conditions of the deep, and organisms are responding. Some are shifting their ranges in search of suitable habitats. Others are adapting to new chemical conditions as carbon dioxide levels rise and ocean acidity increases. Still others may be evolving new strategies to cope with changes in food availability and temperature. evolution in the abyss is not a relic of the past. It is an ongoing process, unfolding right now, hidden beneath the waves. What we see in the deep ocean is evolution unbound, life freed from the familiar constraints of light, warmth, and abundance. It is life sculpted by pressure, shaped by darkness, and honed by scarcity. It is life that looks nothing like the world we know, yet is intimately connected to it. It is a reminder that the story of evolution is not just one of survival, but of invention. And nowhere is that invention more apparent than in the abyss, where strange shapes and stranger lives tell a story that has been unfolding for millions of years and shows no sign of ending. The journey downward continues. The creatures we encounter next will live in places where geology and biology intertwine, where energy seeps from the Earth's crust rather than falling from the sky, where ecosystems form around vents and seeps instead of sunlight. The shapes may grow stranger still, and the lives more improbable, but each will carry the unmistakable signature of evolution's creativity, a testament to life's ability to adapt, endure, and flourish in even the most improbable corners of our planet. All life on the surface of our planet, at least at first glance, seems to depend on the sun. Plants harvest its light to build sugars, animals eat those plants or eat the animals that eat them, and entire ecosystems rise and fall in sync with the turning of day into night. The sun drives weather, shapes seasons, and powers the chemical reactions that sustain life as we know it. But deep beneath the ocean, far beyond the reach of light, none of this applies. Here, sunlight is irrelevant. It cannot penetrate, cannot warm, cannot fuel the machinery of photosynthesis. Yet life persists, not just clinging to existence, but thriving in numbers, complexity, and diversity that rival the surface world. It does so by mastering an art that seems almost paradoxical, the art of surviving without the sun. The fundamental challenge of life in the deep ocean is energy. Every living thing needs it, whether to grow, reproduce, repair damage, or simply stay alive. On the surface, that energy begins with sunlight, captured by plants and algae and transformed into chemical energy through photosynthesis. In the deep ocean, however, no such source exists. Sunlight fades completely within the first 1,000 meters, leaving the vast majority of the ocean in perpetual darkness. Here, life must rely on other means to obtain the energy it needs, and it has evolved a remarkable array of strategies to do so. One of the most basic and widespread strategies is to use the slow, steady rain of organic material from above. Tiny particles of dead plankton, fecal matter, and other detritus drift down from the sunlit surface, forming what scientists call a marine snow. It is not a blizzard but a continuous drizzle, a constant supply of nutrients falling through the water column. Many deep-sea organisms feed directly on this material, filtering it from the water or scavenging it from the seafloor. Others feed on the animals that feed on marine snow, creating complex food webs built on the remnants of life from above. Even the tiniest particles are valuable in a place where food is scarce. Microbes break them down further, recycling nutrients and releasing energy that supports entire communities. Larger packages of energy occasionally fall from above in the form of carcasses, fish, squid, or even whales that die and sink to the seafloor. These rare but significant events are known as food falls, and they can transform the deep-sea landscape. A whale fall, for instance, can support a succession of communities over decades. Scavengers arrive first, stripping the soft tissue in a matter of weeks. Then, bacteria and worms break down the remaining fat and cartilage, releasing nutrients into the water. Finally, specialized organisms like bone-eating worms colonize the skeleton itself, extracting lipids trapped within. Each stage provides energy to a different set of organisms, creating a miniature ecosystem in the middle of the abyss. For many deep-sea species, these rare windfalls are crucial to survival, and their life cycles may even be timed to take advantage of them. But not all energy in the deep ocean arrives from above. Some of the most remarkable adaptations are found in ecosystems that are entirely independent of the surface world, drawing their energy not from the sun but from the Earth itself. The most dramatic examples of this are hydrothermal vent communities, discovered only in the late 1970s. These vents form along mid-ocean ridges, where tectonic plates are pulling apart and magma rises close to the seafloor. Seawater seeps into cracks in the crust, heats up as it encounters hot rock, and is expelled back into the ocean laden with minerals and chemicals. The water that emerges from these vents can reach temperatures of over 400 degrees Celsius, yet it does not boil because of the immense pressure at these depths. It is toxic, acidic, and filled with metals and compounds that would be lethal to most surface life. And yet, around these vents, life flourishes. The key to these ecosystems is chemosynthesis, the process by which certain bacteria and archaea convert inorganic chemicals into energy. Instead of using sunlight to power photosynthesis, they use the energy released by chemical reactions involving substances like hydrogen sulfide, methane, or hydrogen. The most common reaction around hydrothermal vents involves hydrogen sulfide, which is abundant in vent fluids. Chemosynthetic microbes oxidize hydrogen sulfide, combining it with oxygen from seawater to produce energy. They use this energy to fix carbon dioxide into organic matter, just as plants do during photosynthesis. In this way, they form the base of an entire food web, supporting a diverse array of organisms from worms and clams to crabs and fish. The sheer abundance of life around hydrothermal vents is astonishing, especially when compared to the surrounding seafloor, which can be almost barren. Giant tube worms grow over 2 meters long, their bright red plumes waving in the vent currents. They have no mouths, no stomachs, and no digestive systems. Instead, they house chemosynthetic bacteria inside a specialized organ called a trophosome. The bacteria provide them with nutrients, and the worms supply the bacteria with the chemicals they need to thrive. It is a partnership so intimate that neither partner could survive without the other. Clams and mussels, too, host symbiotic bacteria within their tissues, drawing nourishment from their chemical reactions. Crabs and shrimp graze on bacterial mats or prey on other vent dwellers, forming higher levels of the food web. Entire communities form around these oases of chemical energy, existing in complete independence from the sunlit world above. Cold seeps, places where hydrocarbons like methane and hydrogen sulfide seep slowly out of the seafloor, support similar ecosystems, though their flows are gentler and their temperatures lower. Like hydrothermal vents, cold seeps are powered by chemosynthesis, with microbes oxidizing methane or sulfide to generate energy. Mussels and clams cluster around these seeps, sustained by their bacterial partners. Tube worm grow in dense colonies, some living for centuries. Bacterial mats spread across the sediment, providing food for grazing snails and crustaceans. These ecosystems are more stable and longer-lived than vent communities, which can be disrupted by volcanic activity, but they are no less remarkable. They represent another way that life has learned to harness the energy locked within the Earth itself. The chemistry that powers these ecosystems is complex, but the principle is simple. Where there is a source of energy, whether in the form of sunlight, organic matter, or chemical reactions, life will find a way to use it. The deep ocean demonstrates this principle in dramatic fashion. It shows that energy does not have to come from above. It can come from below, from the interaction of water and rock, from the slow seep of methane, from the decay of organic matter, or from the oxidation of metals. Life is not limited by the absence of sunlight. It is limited only by the availability of usable energy, and the deep ocean proves that such energy can exist in many forms. Even microbes that live deep within the seafloor, buried beneath layers of sediment, have found ways to survive on minimal energy. Some subsist on the slow breakdown of buried organic matter, while others use the tiny amounts of hydrogen or methane that diffuse through the rock. Their metabolic rates are astonishingly low, with some cells dividing only once every 100 years. Yet they persist, forming a deep biosphere that may contain as much biomass as all the life in the ocean above. These microbes operate at the edge of what is biologically possible, demonstrating that life does not need abundance to endure. It needs only a trickle of energy and the ability to use it efficiently. Energy strategies in the deep ocean are not just about obtaining food, they're also about conserving it. Many deep-sea animals have low metabolic rates, reducing their energy needs. They grow slowly, reproduce infrequently, and live long lives. Some go into states of torpor or dormancy during times of scarcity, slowing their metabolism even further. Others are opportunistic feeders, capable of switching between food sources depending on what is available. Flexibility is a common theme. In an environment where conditions can change quickly and unpredictably, adaptability is often as important as specialization. The scarcity of energy in the deep ocean also shapes the structure of communities and the interactions between species. Competition can be intense, and many organisms have evolved strategies to minimize it. Some occupy narrow ecological niches, feeding on specific types of particles or chemicals. Others form symbiotic relationships that allow them to share resources or exploit them more efficiently. Predation tends to be opportunistic, with animals taking advantage of whatever food sources they encounter rather than specializing narrowly. Scavenging is widespread, and few resources go unused. Even waste products become valuable, recycled again and again through microbial processes. Energy availability also influences the size and distribution of organisms. Deep-sea gigantism, the tendency for some deep-sea species to grow much larger than their shallow water relatives, is often linked to low temperatures and slow metabolisms, both of which reduce energy demands and allow resources to be allocated to growth. At the same time, many deep-sea organisms are small, their tiny bodies requiring less energy to sustain. This coexistence of extremes is another reflection of the deep ocean's unique energy landscape. It is a place where every joule counts, and life explores every possible strategy to capture, conserve, and use it. The ways in which deep-sea life obtains and uses energy have profound implications beyond marine biology. They challenge our understanding of what is necessary for life and expand the range of conditions we consider habitable. They suggest that life could exist in places far removed from sunlight, beneath the icy crusts of moons like Europa and Enceladus, for instance, where hydrothermal activity may provide chemical energy. They also offer insights into how life might have begun on Earth. Many scientists now believe that hydrothermal vents may have been the cradle of life, providing the chemical gradients and energy sources needed for the first metabolic reactions. If so, the deep ocean is not just a frontier of life today, but a window into its origins billions of years ago. The study of deep-sea energy strategies also has practical applications. Chemosynthetic bacteria have potential uses in biotechnology, from bioengineering and wastewater treatment to the development of new drugs. Enzymes from deep-sea organisms, adapted to function under high pressure and low temperature, are valuable in industrial processes. Even the metabolic pathways used by deep-sea microbes to process methane and sulfide could inform new approaches to energy production and carbon capture. The deep ocean is not just a biological treasure trove, it is a source of solutions to some of the most pressing challenges facing humanity. Despite these insights, our understanding of energy in the deep ocean is still limited. Vast regions remain unexplored, and many of the processes that sustain life there are poorly understood. We're only beginning to map the extent of the deep biosphere, to identify the full diversity of chemosynthetic microbes, and to understand how energy flows through these hidden ecosystems. Each new discovery adds depth to our picture, but it also reveals how much we do not yet know. The deep ocean remains one of the last great frontiers of science, and the study of its energy dynamics is still in its infancy. What is already clear, however, is that life's relationship with energy is far more flexible and inventive than we once believed. It is not tied to a single source or a single set of conditions. It can draw energy from sunlight or from the slow decay of organic matter, from the oxidation of chemicals or from the heat of the earth. It can thrive in abundance or persist in scarcity. It can build complex ecosystems around sources of energy that were once thought inhospitable. And it can do all this in complete darkness, under crushing pressure, in the coldest and most remote corners of the planet. The art of surviving without sunlight is, at its heart, the art of adaptation. It is the story of life finding new ways to capture and use energy, of evolution solving problems we never imagined existed, of organisms rewriting the rules of biology to suit the conditions they face. It is a story that continues to unfold, not just in the deep ocean, but wherever life encounters extremes. And as we venture deeper still, into the realms where geology and biology merge, where energy bubbles up from the heart of the Earth itself, that story becomes even more intricate and surprising. The depths below still hold places where energy flows in forms we barely understand, where ecosystems are built on chemical reactions that seem almost alien, and where life continues to challenge our assumptions about what is possible. To follow that story deeper is to follow life itself, not as we know it on the surface, but as it exists when stripped of sunlight, when forced to invent new strategies, when pushed to the edge of what is possible. And as we move onward into those deeper realms, we carry with us the understanding that life is not limited by the absence of light. It is defined by the presence of energy, in whatever form it may come. On the seafloor, thousands of meters below the surface, where light never reaches and pressure crushes everything that is not built to endure it, there are places where the earth itself breathes. They are vents in the crust, fissures and cracks where seawater and molten rock meet, producing a violent reaction that gives rise to towering chimneys of mineral and jets of water so hot they would boil instantly at the surface. Around these vents, in an environment that should be lethal, dark, acidic, and toxic, life gathers in astonishing abundance. These places are the hydrothermal havens of the deep ocean, cities built not on sunlight but on fire and water, and they are among the most extraordinary ecosystems on our planet. Hydrothermal vents form in regions where tectonic plates are pulling apart or colliding, exposing magma close to the seafloor. Seawater seeps into the cracks and fissures in the ocean crust, sinking deep into the earth where it is heated by contact with molten rock. As it heats, the water reacts with the surrounding rocks, leaching out metals and minerals and becoming enriched with chemicals like hydrogen sulfide, methane, and iron. Eventually, this superheated fluid, sometimes exceeding 400 degrees Celsius, rises back to the seafloor and bursts into the cold ocean water. Because of the immense pressure at these depths, the water does not boil, even at temperatures that would vaporize it at the surface. Instead, it emerges as a plume of dark, mineral-rich fluid that quickly cools and precipitates metals, building towering chimneys known as black smokers. At first glance, the environment around these vents seems utterly inhospitable. The water is toxic, laden with hydrogen sulfide and heavy metals. The temperatures vary wildly, from near freezing just a few meters away to hundreds of degrees near the vent openings. The pressure is immense, hundreds of times greater than at the surface, and yet around these vents life thrives in numbers and densities unmatched by almost any other part of the deep sea. It is an oasis in an otherwise sparse landscape, a bustling metropolis of organisms adapted to exploit the energy and resources provided by the Earth itself. The foundation of these ecosystems is microbial life. Chemosynthetic bacteria and archaea use the chemicals in vent fluid, especially hydrogen sulfide, as an energy source. They oxidize these chemicals, combining them with oxygen from seawater to produce energy, which they use to fix carbon dioxide into organic matter. It is a process analogous to photosynthesis, but instead of sunlight, the energy comes from chemical reactions. These microbes form dense mats around vent openings, coating rocks and chimneys with a thin layer of life. They also live inside the bodies of larger organisms, forming symbiotic relationships that are the cornerstone of the vent community. One of the most iconic residents of hydrothermal vents is the giant tube worm. These creatures can grow over 2 meters long and have no mouth, no stomach, and no digestive system. Instead, they rely entirely on symbiotic bacteria housed inside a specialized organ called a trophosome. The worms absorb hydrogen sulfide and oxygen from the surrounding water through their bright red plumes and deliver them to the bacteria, which convert these chemicals into organic molecules that nourish both partners. It is an elegant and efficient partnership, one that allows the tube worms to thrive in an environment where no other source of food exists. Other organisms have developed similar relationships. Clams and mussels host chemosynthetic bacteria within their gills, which provide them with nutrients in exchange for access to vent fluids. Some shrimp species cultivate bacteria on their bodies and graze on them. Crabs and snails feed directly on bacterial mats, while fish and octopuses hunt the animals that gather around the vents. These interconnected feeding relationships form a complex and dynamic food web, one that is sustained entirely by chemical energy from the earth, rather than sunlight from the sky. The sheer density of life around hydrothermal vents is astonishing, especially given the surrounding seafloor's near barrenness. While the deep ocean beyond the vents may host only a handful of animals per square metre, vent communities can teem with thousands. Tube worms cluster in dense colonies that look like living forests, their plumes waving in the current. Mussels form thick carpets that stretch across the vent field. Swarms of shrimp jostle for space on the walls of chimneys, their bodies glowing faintly from the light of bioluminescent bacteria. Predators lurk at the edges, waiting for opportunities to strike. The abundance of life here is not just a curiosity. It is a testament to the power of chemical energy to sustain ecosystems even in the absence of sunlight. These vent ecosystems are not static. They are dynamic and often short-lived on geological timescales. The same tectonic activity that creates hydrothermal vents can also destroy them, sealing fissures, shifting magma, or triggering eruptions that wipe out entire communities. Some vents may remain active for decades or centuries, while others last only a few years. When a vent dies, the organisms that depend on it must move or perish. Many species have evolved strategies to disperse their larvae over long distances, ensuring that they can colonize new vents as they form. The ocean currents become highways for these microscopic travelers, carrying them from one oasis to another in the vast desert of the deep. The origin of hydrothermal vent ecosystems has profound implications for our understanding of life itself. Some scientists believe that life on Earth may have begun in environments like these, where the combination of heat, water, minerals and chemical gradients provided the perfect conditions for the formation of complex organic molecules. The natural flow of chemicals across mineral surfaces could have powered primitive metabolic reactions long before enzymes or cells existed. If this is true, then hydrothermal vents are not just remarkable ecosystems. They're windows into our own origins, living laboratories where the processes that gave rise to life are still at work today. These insights also shape our search for life beyond Earth. Moons like Europa and Enceladus are believed to have liquid oceans beneath their icy crusts, and evidence suggests that hydrothermal activity may be occurring on their sea floors. If life can thrive around hydrothermal vents on Earth, independent of sunlight, it might also exist in these alien oceans, sustained by chemical energy from the interior of distant worlds. The discovery of such life would transform our understanding of biology and our place in the universe. It would show that life is not unique to Earth, that it can arise wherever energy and water coexist, even in the cold darkness far from any star. The study of hydrothermal vent communities has revealed countless surprises about how life adapts to extreme environments. The bacteria that power these ecosystems are masters of biochemistry, capable of oxidizing a range of chemicals and surviving in conditions of high temperature, high pressure, and high toxicity. Some thrive at temperatures above 100 degrees Celsius, temperatures that would destroy most proteins. Others tolerate heavy metal concentrations that would kill almost any other organism. These extremophils are not marginal forms of life. They are robust, diverse, and essential to their ecosystems, and they demonstrate the remarkable flexibility of life's chemistry. Larger animals too display extraordinary adaptations. The tube worm's symbiotic relationship with bacteria is one of the most efficient nutrient-gathering strategies in nature. Mussels and clams can regulate the flow of vent fluids through their tissues, optimizing the supply of chemicals to their bacterial partners. Shrimp that live in the hottest zones near vent openings have specialized heat-resistant proteins and behaviors that allow them to survive where few others can. Even predators have adapted, timing their movements to the periodic surges of vent fluid or exploiting the patterns of bacterial growth that follow changes in vent activity. Every aspect of life around hydrothermal vents is shaped by the unique challenges and opportunities of this environment. The geology of hydrothermal vents is as fascinating as the biology. The chimneys that rise from the seafloor are built from minerals precipitated out of the vent fluid as it cools. Black smokers, which emit dark metal-rich plumes, build chimneys composed primarily of iron and sulfide minerals. White smokers, which emit lighter-coloured fluids rich in silica and barium, build chimneys of different composition. Over time, these structures can grow several meters tall, forming intricate branching towers. They're constantly being built and rebuilt, eroded by the flow of water and rebuilt by new mineral deposits. The result is a landscape that is constantly changing, shaped by the interplay of geology and chemistry. Hydrothermal vent fields are not isolated. They are part of a broader network of geological and biological processes that span the ocean. The chemicals released by vents influence the composition of seawater and contribute to the cycling of elements like sulfur, iron, and manganese. The heat from vent activity affects local currents and mixing patterns. The organisms that live around vents release larvae and organic matter that drift into surrounding waters, connecting these isolated ecosystems to the broader deep-sea environment. Even when a vent dies, its legacy remains in the form of mineral deposits, microbial communities, and dispersing organisms that carry its influence far beyond its immediate surroundings. Humans have only recently begun to explore and understand hydrothermal vent ecosystems, but they have already reshaped our view of life on Earth. Before their discovery, it was widely assumed that all ecosystems ultimately depended on sunlight. The idea that complex, thriving communities could exist in complete darkness, powered solely by chemical energy, was revolutionary. It forced scientists to rethink fundamental assumptions about biology, ecology, and evolution. It showed that life is not bound to the narrow range of conditions found at the surface. It can exist wherever energy is available, even in places that seem utterly inhospitable. Yet these remarkable ecosystems are vulnerable. Deep-sea mining, driven by demand for minerals found in vent deposits, poses a significant threat. The extraction of metals like copper, zinc, and rare earth elements could destroy vent habitats before we have even begun to study them fully. Climate change too may alter the chemistry and circulation patterns of the deep ocean, affecting the formation and activity of hydrothermal systems. Pollution and deep-sea fishing can introduce contaminants or physical disturbances that ripple through these fragile ecosystems. Protecting hydrothermal vent communities is not just about preserving their beauty and diversity. It is about safeguarding the clues they hold to life's origins, their role in global cycles, and their potential as models for life beyond Earth. Exploration continues to reveal new vent systems and new surprises. Each discovery expands our understanding of the diversity and resilience of life. Some vent fields are dominated by species entirely different from those found elsewhere, suggesting that isolation and geological conditions shape evolution in unique ways. Others host organisms that are found nowhere else on Earth, with metabolic pathways and biochemical adaptations that defy current knowledge. Even the microbial communities in vent fluids themselves, invisible to the naked eye, are astonishingly diverse. encompassing species that may hold the keys to understanding the limits of life. The study of hydrothermal vents is still in its infancy. We have mapped only a fraction of the seafloor and many vent systems remain undiscovered. Advances in technology, from deep-diving submersibles to autonomous underwater vehicles, are opening new frontiers, allowing us to explore deeper, longer, and more thoroughly than ever before. Each expedition brings new data, new specimens, and new questions. How do vent communities colonize new sites? How do they evolve over time? What roles do they play in global chemical cycles? What do they tell us about the history of our planet and its future? What is already clear is that hydrothermal vents are far more than geological curiosities. They are vital components of Earth's systems, engines of chemical transformation, and cradles of biological innovation. They demonstrate that life is not dependent on the sun, that ecosystems can be built from chemical energy, and that biology and geology are deeply intertwined. They remind us that the Earth is a dynamic planet, alive not just on its surface but deep within its crust, and that life has evolved to exploit that dynamism in ways that defy expectation. And as we continue deeper into the abyss, the story of life's ingenuity does not end with hydrothermal vents. There are other sources of chemical energy, other ways of surviving without sunlight, and other ecosystems built on the interactions between water and rock. Some are quieter and more subtle, their flows measured in millimeters per year rather than torrents of boiling water. Others lie hidden beneath layers of sediment or within the crust itself. Together they reveal a world far richer and more complex than we once imagined. A world where fire and water combine not to destroy but to sustain life in the darkest corners of our planet. If life on the surface is a story written in sunlight, then life in the deep ocean is written in chemistry. Down here, where the sun's energy cannot reach, organisms have turned to the raw materials of the Earth itself, extracting energy from elements and molecules that seem lifeless and inert. This is the domain of chemoautotrophs, microorganisms that build organic matter from inorganic substances without ever seeing a ray of light. They are the hidden engines of the deep, powering entire ecosystems and proving that life does not need the sun to thrive. They work in silence, unseen but essential, transforming poisonous compounds into food and sustaining some of the most alien communities on our planet. To understand how chemoautotrophs sustain life in the deep ocean, it helps to look closely at what they do. Like plants and algae on the surface, chemoautotrophs fix carbon dioxide into organic molecules that form the basis of food webs. But where plants use sunlight to power this process through photosynthesis, chemoautotrophs rely on chemical reactions, specifically the oxidation of reduced compounds such as hydrogen sulfide, methane, hydrogen, or ferrous iron. These reactions release energy, which the microbes capture and use to convert carbon dioxide into sugars and other organic molecules. In essence, they are performing the same fundamental task as plants, but with a completely different energy source. The environments where chemoautotrophs thrive are often places where geochemistry and biology intersect. Hydrothermal vents are a prime example. As seawater circulates through the ocean crust, it reacts with hot rock and emerges enriched with reduced compounds like hydrogen sulfide. When this fluid mixes with the cold, oxygen-rich seawater, a chemical gradient is created. Chemoautotrophs exploit this gradient, oxidizing the hydrogen sulfide to produce energy. The energy drives the fixation of carbon, and the resulting organic matter becomes the foundation of a food web that supports tube worms, clams, shrimp, and countless other organisms. Without these microbes, the towering vent communities that astonish scientists and explorers would not exist. Cold seeps, places where methane and sulfide ooze slowly from the seafloor, host similar microbial communities. Here, chemoautotrophs oxidize methane and sulfide, sustaining dense populations of mussels, tube worms, and other animals. Some of these microbes live free on the seafloor, forming mats that blanket the sediment. Others live inside the tissues of larger organisms, forming symbiotic partnerships that benefit both partners. The host provides the microbe with access to chemicals and oxygen, while the microbe provides the host with organic matter. These partnerships are so intimate that in some cases the host cannot survive without its microbial symbionts. The diversity of chemoautotrophic life is staggering. Some microbes specialize in oxidizing hydrogen sulfide, combining it with oxygen to produce sulfate and energy. Others oxidize methane, converting it into carbon dioxide while releasing energy. Some use hydrogen as an energy source, while others oxidize reduced metals like iron or manganese. Each of these metabolic pathways exploits a different chemical gradient, and together they allow chemoautotrophs to thrive in a wide range of environments. This diversity is a key reason why life in the deep ocean is so resilient. Even if one source of energy disappears, others remain, and different microbes can fill the gaps. The chemical reactions that power chemoautotrophy are subtle but powerful. Consider the oxidation of hydrogen sulfide, a common energy source around hydrothermal vents. The reaction combines hydrogen sulfide, H2S, with oxygen, O2, to produce sulfate, SO42, and water, releasing energy in the process. This energy is captured by the microbe cellular machinery and used to drive the synthesis of organic molecules from carbon dioxide. The process is efficient and sustainable as long as the supply of hydrogen sulfide and oxygen continues. Similar reactions occur with methane, hydrogen, and other compounds. Each reaction is a small chemical engine, releasing energy that microbes harness to build the molecules of life. The importance of chemoautotrophs extends beyond the immediate ecosystems they support. They play a crucial role in global biogeochemical cycles, influencing the movement of carbon, sulfur, nitrogen, and other elements between the Earth's crust, oceans, and atmosphere. By oxidizing reduced compounds and fixing carbon, they help regulate the composition of seawater and the availability of nutrients. They also contribute to the sequestration of carbon in deep-sea sediments, affecting the global carbon cycle and ultimately the climate. Even microbes buried deep within the seafloor, living far from any hydrothermal vent or cold seep, participate in these processes, slowly metabolizing buried organic matter and altering the chemistry of the sediment. Some chemoautotrophs live not just on the seafloor but within the crust itself. These subsurface microbial communities inhabit pores and fractures in the rock, where they draw energy from the oxidation of hydrogen or iron. The hydrogen they use can be produced by water reacting with minerals in the crust, while iron is released as rocks weather and alter. These reactions occur without any input from the surface, driven entirely by the interaction of water and rock deep within the earth. The microbes that exploit them form part of what scientists call the deep biosphere, a vast hidden reservoir of life that extends kilometers below the seafloor and may contain more biomass than the entire ocean above. These organisms live at the edge of biological possibility, with metabolic rates so slow that a single cell might divide only once every century. Yet they persist, quietly shaping the chemistry of the planet on geological timescales. Chemoautotrophic microbes also form the basis for some of the most remarkable symbiotic relationships in nature. The giant tube worms that dominate hydrothermal vent communities are perhaps the best-known example. Lacking mouths and digestive systems, they rely entirely on symbiotic bacteria housed within their bodies. The worms absorb hydrogen sulfide and oxygen from the surrounding water and deliver them to the bacteria, which oxidize the sulfide and use the energy to produce organic matter. The bacteria then transfer some of this organic matter to the worm, providing it with nutrition. This partnership is so effective that tube worms can grow rapidly in an environment where food from the surface is virtually non-existent. Other organisms have developed similar relationships. Bathymodiolus mussels, for example, host methane-oxidizing bacteria within their gills. These bacteria convert methane into carbon dioxide and organic matter, which the mussels use as a food source. Some species even host multiple types of symbiotic bacteria allowing them to exploit different energy sources simultaneously. These partnerships allow animals to thrive in environments where food is scarce and patchy, and they highlight the central role of chemoautotrophs in sustaining deep-sea life. The versatility of chemoautotrophs is a key factor in their success. Many species are capable of switching between energy sources depending on availability. Some can use hydrogen sulfide when it's abundant and switch to methane or hydrogen when sulfide is scarce. Others can operate under aerobic or anaerobic conditions, oxidizing chemicals with oxygen when it is present and with nitrate or sulfate when it is not. This metabolic flexibility allows them to survive in environments where conditions change rapidly and unpredictably, such as around hydrothermal vents, where the flow of vent fluid can fluctuate dramatically over short periods of time. The adaptations of chemoautotrophs to extreme conditions are equally impressive. Many species thrive at temperatures above 100 degrees Celsius, temperatures that would denature most proteins. They achieve this with specialized enzymes and membrane structures that remain stable under intense heat. Others live under immense pressure, with cellular machinery adapted to function in conditions that would crush most life forms. Some tolerate high concentrations of heavy metals or acidic conditions that would dissolve most biological tissues. These adaptations are not just curiosities, they're essential for survival in the extreme environments of the deep ocean, and they demonstrate the extraordinary capacity of life to evolve solutions to seemingly insurmountable challenges. The existence of chemoautotrophs has reshaped our understanding of life's origins. Before their discovery, most scientists believed that life must have begun in environments powered by sunlight. The realization that chemical energy alone can support complex ecosystems opened new possibilities. Many researchers now believe that life on Earth may have originated in hydrothermal vent environments, where natural chemical gradients provided the energy needed for the first metabolic reactions. The interaction of hot, mineral-rich fluids with cold seawater creates sharp differences in temperature, pH, and chemical composition, differences that could have driven the formation of organic molecules and primitive metabolic networks. If this is true, then chemoautotrophy is not just a fascinating adaptation, it is a window into the earliest chapters of life's story. This perspective has profound implications for the search for life beyond Earth. If life can thrive in darkness, drawing energy from chemical reactions deep within a planet, then it might also exist on worlds far from any star. The icy moons of Jupiter and Saturn, such as Europa and Enceladus, are believed to have liquid oceans beneath their frozen surfaces. Evidence suggests that hydrothermal activity may occur on their seafloors, creating conditions similar to those around Earth's vents. If chemoautotrophic life exists anywhere beyond Earth, these subsurface oceans are among the most promising places to find it. The same principles that sustain microbial life in the deep ocean could sustain alien ecosystems beneath the ice of distant moons. The study of chemoautotrophs is not just an academic exercise. These microbes and their enzymes have practical applications in biotechnology, industry, and environmental management. Enzymes from thermophilic chemoautotrophs, for example, are used in industrial processes that require high temperatures. Methane oxidizing bacteria have potential uses in reducing greenhouse gas emissions or producing biofuels. Hydrogen oxidizing microbes could be harnessed for bioenergy production. Even the mechanisms by which chemoautotrophs fix carbon could inform new approaches to carbon capture and sequestration, helping to mitigate climate change. The deep ocean is not just a repository of biological diversity, it is a source of tools and ideas with the potential to transform human technology. Despite their importance, chemoautotrophs remain poorly understood. Many species have never been cultured in the laboratory, and their metabolic pathways are known only from genetic sequences. The interactions between different microbial species, the ways in which they form communities, and the factors that control their activity are active areas of research. Even the total abundance and distribution of chemoautotrophic life in the deep ocean are uncertain. As new technologies allow us to sample and analyse deep-sea environments more effectively, we are likely to discover even greater diversity and complexity than we currently imagine. Chemoautotrophs also raise fundamental questions about the nature of life. They demonstrate that metabolism, the ability to capture and use energy, is more fundamental than photosynthesis or even sunlight. They show that life is not dependent on a narrow set of conditions but can emerge wherever energy flows, whether from a star or from the heart of a planet. They reveal that biology and geology are deeply intertwined, that the chemical reactions shaping rocks and minerals can also sustain living cells, and they remind us that the boundaries of life are far broader than we once believed. The hidden engines of the deep are not confined to vents and seeps. They are present in the sediments that blanket the seafloor, in the cracks and pores of the ocean crust, and even within the rocks themselves. They operate on timescales that stretch far beyond human lifespans, cycling elements and shaping the chemistry of the planet over millions of years. They are small and invisible, yet their collective impact is vast. Without them, the deep ocean would be sterile, its ecosystems impossible. With them, it becomes a realm of astonishing complexity and resilience, and as the currents carry the chemical signatures of their activity into the broader ocean, their influence extends far beyond their immediate surroundings. Nutrients released by chemoautotrophic microbes can fuel surface productivity thousands of kilometers away. The carbon they fix can become buried in sediments, locking away greenhouse gases for geological timescales. The metals they transform can precipitate into deposits that shape the composition of the seafloor. These hidden engines are not just sustaining life in the deep, they are shaping the Earth itself. The story of life in the deep ocean is, in many ways, the story of these microbes. They are the foundation upon which entire ecosystems are built, the architects of chemical cycles that sustain the planet, and the descendants of processes that may have given rise to life itself. They remind us that life is not fragile or narrowly confined. It is adaptable, inventive, and deeply rooted in the fundamental processes of the Earth. And as we continue deeper into the abyss, following the trails of energy and chemistry that sustain it, we begin to see that the boundary between the living and the non-living is not a sharp line but a continuum, a flow of matter and energy that connects the rocks beneath our feet to the cells within our bodies. What lies beyond this hidden engine are ecosystems shaped by the eternal dance between predator and prey, where energy captured by microbes is transformed into muscle, motion, and instinct. The story of the deep ocean is not just one of chemistry and microbes. It is also one of struggle and adaptation, of hunters and hunted, of survival in a world where every encounter matters. And as we follow that story deeper still, we will see how life built on chemical energy gives rise to forms and behaviours as remarkable as any on the sunlit surface of our world. In the deep ocean, where sunlight has long since vanished and darkness is absolute, the struggle for survival is no less intense than it is on the surface. Predators still stalk prey, prey still evade predators, and the balance between hunter and hunted still shapes the structure of ecosystems. But here, in this vast blackness, the rules of the game are different. Vision, speed, and strength, the traits that dominate in the open skies or shallow seas, are often less important than patience, deception, and adaptation. Every encounter is shaped by scarcity, every movement calculated to conserve energy, and every kill a matter of life and death. It is a world where the hunt unfolds in silence and shadow, and where life has evolved astonishing strategies to survive in eternal night. Predation in the deep ocean is defined first and foremost by scarcity. Food is not abundant here. It does not grow from the sun's energy as it does in the shallows, nor does it drift past in endless schools as it does in the productive surface layers. Instead, it arrives unpredictably, a sinking carcass from above, a stray fish wandering into unfamiliar territory, a faint rain of particles drifting down from the surface. For predators, opportunities are rare, and missing one can mean weeks or months without a meal. For prey, every mistake can be fatal. The stakes are high, and evolution has sculpted both sides of the predator-prey relationship into forms that seem strange and otherworldly, but are perfectly suited to the deep. One of the most striking adaptations among deep-sea predators is the ability to wait. Many hunters here do not chase their prey, they ambush it. Movement burns energy, and in a place where energy is precious, wasting it can be deadly. Instead of speed, deep-sea predators rely on stealth, patience, and sudden bursts of violence. They hover motionless in the water, their bodies blending into the darkness, waiting for the vibrations of a passing fish or the faint glow of a bioluminescent signal. When the moment comes, they strike with explosive speed, capturing their prey before it can react. The viperfish, with its enormous fangs and lightning-fast strikes, is a classic example. It spends much of its time hovering motionless, then lunges forward with such velocity that its jaws can pierce through even the hard scales of armoured prey. Deception is another common tactic. In a world without sunlight, where sight is limited and curiosity can be fatal, lures are an effective weapon. The anglerfish is perhaps the most famous practitioner of this art. A modified fin ray extends from its head like a fishing rod, tipped with a glowing bulb produced by symbiotic bacteria. The light mimics the small flashes of bioluminescent plankton or tiny prey animals, drawing curious fish closer. When they come within range, the anglerfish's enormous mouth snaps shut, swallowing them whole. Other species use similar tricks. Some squid dangle bioluminescent organs from their arms. Some jellyfish mimic the flashing signals of prey. Even some predatory worms emit glowing threads that lure small animals into their grasp. In the deep, deception can be more powerful than strength. Prey species, of course, are not passive participants in this struggle. They have evolved their own suite of adaptations to evade predators. Many rely on invisibility. Transparency is one of the most common strategies, with gelatinous bodies that allow light to pass through and reveal nothing. Others use dark pigmentation, often deep red or black, to absorb what little light exists, rendering them almost invisible against the backdrop of the abyss. Some use reflective surfaces to scatter light and erase their outlines. Others practice counter-illumination, producing bioluminescent light on their undersides that matches the faint glow from above and hides their silhouettes from predators below. Each of these strategies reduces the likelihood of detection, buying prey precious moments in which to escape. Escape itself often relies on speed and agility, but in the deep ocean, those qualities are used sparingly. Bursts of movement require energy, and prey cannot afford to waste it unless the threat is imminent. Instead, many rely on startle responses, sudden explosive movements triggered by the approach of a predator. Some squid eject jets of water to propel themselves rapidly away. Some release glowing clouds of bioluminescent mucus or ink, creating a distraction while they flee. Even gelatinous animals like jellyfish can contract their bodies suddenly, pulsing into motion when danger nears. These tactics are not designed for long chases but for rapid escapes, quick enough to put distance between predator and prey in the crucial first seconds after detection. Some prey species employ more creative defences. Certain shrimp species, when threatened, snap their claws so rapidly that the resulting shockwave can stun predators or break apart incoming attacks. Some fish inflate their bodies to make themselves harder to swallow. Others carry chemical defences, toxins that make them unpalatable or even lethal to potential predators. Some of these toxins are produced by the prey themselves, while others are acquired from their diet or from symbiotic bacteria. Even in the deep, where energy is scarce and simplicity is often favoured, evolution finds ways to arm the hunted. The interactions between predator and prey in the deep ocean are not always straightforward. Many species blur the lines, being both predator and prey depending on circumstances. A small crustacean that grazes on microbial mats may be preyed upon by a fish, which is then hunted by a larger predator. A scavenger feeding on a whalefowl may become a meal for a lurking eel. The roles shift constantly, and the balance between hunter and hunted is dynamic. This fluidity is essential to the functioning of deep-sea ecosystems, where energy is scarce and must be recycled as efficiently as possible. The scarcity of food also drives extreme opportunism. Many predators will eat almost anything they can catch, from live prey to carrion. Scavenging is common, and many species are both active hunters and scavengers, switching between strategies as opportunities arise. Some deep-sea fish have distensible stomachs and elastic jaws, allowing them to swallow prey far larger than themselves. The black swallower, for example, can consume fish several times its own mass, stretching its stomach to extraordinary sizes. These adaptations allow predators to make the most of rare feeding opportunities, storing energy for the long periods between meals. The unpredictability of food availability also influences the timing of predatory behaviour. Many deep-sea organisms are more active when marine snow, the slow rain of organic particles from the surface, is abundant. Some predators time their reproductive cycles to coincide with seasonal peaks in food supply, ensuring that their young have the best chance of survival. Even scavengers respond quickly to new food sources, converging from great distances when a large carcass sinks to the seafloor. Whalefoals, in particular, create temporary oases of life in the deep. Scavengers arrive within hours, stripping the soft tissue within weeks. Predators follow, drawn by the abundance of prey. Over time, entire communities form around the carcass, transforming it from a single meal into a complex, multi-stage ecosystem that can last for decades. Predator-prey interactions also shape the behaviour and physiology of deep-sea animals in subtler ways. Many species have evolved heightened sensory systems to detect the faintest cues of prey or predator presence. Some fish have enormous eyes that capture even the tiniest glimmers of bioluminescent light. Others rely on lateral lines, sensory organs that detect vibrations and pressure changes in the water. Some predators can sense electrical fields produced by the movements of prey. Even chemical cues are important, with some animals able to detect minute concentrations of molecules released by potential food sources or threats. These senses are finely tuned to the deep-sea environment, where visibility is limited and information is scarce. Camouflage and mimicry are not limited to prey. Some predators have evolved to resemble harmless organisms or even parts of the environment, allowing them to approach undetected. Certain deep-sea fish have elongated, thread-like bodies that resemble drifting debris. Others remain motionless and covered in sediment, indistinguishable from the seafloor until they strike. Some predators mimic the bioluminescent patterns of non-threatening species, luring prey closer under false pretenses. In a world where light is rare and perception is limited, deception is a powerful tool for both hunter and hunted. The slow pace of life in the deep also influences predator-prey dynamics. Many deep-sea animals have low metabolic rates, which means they require less energy and can survive long periods without food. This allows predators to go weeks or even months between meals and prey to endure long stretches without eating. It also means that encounters between predators and prey are infrequent but significant. When they occur, they often determine the survival and reproductive success of the individuals involved. This slow, deliberate rhythm shapes the entire ecosystem, from the behaviour of individual animals to the structure of communities. Predation in the deep is not limited to animals. Microbes also engage in predator-prey interactions, albeit on a microscopic scale. Some bacteria prey on other bacteria, penetrating their cell walls and consuming their contents. Viruses infect and kill microbial cells, releasing organic matter that other microbes can use. These interactions may seem insignificant, but they play a crucial role in recycling nutrients and controlling microbial populations. In a place where energy is scarce, even the smallest predatory events can have ripple effects throughout the ecosystem. The predator-prey dynamics of the deep ocean also reveal much about the evolutionary pressures that shape life here. Traits that would be disadvantages in other environments can become advantages in the deep. Slow growth and long lifespans, for example, are beneficial when food is scarce and predation events are rare. Large mouths and distensible stomachs are useful when meals are unpredictable. Bioluminescent lures, transparent bodies, and chemical defenses all represent solutions to the unique challenges of life in darkness. Each adaptation reflects millions of years of evolutionary trial and error, each success building on the failures of countless generations. These dynamics also influence the larger structure of deep-sea ecosystems. Predator-prey interactions determine the distribution and abundance of species, shape community composition, and influence energy flow. Predators control prey populations, preventing them from overexploiting resources. Prey availability limits predator numbers, ensuring that no single species dominates. Scavengers and decomposers recycle nutrients, sustaining microbial communities that, in turn, support higher trophic levels. The balance between predator and prey is delicate but essential, and disruptions to it can have cascading effects throughout the ecosystem. Human activities have the potential to disrupt these delicate relationships. Deep-sea fishing, for example, can remove key predators or prey species, altering food webs and changing the dynamics of entire ecosystems. Deep-sea mining and pollution can damage habitats and reduce biodiversity, affecting the balance between hunters and hunted. Even climate change can have indirect effects, altering the supply of organic matter from the surface or changing the chemistry of the deep ocean. These changes ripple through predator-prey relationships, potentially reshaping ecosystems that have been stable for millions of years. Despite these challenges, the predator-prey dynamics of the deep remain among the most fascinating aspects of this hidden world. They reveal the creativity of evolution in solving the problems of survival in a harsh and unforgiving environment. They show how life adapts to scarcity, how it uses deception and patience as weapons, and how it turns even the most inhospitable conditions into opportunities. They demonstrate that the struggle between hunter and hunted is universal, unfolding in every corner of the planet, even in places where light has never shone. And as we continue deeper into this world, following the trails of energy from the microbes that capture it to the predators that consume it, we see that the story of life in the deep is one of connection. Every organism, from the smallest bacterium to the largest predator, is linked by the flow of energy and matter. Every kill fuels new life, every death sustains new growth, and every interaction, predator chasing prey, prey evading predator, shapes the world around it. This story does not end with the hunt. Beyond the predator and prey lies another layer of adaptation, one that reveals how life in the deep ocean grows to sizes and ages unimaginable elsewhere, where time itself seems to slow and biology bends to the will of the abyss. One of the most surprising discoveries of deep ocean exploration is the sheer size of some of the creatures that inhabit its depths. In a realm where food is scarce, temperatures hover just above freezing, and pressure crushes anything unprepared for its weight, you might expect life to grow small, to shrink and conserve. Yet time and again, explorers encounter organisms of extraordinary size. Giant squid longer than school buses, amphipods the size of human hands, isopods as big as puppies, jellyfish with tentacles stretching for meters, and single-celled organisms larger than a human fist. These deep-sea giants seem to defy the expectations set by their harsh environment. But they are not accidents of nature. They are the result of millions of years of evolution, shaped by the unique pressures and opportunities of life in the abyss. The phenomenon is known as deep-sea gigantism, and it appears across a wide range of taxa, from invertebrates to fish to microbes. It is not universal. Many deep-sea organisms are small, often microscopic, but it is far more common in the deep ocean than in shallower waters. Understanding why requires examining the conditions that define this environment and how they shape the biology of the creatures that live here. Cold, pressure, scarcity, and time all play crucial roles in creating giants of the deep. Cold is one of the most significant factors. Temperatures in the deep ocean are consistently low, often just a few degrees above freezing. Cold slows metabolic processes, reducing the rate at which organisms consume energy. A slower metabolism means that growth can continue for longer periods, leading to larger sizes over time. It also reduces the overall energy requirements of the organism, allowing it to allocate more resources to growth rather than maintenance. In essence, the cold acts as a biological brake, slowing life's pace and giving organisms the time they need to grow to extraordinary sizes. Pressure is another key factor. At depths of thousands of meters, the weight of the water above exerts crushing force, hundreds of times the pressure at the surface. This intense pressure affects not just the structure of organisms but also their physiology. Larger bodies are more resistant to pressure changes and can distribute the immense force more evenly. This may partly explain why many deep-sea animals grow to large sizes. Their bulk helps them withstand the physical realities of their environment. Moreover, the pressure influences the density and viscosity of water, altering how nutrients and oxygen are distributed. Larger body size can improve the efficiency of nutrient absorption and gas exchange in these conditions, providing a further advantage. Scarcity might seem like a reason for small size, but paradoxically it can also drive gigantism. In the deep ocean, food is rare and unpredictable. When a meal arrives, whether a sinking carcass, a swarm of migrating prey, or a rare feeding opportunity, larger animals are better equipped to exploit it. They can consume more food at once, store more energy in the form of fat or glycogen, and survive longer periods without eating. They can also travel greater distances in search of food, a crucial advantage in a vast and sparsely populated environment. Gigantism, in this sense, is an adaptation not to abundance but to its absence. Time plays perhaps the most important role of all. Many deep-sea organisms live far longer than their shallow water relatives. Some fish and invertebrates live for decades or even centuries. Growth is slow but steady, accumulating over long lifespans. This slow pace is a response to the cold, low-energy environment, where rapid growth is neither possible nor necessary. Over decades, small differences in growth rate add up, resulting in creatures that dwarf their surface counterparts. Time, rather than a burst of rapid development, builds the giants of the deep. One of the most iconic of these giants is the giant squid, a creature long shrouded in myth and mystery. For centuries, sailors told stories of enormous tentacled monsters dragging ships beneath the waves. Only in the last few decades have scientists begun to study these elusive animals in detail. Giant squid can grow over 12 meters in length, with eyes the size of dinner plates, the largest of any animal on Earth. These massive eyes are perfectly adapted to the darkness, capable of detecting the faintest glimmers of light, such as the bioluminescence of approaching predators like sperm whales. Despite their size, giant squid are elusive hunters, using their long feeding tentacles to snatch prey from a distance before pulling it toward their sharp, parrot-like beaks. Their colossal size is not just an accident of evolution, it is a response to the challenges of life in the deep, where prey is scarce. Predators are formidable, and survival demands both patience and power. Even larger, though less famous, is the colossal squid, a close relative that can exceed the giant squid in mass. With shorter, thicker arms and hooks instead of suckers, the colossal squid is built for ambush, seizing prey with brute strength rather than speed. Its bulk helps it conserve energy and store reserves for long periods without food. It also provides protection against predators, including sperm whales, which bear the scars of battles with these enormous cephalopods. Encounters between sperm whales and colossal squid are among the most dramatic predator-prey interactions in the deep ocean, titanic struggles between two of the largest creatures on the planet, playing out in darkness thousands of meters below the surface. Not all giants in the deep are hunters. Many are scavengers or filter feeders, taking advantage of whatever resources drift their way. The giant isopod, for instance, is a distant relative of the pillbugs found in gardens, but it grows up to 0.5 meter long. It roams the seafloor on jointed legs, feeding on carcasses and organic debris that settle from above. Its large size allows it to consume and store large amounts of food, which is critical in an environment where meals may be separated by months or even years. Giant isopods can survive for extended periods without eating, slowing their metabolism to a crawl and entering a state of near dormancy until the next meal arrives. Amphipods, small crustaceans that are usually only a few millimeters long in shallow waters, can reach sizes of over 30 centimeters in the deep ocean. These supersized scavengers often gather around whale falls, where they tear into soft tissue with remarkable efficiency. Like the isopods, their size allows them to exploit rare food sources more effectively and outcompete smaller scavengers. Their large bodies also help them resist the intense pressure of the deep and navigate the dense, viscous water more efficiently. Even single-celled organisms can reach enormous sizes in the deep. Xenophyophorus, a group of giant amoebas that live on the seafloor, can grow up to 20 centimeters across, dwarfing most multicellular plankton. They build intricate branching structures from sediment grains, creating habitats for smaller organisms and influencing nutrient cycling. Their large size allows them to engulf more food particles and process them more efficiently, an advantage in an environment where every scrap of organic matter is valuable. Fish, too, exhibit deep-sea gigantism. The oarfish, a long ribbon-like fish that can grow over 11 meters, is the longest bony fish in the world. It spends most of its life in the deep ocean, feeding on small crustaceans and squid. Its elongated body and slow undulating swimming style are well suited to conserving energy in a low-food environment. The grenadiers, or rat tails, are another example. These deep-sea fish can grow over 2 meters long and live for more than 50 years. They feed on a wide range of prey, from small fish to carrion, and their size allows them to cover large areas in search of food. Gigantism is not limited to animals. Some deep-sea jellyfish have bell diameters exceeding 1 meter and tentacles stretching more than 10 meters. These giants drift slowly through the water, using their vast surfaces to capture tiny plankton and organic particles. Their size increases their feeding efficiency, allowing them to capture more food with less energy. It also makes them less vulnerable to predators, which are less likely to attack such large and potentially unwieldy prey. The slow pace of life in the deep also influences reproduction and development in ways that contribute to gigantism. Many deep-sea animals grow slowly over long lifespans, delaying reproduction until they reach substantial size. This strategy reduces the risk of predation and increases the likelihood of reproductive success. Larger animals can produce more offspring, invest more resources in each one, and better protect them from environmental fluctuations. Slow growth also means that individuals can accumulate more resources over time, supporting larger body sizes and more complex physiological systems. The evolutionary advantages of gigantism in the deep ocean are numerous. Larger size can deter predators, making an animal less likely to be attacked. It can also improve mobility, allowing animals to travel farther in search of food or mates. It can increase storage capacity for energy reserves, extending survival during lean times. It can enhance reproductive output, giving larger individuals an advantage in passing on their genes, and in some cases it can improve physiological efficiency, allowing for better oxygen transport, more effective digestion, or enhanced sensory perception. Gigantism can also influence the structure of deep-sea ecosystems. Large scavengers like isopods and amphipods play a crucial role in breaking down carcasses and recycling nutrients. Large predators like squid and rat tails control the populations of smaller animals, shaping community dynamics. Large filter feeders like jellyfish and xenophyophores help regulate the distribution of organic particles, influencing nutrient cycling and energy flow. The presence of giants affects not just individual interactions, but the functioning of entire ecosystems, linking the biological and chemical processes of the deep in complex ways. Despite their size and importance, many deep-sea giants remain poorly understood. They are difficult to study, often living in environments that are inaccessible to humans and even to remotely operated vehicles. Many species have never been observed alive in their natural habitat, and much of what we know comes from specimens that have floated to the surface or been caught accidentally. These specimens often arrive damaged or distorted by the change in pressure, making it difficult to study their physiology and behaviour. Even their life cycles are poorly understood. We know little about how giant squid reproduce, how long giant isopods live, or how xenophyophores build their massive structures. The mystery surrounding these giants only adds to their fascination. They are reminders of how little we know about the deep ocean and how much remains to be discovered. They also challenge our assumptions about the limits of life. Gigantism in the deep demonstrates that large size is not confined to environments of abundance. It shows that life can grow colossal even in scarcity, that size can be a strategy for survival as much as speed or stealth. It reveals that evolution does not follow a single path, but explores every possible solution to the challenges it encounters. The existence of deep-sea giants also has implications beyond marine biology. It informs our understanding of how organisms respond to extreme environments, how size and metabolism are linked, and how ecosystems function under conditions of low energy and high pressure. It even offers clues about the potential for large life forms on other worlds. If life exists beneath the icy crusts of distant moons or in the subsurface oceans of exoplanets, it may face conditions similar to those of the deep ocean, cold, dark, and nutrient poor. If so, gigantism might emerge there too, shaped by the same forces that sculpted the giants of Earth's abyss. The slow pace of life that underlies deep-sea gigantism also influences the broader dynamics of these ecosystems. Many giants grow slowly and reproduce infrequently, making them vulnerable to disturbances. Human activities such as deep-sea trawling and mining can have devastating effects on their populations, and recovery may take centuries. The destruction of whale populations by industrial whaling, for example, likely reduced the frequency of whale falls, depriving deep-sea scavengers of a crucial food source. The impacts of such changes ripple through the ecosystem, affecting everything from microbial activity to nutrient cycling. Despite these threats, the giants of the deep endure, silent and patient in their cold, dark world. They remind us that size is not just a measure of abundance, but also of adaptation. They show us that life can grow vast and powerful, even where energy is scarce and conditions are harsh. And they invite us to reconsider our understanding of biology, to see that the rules we take for granted on the surface do not always apply in the depths. As we continue deeper into the abyss, the story of size gives way to another dimension of life in darkness, one that concerns not how large organisms grow, but how they perceive and respond to a world without day or night. In the absence of sunlight, time itself changes, and life must find new ways to measure its passing. The giants that drift and crawl through the deep ocean do so in a realm where days and seasons mean nothing, and yet they, like all living things, must still regulate their rhythms, coordinate their behaviours, and anticipate the future. Understanding how they do this reveals yet another layer of adaptation, one that links biology not just to energy and size, but to the fundamental fabric of time itself. Life on the surface of our planet is ruled by the sun. Every living thing, from the simplest bacterium to the most complex mammal, is shaped by the daily cycle of light and darkness. Plants open their leaves to the morning, animals wake and sleep in step with the rising and setting of the sun, and even the smallest cells operate on internal rhythms tied to this predictable pattern. Our world is built on the cadence of day and night, and time, for most life, is measured in the passage of light across the sky. But deep beneath the ocean, where sunlight cannot penetrate and the world is bathed in permanent darkness, this universal clock no longer exists. Here, there is no dawn or dusk, no sunrise or sunset, no seasons marked by the tilt of the earth, and yet life persists, and it still must reckon with time. The creatures of the deep have found ways to measure it, ways to sleep, feed, grow, and reproduce in a world without the cues that surface life takes for granted. Timekeeping in the deep ocean is not a trivial challenge. Circadian rhythms, the internal biological clocks that govern so many processes, are deeply rooted in the daily cycle of light and dark. These rhythms regulate sleep and wakefulness, feeding behaviour, hormone production, and countless other physiological functions. They are so fundamental that even organisms that live underground or inside other organisms retain them, their internal clocks ticking in sync with the world above. But what happens when that external signal disappears entirely? How do organisms know when to rest, when to hunt, when to reproduce, when to migrate? How do they coordinate their lives in an environment where every hour is as dark as the next? The answer is that life adapts. Some deep-sea organisms retain circadian rhythms even in the absence of light, their internal clocks free-running without external cues. These rhythms may drift slightly over time, becoming longer or shorter than 24 hours, but they still provide a framework for organising behaviour. Others have shifted to entirely different temporal patterns, responding not to day and night, but to the subtle cycles of the deep sea itself. The tides, the seasonal pulses of organic matter from above, the slow drift of currents. All of these can provide time cues in the absence of sunlight. Life in the deep does not ignore time, it redefines it. One of the most consistent rhythms in the deep ocean is the vertical migration of organisms. Every night, billions of animals, from tiny zooplankton to large fish, ascend toward the surface to feed, retreating back to the depths before dawn. This daily migration, known as diel vertical migration, is the largest synchronized movement of life on the planet. Even at depths where light never reaches, animals participate in this migration, rising and falling with remarkable precision. They do so not because they see the sun, but because they detect subtle changes in pressure, temperature, or chemical composition associated with the movements of water masses. These cues allow them to track the daily cycle indirectly, maintaining a rhythm even in the perpetual night. Some deep-sea organisms synchronize their activities with longer-term cycles. Seasonal pulses of marine snow, for example, can trigger reproductive events or feeding frenzies. When phytoplankton blooms in the surface ocean die and sink, they deliver a surge of organic material to the deep, providing a rare abundance of food. Many deep-sea animals time their reproduction to coincide with these events, ensuring that their offspring hatch into an environment with sufficient resources. This strategy requires a form of timekeeping, a way of anticipating when the pulse will arrive. Some species may use subtle temperature changes or shifts in nutrient concentrations as cues. Others may rely on internal calendars, counting the passing days in ways we do not yet fully understand. Biological clocks in deep-sea organisms are often remarkably flexible. Experiments have shown that some species can adjust their rhythms to match environmental cycles other than the 24-hour day. Certain deep-sea fish, for example, exhibit activity patterns tied to the lunar cycle, responding to the gravitational effects of the moon even in total darkness. Others respond to tidal cycles despite being far below the reach of tidal currents. These rhythms may seem surprising, but they highlight the adaptability of biological timekeeping. Life does not require sunlight to measure time. It can use any regular, predictable change in the environment as a clock. Even in the absence of external cues, internal biological rhythms persist. At the molecular level, circadian clocks are built from feedback loops of gene expression. Certain genes switch on and off in a regular sequence, producing proteins that accumulate and degrade over time, creating oscillations with a roughly 24-hour period. These molecular clocks are found in organisms from bacteria to humans, and they can continue to function even in constant darkness. In the deep sea, where external signals are weak or absent, these internal clocks may drift slightly, but they still provide structure to the organism's physiology. They ensure that metabolic processes, DNA repair and other critical functions occur at optimal times, even if those times are no longer tied to the sun. The persistence of these rhythms raises fascinating questions about the evolution of timekeeping. Circadian clocks likely evolved early in life's history when sunlight was a dominant environmental signal, but their continued presence in deep-sea organisms suggests that they have been retained because they are useful beyond responding to light. They may help organisms coordinate internal processes, maintain metabolic efficiency, or prepare for regular environmental changes, even when those changes are not tied to the day-night cycle. In this sense, biological timekeeping is not just about responding to the environment, it is also about creating internal order in a chaotic world. Sleep, too, takes on new forms in the deep. On the surface, sleep is often tied to the cycle of day and night, with most animals resting during one and active during the other. In the deep ocean, where darkness is constant, this division loses meaning. Yet sleep, or at least periods of reduced activity and metabolic slowdown, still occurs. Fish, crustaceans, and even some invertebrates exhibit behaviours analogous to sleep, becoming less responsive to stimuli and reducing their energy expenditure for extended periods. These rest states may not follow a strict daily pattern, but they still serve the same essential functions: conserving energy, repairing tissues, consolidating memory, and maintaining neural function. The timing of rest in the deep may be influenced by factors other than light. Some animals may enter rest states after feeding, using the downtime to digest and process nutrients. Others may rest during periods of low food availability, conserving energy until conditions improve. Predators may rest when prey is scarce or inactive, while prey species may rest when the risk of predation is low. In this way, rest becomes a flexible, adaptive behaviour rather than a rigid clock-driven cycle. The absence of sunlight also affects how deep-sea organisms perceive time on longer scales. On the surface, many species rely on seasonal changes in day length to trigger reproduction, migration, or hibernation. In the deep, these cues do not exist. Instead, organisms respond to other seasonal signals, such as changes in temperature, nutrient availability, or the flux of organic matter from above. Some deep-sea corals, for example, spawn in synchrony with seasonal cycles in surface productivity, releasing their gametes at times when food for their larvae will be abundant. Other species may time their migrations to coincide with seasonal shifts in water masses or currents. These behaviours show that life in the deep has not abandoned seasonality. It has simply found new ways to measure it. Some organisms may not rely on external signals at all, instead using internal timers that measure the passage of time directly. Biological clocks based on gene expression, feedback loops, can generate rhythms that persist for weeks, months, or even years. These internal timers can provide a framework for seasonal behaviours even in the absence of external cues. They may drift over long timescales, but natural selection can fine-tune them to match the rhythms of the environment. The result is a remarkable convergence. Even in a world without seasons defined by light, organisms can still synchronize their lives with the rhythms of the Earth. The study of timekeeping in the deep ocean is still in its infancy. Many of the mechanisms by which deep-sea organisms measure time remain unknown. Laboratory experiments are difficult, as bringing deep-sea species to the surface often alters their behavior. Observations in the wild are challenging, requiring long-term monitoring in remote and inhospitable environments. Despite these obstacles, researchers have begun to piece together a picture of how life keeps time in darkness. It is a picture that is both familiar and strange, showing that while the basic principles of biological timekeeping are universal, their expression can vary dramatically depending on context. This research has implications beyond marine biology. It sheds light on the fundamental nature of biological rhythms and their role in life's processes. It suggests that circadian clocks are deeply embedded in biology, not merely as responses to light, but as core mechanisms for organising internal processes. It also highlights the flexibility of these clocks, showing that they can adapt to environments that bear little resemblance to the sunlit world in which they evolved. These insights may even inform medicine and human health, helping us understand how our own internal clocks function and how they can be adjusted when external cues change, as they do in shift work, space travel, or prolonged isolation. The adaptability of timekeeping in the deep also has implications for the search for life beyond Earth. On planets and moons far from the Sun, where light may be weak or absent, life would still need to measure time to coordinate its processes. The strategies used by deep-sea organisms, free-running clocks, responses to chemical or physical cycles, reliance on internal timers, may offer clues about how alien life could solve the same problem. They suggest that timekeeping is not a luxury, but a necessity, a universal feature of life that persists even when its most obvious cues are gone. The absence of sunlight also changes how organisms experience time subjectively. On the surface, daily and seasonal cycles create a sense of temporal structure. In the deep, that structure dissolves. Time stretches and blurs, measured not by the movement of the sun but by the slow drift of currents, the rare arrival of food, the occasional eruption of a hydrothermal vent. For creatures that live centuries or more, individual days may mean little. Their lives unfold on scales that dwarf our own, measured in decades or centuries rather than hours or days. Even for shorter-lived species, time in the deep has a different texture, defined less by external change than by internal rhythms. This altered sense of time influences behaviour in ways we're only beginning to understand. Some deep-sea animals exhibit astonishing patience, waiting months for prey or years for the right conditions to reproduce. Others migrate vast distances over long periods, their movements guided by cues too subtle for us to detect. The rhythms of the deep are slow, deliberate and measured, reflecting the environment itself. They remind us that time is not a single, universal experience, but a spectrum shaped by context and necessity. The ability to function without sunlight also speaks to the resilience and adaptability of life. It shows that biological systems are not dependent on a single environmental condition. They can adjust, recalibrate, and repurpose their mechanisms to suit new circumstances. They can find order in apparent chaos and measure time even when its most obvious markers are gone. This resilience is one of the reasons life has been so successful on Earth, spreading into every corner of the planet and thriving in environments that seem utterly hostile. As we continue deeper into the story of the deep ocean, the question of time leads naturally to questions of communication. In a world without light, how do organisms signal to one another? How do they find mates, coordinate behaviours, or warn of danger when sight is useless and sound travels differently? Just as timekeeping has evolved new forms in the dark, so too has communication. And in the depths of the ocean, where silence seems absolute, life has found ways to speak, to signal, and to connect across the void. In the vast darkness of the deep ocean, where light has been extinguished and silence seems eternal, communication might appear impossible. On land and in shallow seas, animals rely on sight, sound, and scent to connect with one another, to find mates, warn of predators, coordinate hunts, or stake out territory. But here, light cannot travel far. Visual signals fade within meters, if they exist at all. Sound behaves differently too, moving through water with speed and clarity, but distorted by pressure, temperature and depth. Even chemical signals, so crucial in many aquatic environments, disperse slowly and unpredictably in the cold stillness of the abyss. Yet despite these challenges, Communication is everywhere. It is woven into the fabric of deep-sea life, subtle and sophisticated, improvised and ingenious. Creatures here have not abandoned the need to signal and respond. They have reimagined it. The most spectacular and widely known form of communication in the deep is bioluminescence. In a world without sunlight, light becomes a powerful language. Bioluminescence is produced by chemical reactions within an organism's body, often involving the enzyme luciferase and a light-emitting molecule called luciferin. This process requires remarkably little energy, a crucial advantage in an environment where energy is scarce. It has evolved independently dozens of times across the tree of life, appearing in bacteria, fish, squid, jellyfish, and even some crustaceans. Each lineage has shaped it to its own purposes, turning light into a tool for survival and interaction. For some organisms, bioluminescence is a way to attract mates. In the deep, where individuals of the same species may be widely scattered, finding a partner is a significant challenge. Many animals solve it by producing species-specific light displays. Certain deep-sea shrimp, for example, flash in precise patterns to signal their readiness to reproduce, ensuring that their signals are recognized only by members of their own kind. Some fish emit rhythmic pulses of light from specialized organs, their patterns functioning as identification codes. Even tiny plankton use flashes of light to coordinate swarming behaviors that bring individuals together for reproduction. These signals are often invisible to other species, tuned to wavelengths and intensities that only potential mates can detect. Bioluminescence is also used to coordinate behavior within groups. Some species of deep-sea squid communicate through synchronized light pulses, flashing patterns that signal movement, readiness, or alarm. These light shows are not random. They follow precise sequences that other members of the group can interpret. Coordinated flashes can help squid school together in darkness, avoid collisions, or respond collectively to predators. In this way, bioluminescence becomes a social tool, replacing vision-based cues that would otherwise be lost in the dark. Predators have found ways to exploit light for their own purposes. As with the anglerfish's glowing lure, bioluminescence can be used to attract prey by mimicking the signals of harmless organisms, or by drawing attention in an otherwise featureless landscape. Some deep-sea jellyfish produce sudden, bright flashes when touched, startling potential predators and distracting them long enough for escape. Others release glowing mucus into the water, creating a luminous decoy that confuses attackers. Even bacteria participate in this luminous dialogue, forming symbiotic relationships with fish and squid and providing them with light-producing capabilities that they can control and deploy as needed. For prey, bioluminescence can serve as a defense. Some animals produce intense flashes when threatened, blinding predators or revealing their position to larger hunters that might attack them instead. This burglar alarm strategy turns light into a weapon, transforming vulnerability into a chance of survival. Others use counter-illumination, producing light on their undersides that matches the faint glow filtering down from the surface. This camouflage technique erases their silhouette, making them invisible to predators lurking below. In a realm where shadows and outlines can mean the difference between life and death, the ability to control and manipulate light is a powerful advantage. Bioluminescence is not the only language spoken in the deep. Sound plays a vital role as well, particularly among larger animals. Sound travels faster and farther in water than in air, and in the deep ocean, it can propagate over hundreds or even thousands of kilometers. Many deep-sea species have evolved ways to exploit this property, using sound to communicate across distances that light or chemical signals could never bridge. Whales are the most famous practitioners of this acoustic language. Their songs, complex sequences of clicks, moans, and whistles, can travel vast distances, carrying information about identity, location, and even emotional state. These vocalizations are not limited to surface-dwelling species. Deep-diving whales like sperm whales and beaked whales produce powerful clicks used both for echolocation and communication. coordinating movements and maintaining contact in the vast darkness. Fish, too, produce sounds in the deep. Some generate drumming noises by vibrating muscles against their swim bladders, while others use stridulation, rubbing bones or teeth together to create clicks and scrapes. These sounds can serve many purposes: attracting mates, establishing territory, warning of predators, or coordinating group behaviour. Even crustaceans produce acoustic signals, snapping their claws or striking body parts together to create percussive sounds. In some deep-sea environments, such as hydrothermal vent fields, the soundscape is remarkably complex, filled with crackles, pops and hums produced by both biological and geological sources. The deep ocean's physical properties shape how sound is used. The speed and attenuation of sound depend on temperature, pressure and salinity, all of which vary with depth. These factors create layers in the water column, where sound travels differently, influencing how far and how clearly signals can propagate. Some animals exploit these properties deliberately, producing sounds that travel in specific layers to reach distant receivers. Others use the structure of the seafloor or the geometry of vent chimneys to amplify or direct their calls. The result is a sophisticated acoustic landscape in which organisms have learned to navigate and communicate with remarkable precision. Chemical signalling remains important in the deep as well, particularly for smaller organisms and those that live on or near the seafloor. Many species release pheromones, chemical signals that convey information about reproductive status, territory or danger. These signals diffuse slowly but can persist for long periods, making them useful in environments where encounters are infrequent. Some deep-sea worms, for example, release pheromones to attract mates, their signals drifting through the water until they are detected by potential partners. Other species use chemical cues to mark feeding grounds or warn conspecifics of predators. Even bacteria and archaea communicate chemically, releasing molecules that coordinate group behaviours such as biofilm formation or bioluminescent activity. The slow diffusion of chemical signals can also be advantageous. Because they linger, they can serve as records of past events, informing organisms about the recent presence of predators, prey, or competitors. A shrimp might detect the lingering scent of a predator and choose to hide rather than venture out. A scavenger might follow a trail of chemical cues to a distant carcass. A microbe might sense the density of its population through accumulated signalling molecules and alter its behaviour accordingly. In the deep ocean, where direct encounters are rare, these lingering signals extend the reach of communication beyond the moment. Some species combine multiple forms of communication, layering light, sound, and chemical signals to convey complex information. A fish might release pheromones while producing acoustic calls, signalling both its location and its reproductive readiness. A squid might flash bioluminescent patterns while emitting chemical cues, increasing its chances of attracting a mate. These multimodal signals are particularly useful in environments where any single channel may be unreliable. If light is blocked by sediment, sound or chemical cues may still carry the message. If sound is distorted by water layers, light can cut through the darkness. Flexibility is key, and deep-sea organisms excel at using every available tool. Communication in the deep is not limited to interactions within species. Many predator-prey relationships involve a form of communication, even if it is unintentional. The bioluminescent flashes of a startled prey animal may signal danger to others nearby. The chemical trail left by a predator may be detected and avoided by potential prey. The sounds produced by feeding activity may attract scavengers from great distances. These signals, though not deliberately sent, shape behaviour and interactions in profound ways. They create a network of information that connects organisms across space and time, influencing decisions and strategies even among species that never encounter one another directly. The importance of communication extends beyond individual interactions. It shapes the structure of communities and the dynamics of ecosystems. The ability to find mates influences reproductive success and population size, The capacity to coordinate group behaviour affects hunting efficiency and defence. The exchange of chemical signals between microbes can determine the composition of entire microbial communities, influencing nutrient cycling and energy flow. Even the soundscape of the deep, the background hum of biological and geological activity, can affect how species distribute themselves, with some drawn to areas of acoustic richness and others avoiding them. The complexity of communication in the deep challenges many of our assumptions about life in darkness. It shows that the absence of light does not mean the absence of interaction. It reveals that life is not isolated, even in the most remote corners of the planet. It demonstrates that information flows through the deep ocean just as it does on the surface, shaping behaviour, relationships, and evolution. It also reminds us that communication is not limited to the senses we rely on most. Sight may dominate our experience, but it is only one of many ways to connect. In the deep, sound, chemistry, and even touch can convey information as effectively as light. Human exploration of the deep has only begun to scratch the surface of this hidden language. Many of the sounds recorded by deep-sea microphones remain unidentified, their sources unknown. The purpose of many bioluminescent displays is still a mystery, as are the chemical signals that drift invisibly through the water. Even the basic communication systems of some deep-sea species have yet to be described. As technology improves, allowing us to listen more closely, see more clearly, and detect more subtle chemical cues, we are likely to discover layers of complexity that we cannot yet imagine. These discoveries have broader implications beyond marine science. Understanding how life communicates in extreme environments can inform our search for life elsewhere. On distant moons with subsurface oceans, where light is absent and conditions are similar to those of Earth's deep sea, communication may rely on chemistry, sound, or other forms we do not yet fully understand. By studying how organisms signal and interact in the deep ocean, we gain insight into how alien life might do the same. Communication also plays a role in how deep-sea ecosystems respond to change. Human activity is altering the deep ocean in ways we're only beginning to grasp. Noise pollution from shipping and seismic exploration can interfere with acoustic communication, masking signals and disrupting behaviours. Chemical pollutants can mimic or block natural signals, confusing organisms that rely on them. Even changes in temperature and acidity can affect the production and transmission of bioluminescence and sound. These disruptions can ripple through ecosystems, altering predator-prey relationships, mating behaviours, and community dynamics. Understanding how communication works in the deep is essential to predicting and mitigating these impacts. Despite the challenges, the resilience of communication in the deep is remarkable. Life has found ways to speak across darkness and distance, to signal and respond in environments where the basic tools of interaction seem absent. It has turned light into language, vibration into voice, and chemistry into conversation. It has shown that connection is possible even in the most isolated places, that information can flow even where energy is scarce, and that the need to communicate is as fundamental as the need to eat or reproduce. And as we follow this thread deeper, another layer of adaptation emerges, one that concerns not just how life connects, but how it endures. In the deep ocean, survival is not just a matter of finding food or avoiding predators. It is about building systems and structures that can withstand immense pressures, conserve scarce resources, and endure over vast spans of time. The organisms here have mastered the architecture of survival, evolving bodies and behaviours that allow them to persist in conditions that would destroy most life. To understand the deep fully, we must explore how these creatures are built, how they function, and how they thrive where nothing should. To survive in the deep ocean is to confront extremes that would annihilate most forms of life elsewhere on Earth. It is a place where pressure would crush unprotected human bodies in an instant, where temperatures hover just above freezing, where food is scarce and unpredictable, where sunlight is not just dim but absent, and where oxygen can be in short supply. It is not merely an environment that challenges life, it is one that seems to reject it. And yet, life not only persists here but thrives, diversifying into forms so strange and specialized that they often look more like the products of science fiction than of natural history. The creatures of the deep have not merely endured their environment, they have been shaped by it, evolving adaptations so profound and inventive that they redefine what we think life can do. One of the most fundamental challenges of the deep is pressure. At a depth of 4,000 meters, the water above exerts more than 400 times the pressure of the atmosphere at sea level. At 10,000 meters, the depth of the Mariana Trench, that pressure exceeds 1,000 atmospheres. For most organisms, such pressure would crush cellular structures, disrupt chemical reactions, and cause proteins to unfold. But deep-sea life has evolved ways to withstand it. The architecture of their cells is different from ours. Their membranes are rich in unsaturated fatty acids, which remain fluid under high pressure and low temperatures. Their proteins are structured to resist deformation, and many produce small molecules known as piezolites that stabilize proteins and prevent them from collapsing under pressure. Even their DNA repair mechanisms are adapted, functioning reliably despite the immense physical forces around them. The effects of pressure are not limited to the molecular scale. At larger scales, organisms must also contend with its physical consequences. Gas-filled spaces such as lungs or swim bladders are a liability in the deep, where pressure would compress them to a fraction of their original volume. Many deep-sea fish solve this problem by eliminating gas-filled organs entirely, relying instead on oil-filled bladders or neutral buoyancy achieved through body composition. Some have gelatinous tissues that are slightly less dense than seawater, allowing them to float effortlessly without expending energy. Others have dense bones and heavy musculature that allow them to remain stable in the water column despite the crushing force around them. These adaptations are not merely structural, they are functional, enabling movement, feeding, and reproduction in an environment where physical laws operate differently than they do near the surface. Temperature poses another profound challenge. Most of the deep ocean is just above freezing, typically between 1 and 4 degrees Celsius. Such cold slows chemical reactions, reduces metabolic rates, and affects the fluidity of cell membranes. Deep-sea organisms respond with biochemical and physiological adaptations that allow their bodies to function efficiently in these frigid conditions. Their enzymes are structured to remain flexible and active at low temperatures, catalyzing reactions that would otherwise proceed too slowly to sustain life. Their membranes contain lipids that remain fluid in the cold, ensuring that nutrients and signals can pass in and out of cells. Many species have antifreeze proteins that prevent ice crystals from forming in their tissues, an adaptation critical in regions where supercooled water seeps from ice-covered surfaces or polar depths. Scarcity of food shapes nearly every aspect of life in the deep. Unlike the sunlit surface waters, where photosynthesis fuels a constant influx of energy, the deep must rely on the slow trickle of organic matter from above, on rare food falls, or on chemical energy from hydrothermal vents and cold seeps. This scarcity drives adaptations in feeding strategies, metabolism, and behavior. Many deep-sea animals are opportunistic feeders, capable of consuming a wide range of food sources. Some have enormous mouths and distensible stomachs, allowing them to swallow prey much larger than themselves. Others have slow metabolisms and can survive months or even years between meals. Scavengers are abundant, converging from great distances when a carcass falls to the seafloor. Some organisms form symbiotic relationships with chemosynthetic microbes, outsourcing their energy needs to partners that can convert inorganic chemicals into food. Each of these strategies reflects the same fundamental principle. In the deep ocean, energy is precious, and wasting it is not an option. Movement is another area where adaptation is essential. In the absence of strong currents or abundant prey, many deep-sea animals move slowly, conserving energy. Their muscles are often less developed than those of their shallow water relatives, suited for bursts of motion rather than sustained swimming. Some species, like certain sea cucumbers and worms, move so slowly that they barely seem to move at all, relying on the slow drift of currents to carry them to new feeding grounds. Others have evolved to use the structure of the water itself to their advantage. Jellyfish, for instance, pulse gently to maintain position, expending minimal energy. Some fish use elongated fins to glide rather than swim. Even predators often rely on ambush rather than pursuit, waiting motionless for prey to come within striking distance. Vision, too, has adapted to the perpetual darkness. Many deep-sea animals are blind, their eyes reduced or absent altogether. Instead, they rely on other senses, vibrations, pressure changes, chemical cues, and even electric fields, to detect their surroundings. Others have evolved eyes of extraordinary sensitivity, capable of detecting the faintest traces of bioluminescence or the dim glow of starlight filtered through kilometers of water. Some species have tubular eyes that focus on the faint light from above, while others have large globular eyes that gather as much light as possible from all directions. Certain fish have two retinas stacked one behind the other, allowing them to detect both dim light and bioluminescent flashes. These adaptations turn darkness from a limitation into a navigable environment, one that organisms can sense and interpret with remarkable precision. Bioluminescence itself is another adaptation that transcends communication and becomes a tool for survival. Many predators use it to lure prey, as in the anglerfish's glowing lure. Prey species use it for defense, producing flashes to startle attackers or release glowing particles to confuse them. Some organisms even use bioluminescence to illuminate their surroundings, sweeping the darkness with light as they search for food. Others use it as camouflage, matching the faint light from above to erase their silhouettes. These uses of light are not ornamental. They are essential adaptations that turn a challenging environment into one that can be exploited and navigated. Reproduction in the deep ocean has evolved under unique pressures. Finding a mate in a vast, sparsely populated environment is no small feat. Many species release gametes into the water, relying on chance encounters for fertilization. Others use chemical signals to attract partners, broadcasting their presence over long distances. Some species have evolved remarkable strategies to ensure reproductive success. Male anglerfish, for example, are tiny compared to females and spend their lives searching for a mate. When they find one, they attach themselves permanently, fusing with the female's body and becoming little more than a source of sperm. This extreme adaptation ensures that when the female is ready to reproduce, a mate is always available. Other species brood their young, protecting them until they are capable of surviving on their own. Some release larvae that drift with currents, spreading widely in search of new habitats. These strategies reflect the challenges of reproduction in a place where encounters are rare and opportunities fleeting. Adaptations extend even to life cycles and longevity. Many deep-sea organisms grow slowly and live for decades or centuries. This slow pace reduces energy demands and allows them to survive long periods of scarcity. It also means that they reproduce infrequently, investing heavily in each reproductive event. Some corals on the deep-sea floor are thousands of years old, their growth rings recording centuries of environmental change. Certain fish species, like the Greenland shark, may live for more than 400 years, their slow metabolisms and cold environments extending their lifespans far beyond those of their shallow water relatives. These extraordinary lifespans are not just curiosities, they're integral parts of survival strategies that emphasize endurance over rapid growth. Symbiosis is another powerful adaptation that underpins survival in the deep. Many animals partner with microbes that provide them with energy, nutrients, or other benefits. Tube worms host chemosynthetic bacteria that convert hydrogen sulfide into organic matter. Mussels and clams harbour methane oxidizing microbes in their gills. Even some fish and shrimp cultivate bioluminescent bacteria in specialized organs, using their light for communication, camouflage, or predation. These partnerships allow animals to tap into energy sources that would otherwise be unavailable, expanding the ecological possibilities of the deep. They also demonstrate the interconnectedness of life in this environment, where survival often depends on cooperation as much as competition. Adaptations are not limited to individual organisms. Entire communities have evolved strategies to thrive in the deep. Around hydrothermal vents, for example, complex ecosystems develop rapidly, supported by the chemical energy from vent fluids. When a vent dies, the community collapses, but organisms disperse to colonize new vents elsewhere. This cycle of colonization and extinction shapes the evolution of vent species, favoring traits like long-distance dispersal, rapid growth, and the ability to exploit new habitats quickly. Similar dynamics occur around whale falls and other ephemeral resources, where communities assemble, flourish, and disappear in response to changing conditions. These patterns show that adaptation in the deep is not just about surviving in place. It is about surviving change. The architecture of survival in the deep is not just biological, it is behavioral, ecological, and evolutionary. It is reflected in migration patterns that maximize energy use, in feeding strategies that exploit rare opportunities, in reproductive cycles that align with environmental cues. It is seen in the way organisms build shelters from sediment, burrow into the seafloor, or anchor themselves to rocks in the face of currents. It is evident in the way predators adjust their hunting strategies to the movements of prey, and in the way prey alter their behaviors to minimize detection. Every aspect of life in the deep is shaped by the relentless pressure of adaptation, every detail honed by the demands of an environment that allows no margin for error. Even microbes have evolved extraordinary strategies to persist in the deep. Some live within the pores of rocks, surviving on trace amounts of hydrogen or methane produced by geological reactions. Others metabolize slowly, dividing only once every 100 years, yet persisting for millions. Some form spores that can remain dormant for millennia, awakening only when conditions improve. These microbes are not just survivors, they are engineers of their environment, altering the chemistry of the seafloor, cycling nutrients, and influencing the availability of energy for other organisms. Their adaptations are subtle but profound, demonstrating that even the smallest forms of life play crucial roles in the architecture of deep-sea ecosystems. The diversity of adaptations in the deep ocean underscores a fundamental truth about life. It is not defined by the conditions it prefers, but by the conditions it can endure. Life does not require light, warmth, or abundance. It requires only the ability to capture energy, to replicate, and to adapt. The deep ocean shows us that these requirements can be met in ways we never imagined, that biology can reinvent itself to suit even the most hostile environments. It also reveals that adaptation is not static. It is a continuous process, a conversation between organisms and their environment that unfolds over millions of years. As conditions change, as vents shift, as currents alter, as tectonic plates move, life responds, evolving new solutions and discarding old ones. Understanding these adaptations has implications far beyond marine biology. They inform our search for life beyond Earth, suggesting that organisms could survive in the subsurface oceans of icy moons, or in the high-pressure environments beneath the crusts of distant planets. They offer insights into the origins of life on Earth, which may have begun in environments similar to those of the deep ocean. They also provide models for biotechnology, inspiring new materials, enzymes, and systems that function under extreme conditions. The lessons of deep-sea adaptation are not confined to the ocean floor. They reach into medicine, engineering, and the very question of what life is and where it can exist. The architecture of survival in the deep is a story of resilience and creativity, of life finding ways to endure where none should exist. It is a story written in the shapes of bodies, in the chemistry of cells, in the rhythms of behavior, and in the dynamics of ecosystems. It is a testament to the power of evolution to solve problems, to turn obstacles into opportunities, and to build complexity from adversity. And it is not a story with an end point. As we continue deeper into the abyss, we find that even the most ancient adaptations are part of a larger narrative, one that connects the life of today to the life of billions of years ago. The deep ocean is not just a frontier of biology, it is a living archive, preserving echoes of life's origins and hints of its future. Those echoes grow louder as we look beyond individual adaptations to the ancient lineage of the organisms that possess them. Many of the creatures that inhabit the deep are living fossils, their forms little changed from ancestors that swam the seas hundreds of millions of years ago. Others carry molecular traces of the earliest life on Earth, their metabolisms linked to processes that predate the rise of oxygen or the emergence of complex multicellular life. In the deep ocean, the past and present coexist, and by studying the adaptations that sustain life here, we begin to glimpse the origins of life itself and the ancient connections that tie us all to this dark and hidden world. The deep ocean is not only a place of extremes and adaptation, it is also a window into the past, a living archive of Earth's earliest history. To descend into its depths is, in many ways, to travel back in time, to glimpse conditions that existed billions of years ago, long before plants turned sunlight into sugar, before animals walked on land, before even the continents themselves had settled into their modern shapes. Many scientists believe that life on Earth began in environments much like those found today at the bottom of the ocean, dark, pressurized, mineral-rich, and powered not by sunlight, but by the chemical energy that seeps from the planet's interior. The organisms that inhabit these depths are not just survivors of an extreme environment, they are heirs to an ancient legacy, their biology still bearing the imprint of life's first chapters. The theory that life began in the deep ocean is rooted in both chemistry and geology. Early Earth was a violent and unstable place, its surface bombarded by meteors, its atmosphere lacking oxygen, and its seas laced with volcanic activity. In such an environment, surface conditions may have been too harsh for life to gain a foothold, but deep beneath the waves, hydrothermal vents offered a refuge. These vents form where seawater seeps into the Earth's crust, becomes superheated by underlying magma, and then gushes back into the ocean loaded with minerals and chemicals. The result is a dynamic environment rich in energy and chemical diversity, the very ingredients needed for life. Hydrothermal vents provide a natural setting for the kinds of chemical reactions that could give rise to life. The hot, mineral-rich fluids mix with cold seawater, creating steep gradients in temperature and chemistry. These gradients can drive the formation of complex organic molecules from simple precursors, a process known as abiotic synthesis. Minerals like iron and nickel sulfide can act as catalysts, speeding up reactions that link small molecules into larger ones. Structures called micropores within vent minerals can act as natural reactors, concentrating molecules and providing surfaces where they can interact. Over time, these reactions could produce the building blocks of life, amino acids, nucleotides, and lipids, and eventually assemble them into self-replicating systems. The earliest life forms were likely simple, consisting of molecules that could replicate and catalyze reactions. These proto-life forms would have thrived in the chemical-rich environment of hydrothermal vents, using the energy released by chemical reactions to fuel their metabolism. Even today, many vent-dwelling microbes rely on similar processes. They do not need sunlight or organic food. Instead, they use chemosynthesis, harnessing energy from reactions between chemicals like hydrogen sulfide and oxygen, or methane and sulfate. These metabolic pathways are among the most ancient on Earth, and their presence in modern microbes suggests a deep evolutionary connection to life's beginnings. The genetic evidence supports this view. The tree of life, the evolutionary relationships among all organisms, points to a common ancestor known as Luca, the last universal common ancestor. Luca is thought to have lived around 3.5 to 4 billion years ago, and many of its features align with what we see in deep-sea microbes today. It likely thrived in an environment rich in hydrogen and carbon dioxide, using chemical energy rather than sunlight. Its enzymes were adapted to high temperatures and pressures, and its metabolic pathways resembled those found in modern vent microbes. These similarities suggest that Luca, and perhaps life itself, emerged in settings much like the hydrothermal system still active at the bottom of the ocean. The deep ocean preserves not just the conditions of early Earth, but also many of its life forms. Some of the organisms that inhabit hydrothermal vents and cold seeps are direct descendants of ancient lineages that have changed little over billions of years. Archaea, one of the three main domains of life, are particularly abundant here. Many species of Archaea are extremophils, thriving in conditions that would kill most other organisms: high temperatures, high pressures, and chemical-rich environments. Their ability to metabolize inorganic compounds and tolerate extreme conditions makes them likely candidates for some of the earliest forms of life. The fact that they still dominate vent ecosystems today speaks to the continuity of life strategies over geological time. Other organisms in the deep also bear the marks of ancient ancestry. Some deep-sea sponges, for example, belong to lineages that diverged from other animals over 600 million years ago. Certain species of jellyfish and comb jellies retain body plans that have changed little since the dawn of animal life. Even some deep-sea fish, like the coelacanth, are often called living fossils, their anatomy resembling that of ancestors that swam the oceans hundreds of millions of years ago. These organisms are not unchanged. Evolution never stops, but they preserve elements of ancient biology that have been lost or transformed elsewhere. In their genes, structures, and behaviours, they carry echoes of life's earliest experiments. The chemical composition of the deep ocean itself also reflects ancient processes. The mineral-laden fluids that gush from hydrothermal vents are shaped by the same geochemical reactions that have been occurring for billions of years. The cycling of elements like carbon, nitrogen, and sulfur through deep-sea ecosystems mirrors the cycles that sustained early life. Even the structure of vent communities, with microbes forming the base of the food web and larger animals relying on them, may resemble the organisation of some of the first ecosystems on Earth. Studying these systems offers a glimpse into the past, revealing how life might have been structured before photosynthesis transformed the planet. The deep ocean's connection to Earth's early history is not limited to hydrothermal vents. Cold seeps, areas where hydrocarbons like methane and hydrogen sulfide leak from the seafloor, also host communities built on chemical energy rather than sunlight. These seeps too support chemosynthetic microbes and the animals that depend on them. They represent another possible cradle of life, one that may have existed alongside or even before hydrothermal vents. The diversity of such environments suggests that life could have originated in multiple settings, each contributing different chemical and physical conditions to the emergence of biological complexity. The parallels between deep-sea environments and early Earth have profound implications for our understanding of life's origins. They suggest that life does not require a narrow set of conditions. It does not need sunlight, oxygen, or even organic matter from the start. It needs energy, chemical gradients, and the right surfaces for reactions to occur. These conditions are not rare. They exist wherever water and rock interact under the right conditions, not just on Earth, but potentially on other worlds as well. Moons like Europa and Enceladus, with their subsurface oceans and hydrothermal activity, may host environments strikingly similar to Earth's deep-sea vents. If life could emerge here, it might emerge there too. The deep ocean also teaches us about the resilience of life. Many vent communities are ephemeral, lasting only as long as the vent remains active. When it dies, the community collapses, and organisms must disperse to find new vents. This cycle of colonization and extinction mirrors the challenges life may have faced in its early days, when hydrothermal systems were unstable and transient. The ability of vent organisms to disperse, adapt, and exploit new habitats reflects strategies that may have been critical to life's persistence billions of years ago. It also demonstrates how life can thrive in environments that are dynamic and unpredictable, not just stable and benign. Even the biochemistry of deep-sea organisms offers clues to life's ancient origins. Many vent microbes use pathways that are considered primitive, relying on reactions that require only simple inorganic compounds. Some fix carbon using the acetyl-CoA pathway, one of the most ancient metabolic routes known. Others generate energy through the reduction of sulfate or the oxidation of hydrogen, processes that would have been possible on the early Earth before oxygen became abundant. These pathways are not relics. They are still effective strategies for life in the deep. Their persistence shows that the solutions life discovered billions of years ago remain relevant today. The genetic diversity of deep-sea microbes also hints at their ancient lineage. Many possess genes and proteins that are deeply conserved across all domains of life, suggesting that they were present in Luca or even earlier ancestors. Others carry unique adaptations that have evolved in response to the deep-sea environment, but still bear traces of ancient origins. Studying these genes can reveal not only how modern organisms function, but also how life itself evolved from simple molecules into complex self-sustaining systems. The deep ocean's role as a time capsule extends beyond biology. The sediments that accumulate on the seafloor record Earth's history in layers of silt and clay. Embedded within them are microfossils, chemical signatures, and isotopic ratios that trace the evolution of life and the planet itself. These records show how microbial communities responded to shifts in ocean chemistry, how ecosystems changed as oxygen rose and fell, and how life adapted to mass extinctions and climate fluctuations. They provide a continuous archive stretching back hundreds of millions of years, one that complements the story told by rocks on land and fossils in shallow seas. The connection between the deep ocean and life's origins is not merely academic, it shapes how we think about the future. As we explore the solar system and beyond, the lessons of the deep guide our search for life. They tell us where to look, in places where water, rock, and energy interact. They inform the kinds of instruments we design, the experiments we conduct, and the questions we ask. They remind us that life is not limited to the conditions we know, but can emerge and thrive in environments that seem alien to us. And they expand our understanding of what it means for a planet to be habitable. The deep ocean also challenges our assumptions about life's uniqueness. If life could arise here in darkness and pressure, without sunlight or oxygen, then it may not be rare in the universe. It may be a common outcome of the right conditions, emerging wherever water and energy coexist. This possibility changes how we think about our place in the cosmos. It suggests that the story of life on Earth may not be an isolated event, but part of a broader pattern, one that could be playing out on countless worlds. Even as it connects us to the distant past, the deep ocean reminds us of how much we still do not know. Many of its inhabitants remain undiscovered. Many of its processes are poorly understood. The chemistry of its vents and seeps, the dynamics of its microbial communities, the details of its evolutionary history, all are subjects of ongoing research. Each new expedition reveals surprises, from novel metabolic pathways to previously unknown forms of life. These discoveries not only enrich our understanding of the deep, but also reshape our theories about life's origins and potential. The story of the deep is not just about the past or the possibility of life elsewhere. It is also about continuity, the processes that sustain life at hydrothermal vents today. The chemical reactions, the microbial metabolisms, the ecological interactions are not fundamentally different from those that may have sustained the first living systems. They have been refined and elaborated over billions of years, but their essence remains the same. In this sense, the deep ocean is not just a relic of the past. It is a living continuation of it, a bridge between the world that was and the world that is. This continuity extends to the rest of life on Earth. We are products of the same evolutionary processes that shape the microbes at hydrothermal vents. The metabolic pathways in our cells, the structure of our proteins, even the genetic code itself, all trace back to ancestors that may have lived in environments like those at the bottom of the ocean. When we study the deep, we are not just exploring a distant and alien realm. We are exploring our own origins, tracing the threads that connect us to the first living things. The deep ocean also offers lessons about resilience and adaptation that are relevant today. Life here has persisted through dramatic changes in Earth's climate, chemistry, and geology. It has survived asteroid impacts, ice ages, and mass extinctions. Its ability to endure offers hope that life, once begun, is hard to extinguish. This resilience is not just a feature of microbes or extremophiles, it is a property of life itself, a testament to its capacity to adapt and persist in the face of change. Yet the deep is not immune to human influence. Climate change, pollution, and deep-sea mining all threaten to disrupt the delicate balance of its ecosystems. These threats are not just environmental concerns, they are challenges to our understanding of life's continuity. The same processes that shaped life's origins and sustained it for billions of years could be altered in decades by human activity. Protecting the deep is not just about preserving biodiversity. It is about safeguarding one of the most fundamental stories on our planet, the story of life itself. The echoes of that story resonate beyond Earth, shaping our exploration of the cosmos. If life exists elsewhere, it may not resemble the familiar forms we know. It may be microbial, slow-growing, and chemically driven, like the organisms that thrive at hydrothermal vents. It may rely on chemosynthesis rather than photosynthesis, on mineral surfaces rather than sunlight. By studying the deep, we prepare ourselves to recognize life in unfamiliar guises, to see the universal patterns beneath the surface differences. As we continue deeper into this world, the sense of connection becomes impossible to ignore. The deep ocean is not a separate realm, sealed off from the rest of Earth's history. It is a thread that runs through that history from the very beginning, linking the first replicating molecules to the complex biosphere that now spans the planet. It is a reminder that life's story is not confined to the surface or to the light. It began in darkness, in water and rock and chemical energy, and that is where much of it still unfolds, and it suggests that the future of life, here and elsewhere, may continue to be written in places like this, where the conditions that gave rise to life still exist. That sense of continuity carries forward as we shift our gaze from the past to the present and future. The deep ocean, once thought of as remote and inaccessible, is increasingly within reach of human exploration. With every new descent, we uncover more of its secrets, and with each discovery, our picture of this vast hidden realm becomes clearer. Yet even as we learn more, we are reminded of how much remains unseen, and how much lies ahead as we push further into this alien world. The exploration of the deep is not just a journey into Earth's history, it is a journey into its future, and into the possibilities that await us as we continue to probe the unknown. For most of human history, the deep ocean was a realm of mystery and imagination, a place feared, revered, and rarely questioned. People stood on shorelines and gazed out at the sea without knowing what lay beneath its surface. It was often described in myths as a domain of monsters, gods, and unfathomable forces, a hidden world beyond human reach. The surface waters were familiar. Sailors could navigate them, fishers could harvest them, and coastal communities could rely on them. But the depths themselves were unknowable. Even the most adventurous explorers of the ancient world, with all their courage and curiosity, were limited by the technology of their time. They could sail across the seas, but they could not descend into them. The deep remained a place of speculation rather than observation. The first attempts to probe the depths were crude but ambitious. Ancient philosophers and scientists debated the nature of the ocean floor, imagining vast chasms or solid, featureless plains. In the 3rd century BCE, Aristotle speculated about the creatures that might live in deep waters, while the Roman naturalist Pliny the Elder described bizarre sea monsters that may have been inspired by fleeting glimpses of deep-dwelling species washed ashore. These early ideas were based on imagination more than evidence, but they reflected a deep human desire to understand what lay hidden beneath the waves. Practical efforts to explore the deep began in earnest during the Age of Exploration, when European sailors expanded their voyages across the globe. As ships ventured farther from land, sailors began measuring ocean depth by lowering weighted lines into the water. These sounding lines provided the first rough estimates of depth in coastal waters and along trade routes, but they were of little use in the open ocean. Beyond a few hundred meters, the lines became impractical, too heavy to retrieve, too prone to drifting in currents, and too easily broken. The deep ocean remained beyond reach, a vast and mysterious void. By the 19th century, curiosity about the deep ocean had grown alongside advances in science and technology. The Industrial Revolution brought new tools and new questions. Naturalists began to wonder whether life could exist at great depths, where sunlight did not penetrate. Some believed the deep sea was a lifeless desert, too cold, too dark, and too pressurized to support life. Others suspected that unknown creatures lurk there, adapted to conditions beyond human imagination. These debates set the stage for one of the most important scientific expeditions in history. In 1872, the British Royal Navy launched HMS Challenger on a mission that would transform our understanding of the deep ocean. Over the course of nearly 4 years, the Challenger circumnavigated the globe, covering more than 68,000 nautical miles. Its crew lowered weighted nets, thermometers, and sampling devices into the depths, measuring temperature, salinity, and depth at hundreds of locations. They dredged the seafloor, collecting sediments and organisms from as deep as 8,200 meters. The results were revolutionary. Far from being lifeless, the deep sea teemed with strange and diverse life forms. The expedition documented over 4,000 new species, mapped major features of the ocean floor, and gathered data that laid the foundations of modern oceanography. The Challenger expedition proved that science could reach into the deep, and that the mysteries of the abyss were not beyond human understanding. The success of the Challenger inspired further exploration, but progress was slow. Sampling methods remained limited, and direct observation was impossible. Scientists could study what they hauled up in nets or dredges, but they could not see the deep ocean as it really was. That began to change in the early 20th century with the development of deep-diving submersibles. In 1930, American naturalist William Beebe and engineer Otis Barton descended more than 400 meters off the coast of Bermuda in a steel sphere called the bathysphere. Suspended by a cable from a ship above, the bathysphere had no means of propulsion or control, but it offered something no one had ever experienced before, a direct view of the deep ocean. Through small portholes, Beebe and Barton observed fish, jellyfish, and other creatures that had never been seen alive. Their observations, though limited by the technology of the time, offered the first glimpses of life in the deep as it existed in its natural habitat. The bathysphere's achievements captured the public imagination and demonstrated the potential of human exploration beneath the waves. But its limitations were obvious. It could not move under its own power, its occupants had no control over their depth or position, and its cable restricted how deep it could go. True exploration of the deep would require vehicles that could descend freely and return safely, a challenge that would take decades to overcome. The breakthrough came in the 1950s and 1960s with the development of bathyscarfs, self-propelled deep-diving vessels designed to withstand the immense pressures of the deep ocean. The most famous of these was the Trieste, built by Swiss scientist Auguste Piccard and later acquired by the US Navy. In 1960, Piccard's son Jacques and US Navy Lieutenant Don Walsh piloted the Trieste to the deepest known point on Earth, the Challenger deep in the Mariana Trench, nearly 11,000 meters below the surface. Their descent took nearly 5 hours, and for 20 minutes at the bottom, they observed a barren, sediment-covered seafloor. The Trieste's journey proved that humans could reach even the most extreme depths and return alive. It was a milestone in exploration, one that opened the door to future missions. In the decades that followed, deep-sea exploration expanded rapidly. Advances in materials, science, engineering, and robotics made it possible to build submersibles that were safer, more maneuverable, and capable of carrying sophisticated scientific instruments. Manned submersibles like Alvin, launched in 1964, allowed scientists to explore the deep firsthand. Alvin became famous in 1977 when it carried researchers to the Galapagos Rift, where they discovered hydrothermal vents and the rich ecosystems surrounding them. This discovery was one of the most significant in the history of marine science, revealing that life could thrive without sunlight, relying instead on chemical energy from the Earth's interior. It revolutionized our understanding of biology and strengthened the idea that similar ecosystems might exist elsewhere in the solar system. While manned submersibles offered unparalleled opportunities for direct observation, they were expensive and limited by the endurance of their crews. The development of remotely operated vehicles, ROVs, and autonomous underwater vehicles, AUVs, in the late 20th century transformed deep-sea exploration again. ROVs could dive deeper and stay underwater longer than manned submersibles, controlled from the surface by operators using cameras and robotic arms. AUVs could operate without human intervention, mapping the seafloor, collecting samples, and conducting experiments over long periods. These technologies dramatically increased the scope and scale of exploration, allowing scientists to survey vast areas of the deep ocean and study its ecosystems in unprecedented detail. Each new generation of technology has brought new discoveries. In the 1980s and 1990s, ROVs revealed the diversity of life around cold seeps and whale falls. They documented towering methane ice structures, colonies of tube worms and clams, and strange communities built around decaying carcasses. They discovered new species with astonishing adaptations, from fish with antifreeze proteins in their blood to microbes that metabolize methane and sulfur. In the 2000s and beyond, AUVs mapped the seafloor with centimetre-scale precision, revealing volcanic ridges, deep canyons, and massive landslides. Fibre optic cables transmitted real-time data from deep-sea observatories, allowing scientists to monitor ecosystems continuously for months or years. Each advance has peeled back another layer of mystery, transforming our understanding of the deep from speculation to science. Deep-sea exploration has also expanded beyond scientific research. Governments and private companies have begun exploring the deep for resources, from minerals and metals to oil and gas. Deep-sea mining in particular has sparked both excitement and concern. Nodules rich in manganese, cobalt and rare earth elements lie scattered across vast swathes of the seafloor, and hydrothermal vent deposits contain valuable metals like copper and gold. These resources could play a crucial role in future technologies, but their extraction poses significant risks to fragile deep-sea ecosystems. The debate over how to balance exploration and conservation is ongoing, and it highlights the broader implications of our growing ability to access the deep. The deep ocean has also become a stage for international cooperation and competition. Nations have launched ambitious programs to map and study their exclusive economic zones, while global initiatives aim to create comprehensive maps of the entire seafloor. Projects like Seabed 2030, launched in 2017, seek to map the entire ocean floor by the end of this decade, combining data from ships, submersibles, and satellites. At the same time, deep-sea exploration has become a frontier for prestige and influence, with nations competing to plant flags on the seafloor, claim resource rights, and demonstrate technological prowess. These geopolitical dimensions add another layer of complexity to the story of human engagement with the deep. Public fascination with the deep ocean has grown alongside these scientific and political developments. Documentaries, books, and exhibitions have brought its wonders to audiences around the world. Images of glowing creatures, alien landscapes, and strange otherworldly ecosystems have captivated imaginations and inspired new generations of scientists and explorers. Popular culture has also embraced the deep, with films and stories that blend scientific discovery with adventure and mystery. This cultural dimension is not just entertainment, it plays a vital role in building support for exploration and conservation, reminding people that the deep ocean, though distant and dark, is part of our shared planet. Despite all the progress made, vast portions of the deep ocean remain unexplored. It covers more than 60% of Earth's surface, yet we have mapped less than a quarter of its seafloor in detail. Much of it has never been seen by human eyes or cameras. Countless species remain undiscovered, countless geological features uncharted. The deep is still, in many ways, the last frontier on Earth, a vast and mostly untouched wilderness that challenges our technology, our imagination, and our understanding of life. Exploration continues to evolve, driven by advances in robotics, artificial intelligence, and materials science. New generations of AUVs can operate for months at a time, covering thousands of kilometers and collecting terabytes of data. Swarms of small, inexpensive robots can work together to map large areas or monitor dynamic processes. Next-generation sensors can detect trace chemicals, measure microbial activity, and capture high-resolution images in near-total darkness. Some researchers are even exploring the use of soft robotics inspired by deep-sea animals, designed to operate gently and efficiently in delicate ecosystems. These innovations promise to accelerate discovery, revealing aspects of the deep that have remained hidden until now. Exploration is not only about technology, it is also about perspective. Each dive, each sample, each new image challenges our assumptions and expands our understanding. It forces us to confront the complexity and diversity of life, the power and dynamism of geological processes, and the profound interconnectedness of Earth's systems. It reminds us that the deep ocean is not a static alien world, but an integral part of the planet's biosphere, influencing everything from climate to nutrient cycles. It also reminds us that exploration is not an end in itself, but a means of deepening our relationship with the planet we inhabit. The history of deep-sea exploration is a story of persistence and ingenuity. It is a story of ropes and weights giving way to steel spheres, of fragile submersibles descending into darkness, of robotic explorers mapping landscapes no human has ever seen. It is a story of questions that once seemed unanswerable, becoming sources of knowledge, of mysteries becoming ecosystems, of myths giving way to science. It is also a story still being written. Each new descent adds a line, each new discovery a chapter, and as our tools become more powerful and our reach extends deeper, the pace of that story accelerates. The journey into the deep has also reshaped how we think about ourselves. It has shown us that Earth is not just a planet of land and sky, but a water world, its deepest places shaping its climate, chemistry, and biology in ways we're only beginning to grasp. It has revealed that life is more adaptable, more inventive, and more widespread than we imagined. It has challenged our ideas about where life can exist and how it can survive. And it has reminded us that the unknown is not something to fear, but something to explore. The story of exploration does not end here. The deep ocean is still revealing its secrets, still surprising us, still changing how we think about life and the planet. And as we look to the future, we see that the greatest discoveries may still lie ahead, not just in what we find, but in how those findings reshape our relationship with the world. The deep has always been a place of mystery, but it is also a place of connection, linking past and present, Earth and cosmos, science and imagination. As we continue to explore, we're not just learning about the deep ocean. We're learning about ourselves and the possibilities that lie beyond the horizon of our current knowledge. That journey carries us forward, beyond history and into the unknown. The deep is not static. It is a place of constant change, shaped by forces that operate over timescales far longer than human lives. and just as our exploration of it has evolved, so too will the ways we interact with it in the future. The question is not whether we will continue to explore, but how, and what we will discover as we push deeper still. And beyond that, as our tools and ambitions grow, what unseen worlds might still await us in the darkness below? The deep ocean has always existed beyond the limits of human reach, a world that carried on unchanged and unseen while civilizations rose and fell above it. For centuries it remained hidden, its landscapes unmapped, its inhabitants unknown, and its processes beyond comprehension. Even now, after decades of exploration and discovery, most of it remains mysterious. We have mapped more of the surfaces of Mars and the Moon than we have of our own seafloor. We have catalogued only a fraction of the species that live in the deep, and our understanding of how they interact, evolve and shape the planet is still incomplete. As technology advances and our ambitions grow, the question is no longer whether we will continue to explore the abyss, but what the future holds as we do. What lies ahead for humanity's relationship with this vast hidden realm, and what secrets might still be waiting in the darkness below? One of the most immediate frontiers in deep-sea science is simply to know what is there. Despite centuries of study, the majority of the deep ocean remains unmapped. Vast regions of the seafloor have never been surveyed with modern instruments, and many that have were mapped only in rough detail. This lack of knowledge is not just a matter of curiosity. The topography of the seafloor influences ocean circulation, climate, and even weather. It shapes the distribution of life and the flow of nutrients. It holds clues to the Earth's geological past and to the processes that continue to shape it. Completing the map of the ocean floor is one of the most ambitious scientific projects of our time, and efforts like the Seabed 2030 initiative aim to achieve that goal within the next decade. Using a combination of ship-based sonar, autonomous underwater vehicles and satellite measurements, scientists hope to create a complete, high-resolution map of the seafloor. Such a map will not only reveal features we have never seen, mountains taller than Everest, canyons deeper than the Grand Canyon, plains that stretch for thousands of kilometers, but also provide the foundation for future exploration and research. Beyond mapping, the deep ocean still holds countless undiscovered species. Scientists estimate that more than 90% of deep-sea life has yet to be described. Many of these species are likely small and microscopic, part of the microbial communities that form the base of deep-sea ecosystems. Others may be larger and more conspicuous: fish, squid, worms, and crustaceans with adaptations unlike anything we have seen before. Each new discovery expands our understanding of evolution and ecology, revealing new ways that life can survive and thrive under extreme conditions. Many of these species may also hold potential benefits for humans. Deep-sea organisms produce unique molecules to cope with pressure, temperature, and chemical stress. These compounds could inspire new medicines, materials, and technologies. The more we explore, the more we learn that the deep is not just a realm of scientific curiosity, but a source of innovation and possibility. Understanding how deep-sea ecosystems function is another frontier. We know that life here is shaped by scarcity, pressure, and darkness, but the details of how energy flows through these ecosystems are still being uncovered. How do microbial communities assemble and interact? How do chemical gradients shape the distribution of life? How do deep-sea food webs respond to changes in climate, currents, and nutrient supply? These questions are not just academic. The deep ocean plays a critical role in regulating Earth's climate and cycling nutrients. It stores vast amounts of carbon, helps regulate the planet's temperature, and influences the productivity of surface waters. Understanding these processes is essential, not only for basic science, but also for predicting how the planet will respond to human activities. Climate change is already altering the deep ocean in ways we are only beginning to understand. As surface temperatures rise and ice melts, ocean circulation patterns are shifting, affecting the delivery of oxygen and nutrients to the deep. Warmer water holds less oxygen, and as oxygen levels decline, some deep-sea habitats may become uninhabitable for certain species. Changes in the amount and composition of organic matter sinking from the surface could reshape deep-sea food webs, favouring some organisms over others and altering ecosystem dynamics. Ocean acidification, driven by increased carbon dioxide, may also affect deep-sea organisms, particularly those that build shells or skeletons from calcium carbonate. These changes are likely to unfold slowly, but their impacts could be profound, reshaping the deep ocean in ways we cannot yet predict. Human activity is not only altering the deep indirectly through climate change, but also directly through exploration and exploitation. Deep-sea mining is one of the most contentious issues on the horizon. Rich deposits of minerals like manganese, cobalt and nickel lie scattered across the seafloor, along with valuable sulfide deposits at hydrothermal vents. These resources are critical for technologies like batteries, electronics, and renewable energy systems. As demand for them grows, so does interest in mining the deep. Yet the potential impacts of such activities are enormous. Mining could destroy fragile habitats that have taken millennia to form, release plumes of sediment that smother life, and disrupt ecological processes that we barely understand. It could also eliminate species before we even discover them. The debate over deep-sea mining pits economic interests against environmental concerns, and its outcome will shape the future of the abyss. Conservation of the deep ocean is still in its infancy. Most of it lies beyond national jurisdictions, in international waters that are governed by a patchwork of treaties and regulations. Efforts are underway to create protected areas in the deep, but these face political, legal and logistical challenges. Establishing effective conservation measures requires not only scientific knowledge, but also international cooperation and political will. It also requires a shift in how we think about the deep ocean, not as an inexhaustible frontier to be exploited, but as a vital part of Earth's life support system, one that must be managed and protected for the benefit of all. The future of exploration itself is likely to be transformed by advances in technology. Autonomous underwater vehicles are becoming more capable, able to operate for months or even years, navigate complex terrain, and collect enormous amounts of data. Swarms of small, inexpensive robots could map vast areas of the seafloor, monitor ecosystems, and respond to changes in real time. Artificial intelligence will play a growing role, analysing data, guiding exploration, and even making decisions autonomously. Improvements in communication technology will allow us to transmit data from the deep in real time, enabling more responsive and collaborative research. Even human exploration may take new forms, with advances in submersible design allowing for deeper, longer and safer dives. These technologies will not only expand our ability to explore, but also change how we do science. Continuous monitoring of deep-sea environments could reveal patterns and processes that have so far eluded us, from seasonal changes in microbial activity to long-term shifts in ecosystem structure. Real-time data could improve our ability to predict events like undersea volcanic eruptions, methane releases, or ecosystem collapses. The integration of biological, chemical, geological, and physical data could provide a more complete picture of how the deep ocean functions as part of the Earth system. These insights will not only deepen our understanding of the deep, but also improve our ability to manage and protect it. The future of the abyss also extends beyond Earth. The environments we find in the deep ocean, cold, dark, high pressure, and rich in chemical energy, are likely analogues for conditions on other worlds. Moons like Europa and Enceladus are believed to harbour subsurface oceans beneath their icy crusts, potentially warmed by hydrothermal activity. The lessons we learn from exploring Earth's deep ocean will inform how we search for life in these alien seas. The technologies we develop for operating in extreme conditions here could be adapted for missions beyond Earth, and the organisms we discover, their metabolisms, adaptations and survival strategies may provide clues about what life might look like elsewhere, the prospect of exploring extraterrestrial oceans raises profound questions about our relationship with the deep on our own planet. If we are to search for life on distant worlds, we must first understand life in the most remote and challenging environments here. The deep ocean is our best training ground for such exploration. It is where we learn how to operate in darkness, how to detect life without sunlight, how to interpret chemical signals, and how to work in conditions of immense pressure. It is also where we confront the limits of our knowledge and technology, pushing them further with each descent. Even as we look outward, the deep ocean challenges us to look inward, to consider how we interact with our own planet and how we shape its future. The deep is not a separate world. It is intimately connected to the rest of Earth's systems. It influences climate, supports biodiversity, and sustains human life in ways we are only beginning to understand. Its future is tied to ours, and the choices we make will determine not only what we find there, but also what remains. Will we explore responsibly, balancing curiosity with caution, discovery with stewardship? Or will we repeat the mistakes of the past, exploiting before we understand, damaging before we know the consequences? The answers to these questions will depend on more than science and technology. They will depend on values, policies, and collective decisions. They will require new forms of governance that recognize the deep ocean as a shared resource and a shared responsibility. They will require collaboration across nations, disciplines, and sectors. And they will require a deeper public understanding of the deep, an appreciation of its importance, and a commitment to its protection. Without these, even the most advanced technologies will not be enough to safeguard the abyss. The deep also invites us to rethink our perspective on time. Human lifespans and political cycles are measured in decades, but the processes that shape the deep ocean unfold over centuries, millennia, or longer. Currents shift slowly, sediments accumulate over eons, ecosystems evolve over geological timescales. Our exploration of the deep is only just beginning, and our impact on it will be felt long after we're gone. Thinking about the future of the abyss requires us to think on longer timescales, to imagine not just the next decade or century, but the next 1,000 years. It requires us to ask not just what we can learn or gain, but what kind of legacy we want to leave. There is reason for hope. The story of deep-sea exploration so far is one of discovery, wonder, and increasing responsibility. We have gone from fearing the deep as a realm of monsters to studying it as a dynamic, living system. We have gone from crude soundings to high-resolution maps, from speculative myths to detailed observations. Each step has expanded our knowledge and deepened our sense of connection to this hidden world. There is every reason to believe that the next steps will do the same. With each new technology, each new expedition, each new insight, we move closer to understanding the deep in all its complexity. Yet the greatest discoveries may still be the ones we cannot yet imagine. They may lie in species that challenge our definitions of life, in ecosystems that rewrite our understanding of biology, in geological processes that reshape our view of the planet. They may lie in unexpected connections between the deep and the surface, between the ocean and the atmosphere, between Earth and other worlds. They may lie in the answers to questions we have not yet thought to ask. The abyss has always held surprises, and there is no reason to think that will change. The future of the abyss is, in many ways, a mirror of the future of humanity. It will reflect our curiosity, our ingenuity, and our capacity for wonder. It will also reflect our choices, our priorities, and our willingness to act as stewards rather than conquerors. The deep will endure long after we are gone, but what it looks like, what lives there, what secrets it holds, what stories it tells, will be shaped by what we do now. It is a future we are already writing, one decision, one expedition, one discovery at a time. And as we look ahead, we are reminded that exploration is not just about reaching new places, it is about deepening our understanding of the places we already know. The deep ocean is part of our planet, part of our story, part of who we are. Its future is tied to ours, and its mysteries are, in a very real sense, our own. As we continue into the unknown, we do not leave the past behind. We carry it with us, woven into every question we ask and every answer we find. The abyss is not just a destination, it is a journey, one that will continue as long as there are questions to ask, depths to explore, and unseen worlds waiting in the dark. And even beyond those depths, beyond the limits of our maps and machines, there will always be something more. For the deep ocean is not a finite realm with edges and endings. It is a process, a story, an unfolding. Its future is not something to be reached, but something to be lived, explored, and shaped. And as we follow that story deeper, we find ourselves not at the end of anything, but at the threshold of what comes next, the point where exploration becomes understanding, and understanding becomes connection. At the deepest points of the ocean, where light has never reached and pressure would crush steel, the water is still. It is not motionless. Currents flow, sediments drift, and chemical gradients shift. But the pace is so slow, and the changes so gradual that it feels like the closest thing our planet has to silence. This silence is not empty. It is alive with bacteria that metabolize the minerals seeping from the Earth's crust, with worms that sift through the sediment, with fish that drift like shadows through the darkness. It is alive with chemical reactions that have been running for billions of years, with geological processes that shape the crust beneath us, with cycles of carbon and nutrients that connect the deep ocean to the surface world. To stand on the seafloor of the abyss, or even to imagine it clearly, is to feel the pulse of the planet at its most fundamental level, slow, patient, and relentless. This is the heart of the Earth, not in the literal sense of molten iron and heat, but in the sense of depth, stability, and endurance. The deep ocean is as old as the planet itself. It formed as water collected on the cooling crust of the young Earth, and it has persisted through every chapter of our planet's story. It has witnessed continents drift and mountains rise, species appear and vanish, climates shift from icehouse to greenhouse and back again. It has endured asteroid impacts, volcanic cataclysms, and mass extinctions. Through it all, it has remained, vast and dark and vital, shaping the surface world in ways that most of us never see or think about. Every breath we take, every cloud that forms, every ecosystem on land or in shallow water is connected in some way to the deep ocean. It is not a separate realm. It is the foundation of the world we live in. Standing back and looking at the deep ocean this way changes how we see everything above it. It reminds us that the planet is not just a thin layer of air and land where we build our cities and grow our food. Most of Earth is water, and most of that water is deep. The biosphere is not confined to the surface. It extends into the darkness for kilometers below, into places where sunlight has never shone, and where life thrives on chemical energy rather than light. The processes that regulate our climate, recycle our nutrients, and sustain our atmosphere are not limited to forests, rivers, and coral reefs. They are rooted in the slow workings of the deep, in the microbes that fix carbon at hydrothermal vents, in the sediments that bury organic matter, in the circulation of cold, dense water that moves heat around the globe. Our planet is shaped from below as much as from above. It is easy to forget this because the deep ocean is invisible to us. We live our lives in the thin film of the surface, rarely thinking about the kilometers of water beneath us. Even scientists who devote their careers to studying the ocean spend more time looking at data and samples than at the deep itself. The handful of people who have descended to its greatest depths could fit into a single room. Yet the deep is always there, influencing everything we do. It is the sink that absorbs the heat trapped by greenhouse gases. It is the reservoir that holds most of Earth's carbon. It is the engine that drives global circulation patterns and stabilizes the climate. Its microbes produce gases that shape the atmosphere. Its sediments preserve the record of the planet's history. Its ecosystems recycle the nutrients that feed life in the sunlit shallows. Whether we think about it or not, the deep ocean is part of our lives every moment. Recognizing this changes not just our understanding, but our relationship with the planet. It shifts our perspective from one of separation to one of connection. The deep is not a distant alien place. It is part of the same world we inhabit, part of the same system that sustains us. Its health and stability are tied to ours. When we burn fossil fuels and warm the planet, the deep ocean absorbs much of the excess heat, buffering us from the full consequences of our actions. When we alter the chemistry of the atmosphere, the deep responds, storing carbon and changing its circulation patterns. When we pollute the surface waters, the deep eventually receives that pollution, carrying its imprint for centuries. Every action we take reverberates downward, and every process in the deep reverberates upward. The boundaries we imagine, between land and sea, surface and depth, human and natural, dissolve when we see the Earth as a whole. This interconnectedness also reshapes how we think about the future. The deep ocean is not static, it is dynamic and responsive, but it operates on timescales far longer than those we're used to. A shift in circulation can take centuries to complete. The burial of carbon in sediments unfolds over millennia. The formation of mineral deposits takes millions of years. The decisions we make now about climate, pollution, resource extraction will shape the deep ocean not just for our lifetimes but for generations far beyond. They will affect the composition of its waters, the structure of its ecosystems, the stability of its currents, and those changes in turn will shape the world above. Understanding this forces us to think differently about responsibility. It is not enough to consider the immediate effects of our actions. We must also consider the long echoes they will send into the depths and the future. This sense of responsibility is not just a burden, it is an invitation. The deep ocean offers us opportunities as profound as its challenges. It holds resources that could support renewable energy technologies, from metals for batteries to rare earth elements for electronics. It harbours organisms with biochemical tools that could transform medicine, agriculture and industry. It contains geological records that could help us understand the planet's past and predict its future. It offers insights into life's origins and clues about the possibility of life elsewhere. Exploring it is not just an act of curiosity. It is a way of expanding the boundaries of what we know and what we can do. It is a way of discovering solutions to problems that affect us all. But those opportunities must be approached with caution and humility. The deep ocean is not an empty space waiting to be used. It is a complex, interconnected system, one that operates on scales and timescales far beyond our usual experience. Its ecosystems are fragile, its processes slow, its recovery from disturbance measured not in years, but in centuries. Once damaged, some deep-sea environments may never return to their original state. The challenge for humanity is to find a balance, to explore and learn and benefit from the deep without destroying what makes it valuable in the first place. This balance is not easy, but it is essential if we are to be more than just temporary visitors in the deep story. Exploring the deep also changes us in ways that go beyond science or technology. It expands our sense of scale. It reminds us that the world is larger and more complex than our daily lives suggest. It challenges our assumptions about where life can exist and how it can survive. It humbles us with its vastness and its indifference. It invites us to think not just in terms of human lifetimes or human concerns, but in terms of planetary processes and deep time. It places us within a story that began billions of years before we arrived and will continue billions of years after we're gone. This shift in perspective is one of the most profound gifts of exploration. It reminds us that we are part of something much larger than ourselves. It also deepens our sense of wonder. Even after decades of exploration, the deep ocean continues to surprise us. New species are discovered on almost every expedition. Strange geological features are revealed by each new map. Unfamiliar chemical processes and unexpected ecological interactions emerge with every new study. The deep is a constant reminder that the world is not fully known, that mystery still exists, and that discovery is still possible. In a time when so much of the planet has been mapped, measured and transformed, the deep ocean remains a frontier, not just a place on a map, but a realm of questions we have not yet thought to ask. That sense of wonder has practical consequences. It inspires the next generation of scientists, engineers and explorers. It drives innovation and creativity. It fosters collaboration across disciplines and nations. It builds public support for science and conservation. Wonder is not a luxury. It is a catalyst. It is what pushes us to look beyond what we know and to imagine what might be possible. The deep ocean provides that wonder in abundance. Its landscapes are as dramatic as any on land. Its life forms as strange and beautiful as anything in the cosmos. Its processes as fundamental as the forces that shape the stars. To engage with it is to engage with the planet at its most elemental level. This engagement is not just for scientists or explorers. The deep ocean affects everyone. It influences the climate that shapes our weather and agriculture. It supports the fisheries that feed billions of people. It stores the carbon that keeps our atmosphere stable. It generates the oxygen we breathe. It shapes the coastlines where we live and the storms that reach them. Decisions about how we study, protect and use the deep are decisions about the future of humanity itself. They are decisions about the kind of planet we will live on and the kind of legacy we will leave behind. The deep ocean also reminds us that our planet is rare and precious. In a universe full of worlds, few are known to have liquid water, stable climates, and life. Fewer still are known to have deep oceans teeming with complex ecosystems. Earth's deep ocean is not just a feature of the planet, it is one of its defining characteristics, one of the reasons life exists here at all. Its circulation helps stabilize the climate, its chemistry helps sustain the biosphere, its ecosystems recycle the elements needed for life. Without it, the Earth would be a different world, colder, less stable, perhaps lifeless. To understand the deep is to understand what makes our planet unique. That understanding extends beyond Earth. The environments we find in the deep ocean are among the best analogues for conditions on other worlds. They show us that life can exist without sunlight, powered by chemistry alone. They show us that it can adapt to extreme pressure, cold, and darkness. They show us that ecosystems can form around sources of energy far removed from the surface. These lessons guide our search for life elsewhere. They shape how we design missions to icy moons and distant planets. They influence how we interpret the data we receive from space. They remind us that the conditions that gave rise to life here may not be unique, and that the universe may hold many more worlds where life has taken root in the dark. The deep ocean is not just a part of Earth's story, it is a part of the universe's story. A reminder of the common processes that shape planets and give rise to life. It connects the water that falls as rain to the water that circulates beneath the crust, the microbes that metabolize minerals to the stars that forge those elements, the ecosystems that flourish in darkness to the cosmic forces that made them possible. It is a thread that runs through everything, binding the smallest cell to the largest galaxy, the present moment to the deepest past and the farthest future. To engage with the deep ocean, then, is to engage with something far larger than ourselves. It is to place ourselves within the broader context of the planet and the cosmos. It is to recognize that we are not separate from the deep but part of it, that the atoms in our bodies once cycled through its waters, that the air we breathe is shaped by its chemistry, that the climate we depend on is stabilized by its currents. It is to see that the boundary between the surface and the depth is not a wall but a membrane through which matter, energy and life constantly flow, And perhaps most importantly, it is to understand that the story of the deep is not finished. It is still unfolding, shaped by forces both natural and human. It is shaped by the slow drift of tectonic plates and the rapid rise of technology, by the steady accumulation of sediments and the sudden impact of policy decisions. It is shaped by our curiosity, our creativity, and our capacity for care. We are now part of that story, for better or worse. The choices we make will echo through the deep for centuries to come. The question is what those echoes will say. The answer is not predetermined. It depends on us, on how we explore, how we learn, how we act. It depends on whether we see the deep as a resource to be exploited or a system to be understood, as a frontier to be conquered or a partner to be respected. It depends on whether we treat its silence as emptiness or as a voice worth listening to. It depends on whether we remember that in exploring the deep, we're also exploring ourselves, our place in the world, our impact on it, and our responsibility to it. The stillness of the deep is deceptive. Beneath its calm surface, everything is in motion, water circulating, chemicals reacting, life evolving. It is a place of constant change, but the pace of that change is measured in centuries and millennia, not days and years. In that slow, steady motion lies a lesson. Not everything must happen quickly to matter. Not everything must be visible to be real. Some of the most important processes in the deep ocean, in the planet, in ourselves, unfold quietly, out of sight, shaping the world in ways we rarely notice but could not live without. In that sense, the deep ocean is not just a place. It is a teacher. It teaches patience and perspective, humility and curiosity. It teaches that the most powerful forces are often the least visible, that the most profound changes happen slowly, and that the most important connections are the ones we cannot see. It teaches us that the world is deeper, richer, and more interconnected than we imagine, and it invites us to keep learning, to keep exploring, to keep reaching beyond what we know. In the end, the deep ocean is not just part of our planet, it is part of our story, a story that began long before us and will continue long after. It is a story written in darkness and pressure, in chemistry and time, in life that thrives where none should. It is a story that reminds us of where we come from and hints at where we might go. And it is a story that, if we choose, we can continue to read, to write, and to live.